Welcome back, guys, and this is the Ultimate Microservices Bootcamp. Now, a few days back, I launched this video, which was building a massive Golang microservices project using GraphQL, gRPC, Docker, Postgres, and Elasticsearch. And I realized, and I've realized this before as well, that microservices concepts is something that's not easily available on the internet. And this is why what I did was I took a poll on my Discord community. And what we decided was that I'll work on this comprehensive microservices concepts course. It'll be a few hours long video, and then I'll start building the rest of the project. So I want to show more in-depth Golang microservices projects to you guys. And before I can do that, I wanted to at least take you through the concepts that go into building microservices, right? So this is what today's video is all about. This is what today's course is all about. And let me quickly show you what we're going to be covering. I'm basically going to be taking you through this massive board. It's a complete mind map board that I've created for you guys. And we'll go through this step by step. We'll cover each of these concepts. And these are all basically microservices related concepts. And before we do this, I have a presentation for you guys. So we'll go through a quick presentation, a few slides, like maybe 6-7 slides. And then we'll jump into this board. That's how I've planned it. Now, the link to this board, the board that I just showed you, the link to this board will only be available to my community on YouTube, the members that have been supporting me for many months. So there's Suresh, who's been on this since 22 months. He's been supporting me since 22 months. Rohit has been supporting me since 19 months. Tomas, I'm not sure if I'm pronouncing it right. He's been supporting me since 16 months. And Sambasivam since 10 months. So it's like because of the support of people like these that I'm able to do what I do. And the link for this board will be available to them. So I'll be taking you through the board, but the link will only be available to the community because I hope you can understand they've been supporting since like 22 months. It's not easy, and I have not been giving them much value, but I want to change that now, and they'll get way more than what they have paid me for. That's what I ensure every time in life, that I always over deliver on value for anybody who supported me. So that's how we're going to do it. Now let's get started with the slides. So in this bootcamp, we're going to learn the what, why, and how of microservices. It's going to be there won't be any coding. It's just concepts for the next few hours. And we'll first go through multiple perspectives on how to look at microservices and why it's important, and why do you even build microservices in the first place. Then we'll learn how to decompose from a monolith into microservices. How do you do that? Then we'll learn about inter-service communication and event-based architecture, and then we look at challenges and scaling. Okay, and the event-based architecture is going to be quite heavy, this part, so things will get intense in this section. So make sure you don't give up in the middle. don't give up, stick with it. And by the end of this video, you will have learned a lot. I'm going to be distilling my decade-plus years of experience, and also it took me about 5 weeks of effort to put this whole board together. So that's what you get in this video. I'm Akhil Sharma, founder at Armor AI, and I specialize in Go, Rust, software architecture, and building products that scale. You probably know that about me if you've been following this channel for long enough. And the reason why I'm teaching this is because I've taught microservices projects in the past, especially in the 56 Golang projects playlist. And I want to teach more, I want to build more microservices projects on YouTube with you guys. And for that, what I've realized is you need to know some concepts, and the resources and videos are not present online for those concepts. And even paid resources on the internet, like even if you buy paid Udemy courses or paid specialized courses, even for $1,000, you don't get that kind of information that I've tried to distill in this little free online course. And to be able to build scalable microservices, I believe it's 90% is concepts. Like once you understand everything really well, then it's just about execution, and execution is very little part of it. Because if you know the structure really well, it's very simple to build microservices. So that's 10% is execution. So if you know the what and why, it's easier to figure out the how, which the how is the execution, right? Like you can easily watch videos and build microservices, but you need to understand why you're doing it in the first place. So why are microservices important? It's because apart from helping you build great software, it's required and is in high demand in the industry and also in your tech career. And all senior level interviews have a good chunk of microservices. Like they'll ask you about microservices, because at senior levels, that's like you'll have to handle the entire architecture, the entire infrastructure of the product, and not just a small part of the product. So that's why you'll need to have a complete bird's eye view of everything that's happening. And getting a senior engineering job at any enterprise firm, especially the Fortune 1000 firms, requires solid understanding of microservices, because all the bigger companies like Uber or Netflix or any company that you talk about, Atlassian, any company that you talk about, they have adopted the microservices architecture, and that's what you'll be exposed to. That's what they'll expect you to know before you join any company, especially at a senior engineering level. So to be a great engineering leader, you need solid understanding of business, as you know, right? You can't just be a great engineer, you also need to understand how the business works. And the thing here is that to be able to build great microservices, you need a solid understanding of business as well. So you can't just build microservices if you don't understand the business and how it works. You have to be able to understand that and then build microservices from there. So the more you polish your microservices knowledge and concepts, the better you understand the business impact. And how are these related? So how are microservices and how is business related? That we will learn in the decomposition section in this course. So why am I the right person to teach this? Because I've built software for most of my life, and I've worked as a software engineer, technical product manager. I've ran tech consultancy for 5 years with Fortune 1000 clients. I've managed technical processes teams and led open source projects, and I've built and scaled startups. And my current startup, Armor AI, it's backed by Techstars and Outlier Ventures, and we're in the Google AI Startups program, the NVIDIA Inception program, and we have tens of microservices in our architecture. So this is my day-to-day. I do this on a daily basis. And also now I know how to teach really well, because I've been teaching online as a passion since the past 3 years on YouTube. And I've become slightly good at explaining things. So it's not only that I know how to build things, now I can say that I've also become really good at explaining things. So hopefully I'll be able to explain things to you in a way that it'll all make sense to you. And I also am an instructor with LinkedIn Learning. So I've built 3 very popular courses in collaboration with them. So if you're on the LinkedIn Learning platform, you can check out my courses. I have a Golang web development course and a Rust web framework course, and now a LLM cybersecurity course as well. And I'm a published author. I've written the book Rust for Blockchain Application Development. Okay, so you're in safe hands, you're at the right place, and you will get to learn a lot. So why do you need this in 2024? Here are some reasons. So what I think is going to happen is that what I know is happening in many companies is that the easier engineering related work is being automated by LLMs. So engineers, we need to upgrade ourselves. Okay, let me just move myself out to the side. Sorry. Actually, I'm not sure if in the previous slide I was still, like, was I in the middle? I'm not sure. Sorry if I was in the middle, really sorry. Now I've moved myself out for this slide at least. So yeah, so engineers will be responsible for handling more difficult and advanced work, and software will get more complex since it'll be faster to build software with LLMs. Okay, and architecture, like any software architecture, will get more and more complex because you'll have to call multiple APIs and you'll have to aggregate the results from those multiple APIs. And extremely complex architectures go really well with microservices. Now, because you'll have to call multiple APIs, maybe LLM APIs like OpenAI or Anthropic, or you'll have to deploy your own LLMs, or you have to call some APIs for external data or some payment APIs, right? So to do all that, and also to have your own business logic running at the center, and also your application to be able to work with multiple different softwares, you'll need complex architectures, but those complex architectures go really well with microservices. So this is the perfect time to upskill. Like 2024 is the perfect time to upskill. Okay, and why is this particular course special? Is because all of this knowledge that you'll get right now has been distilled from real world industry experience, and it's also completely free. It's like completely free of cost. And it's also taught by an industry professional and not a professor, and basically an industry professional who's built scalable software hands-on. And this, I believe, will be the most detailed resource on the internet. That's also going to be, which is also easy to understand. Not just the most detailed resource on the internet, but it's also easy to understand. And it ties in perfectly with my existing playlist. So there's my Golang projects playlist, and if you haven't checked it out, make sure you check it out. There's a 56 Golang projects playlist, so make sure you check it out. I also have a system design playlist, and I also have a technical architecture playlist. So this ties in really perfectly with these existing playlists. And this is available as a huge board or a mind map. So we'll be able to, we'll go through this board and mind map. It's very easy to revisit and understand everything again once you just go through this video in a very fast speed, because it's a mind map. You'll be able to go through it very easily. And if you're part of the members on my YouTube, if you're part of my YouTube, if you have my YouTube membership, then you would also have access to the board, and you can go through the board yourself. And this will actually serve you for life until you become the CTO of a huge company. So the way I've designed this board is that this is like evergreen knowledge, and like starting from 1995, when there was Alistair Cockburn on the scene, you know, whatever he's done, all of his work, and all of the works of great people like Uncle Bob. So I've kind of incorporated a lot of concepts from them as well. So it's all like very evergreen knowledge that will serve you till you become the CTO of a huge company. So it's going to help you from the beginning till the end of your career. Okay. And if you ever want to get in touch with me, it's very easy to get in touch with me through YouTube comments. I try to reply as much as possible, as you would know by now. The other place is the Discord community. So the link is in my profile. I am very easy to reach in the Discord community. You can always tag me, ask questions, whatever you want. You can also send me DMs on LinkedIn. I almost always reply. Or you can DM me on Twitter. So this is my Twitter handle. You can always DM me on Twitter. Okay. So now, what I need from you is I need you to comment, like, and subscribe to this channel. And I want you to share this video. So once you have done learning, once you have watched this video completely, I want you to share this video and this channel with your colleagues so that they can also learn and benefit from this awesome free resource. And you can share this on LinkedIn or Twitter by tagging me. That'll be like very helpful, because more people on Twitter then find out about this video, and that'll be awesome. So now let's get started. Now let's go to the board. Let's get started. Now on this board, I've mentioned some of the reference articles that I've used, right? You can read these in more detail. And I've mentioned that 99% of the images that you see on this board are drawn by me. That's why it took me 5 weeks to draw them by hand, because in many of the cases I didn't find the right images that I wanted. Actually the problem is when you look at these images, they're not the real 100% representation of how things actually work, and they're like really abstracted these images. So what I've done is I've tried to hand draw all of these images inside Whimsical myself. And in case where I have taken images from the internet, where I found images to be satisfactory and I've taken them from the internet, I have given credit. So in case you find something here that's not credited to the original author, please let me know. I'm happy to include the author's link there at that place. Okay. Now, if you look at microservices, so I'll just push this mic away. So if you look at microservices, right, this is the 10,000 feet perspective. Now, before I jump into 10,000 feet perspective, I'll just give you a 10,000 feet perspective of this board. This is a huge board. We have a huge number of things to cover. So just sit back and relax, okay? There's a lot of things that are coming up. But also, I want you to focus, because there's so many small things that are happening here that if you miss, then it becomes difficult to connect the dots, because the way I've organized this board is almost like in a format that it all connects to each other. Okay. So even if my head does come in between sometimes in the text, don't worry, because at that particular point of time, I'm not focusing on that text. So for example, if my head is here, I'm not talking about that text. So don't get worried that, hey, I can't see that text, because I'm actually going to be talking about this at that time. Okay. But I'll move myself out anyways for the time being. All right. So this is the 10,000 feet perspective of how a system evolves into monolith. So you into a microservices architecture. So you have you start with monolith, and you have your front end and back end, which are tightly coupled together. And this is what a tightly coupled software looks like. And what you start doing is you start dividing the monolith into smaller sections. And at that particular point of time, they're not really microservices. They're more like macro services. So you separate out the users, you separate out the products, you separate out the orders. Like let's say in a e-commerce setup, e-commerce project, you separate these out. So they become lightly coupled, but they can have strong interdependencies. So even though they're lightly coupled, here they were tightly coupled in the sense they were heavily involved with each other. Here they become lightly coupled, but they can still have strong interdependencies. And even though these two words might not make much sense to you, don't worry. And even if you don't understand why and or how we went from monolith to microservices and then to microservices right now, it doesn't matter, because this is what the whole course is all about. And this is what we're going to be covering in a lot of detail. But when you go from microservices to microservices, you stay lightly coupled, and you go down to the atomic level as much as possible. So you want to divide the services to as much to an atomic level as much as possible. You want to have clear separation of concern, and you want to have as less interdependency as possible. Okay, you don't want the modules to be dependent on each other. That's ideally how you want to divide things. So this is what the monolith would look like, and this is what, after you've divided it into microservices, this is how it would look. Okay. Now let's see what an online business looks like. So an online business, right? You obviously need to make it useful. You need to make an online business useful, which means that you need to build the right features for the right target audience, right customers, and then you have to prioritize things on the roadmap. But that's not our job. That's the job of the product managers. Our job is something else. So for an online business, it needs to be available, needs to be reliable, and you need to be able to make changes quickly to adapt, because competition changes really quickly in online businesses, right? New technologies keep coming up, new methodologies keep coming up. The online businesses need to be scalable. That's why people build online businesses, because they're extremely scalable and they can achieve global scale very fast, very, very easily. And new features have to be rapidly delivered, not just developed, but also delivered. And you also need faster innovation. So these are the things that are required for an online business. And this is where microservices come in. This is what microservices can enable. And this is why we're learning about microservices, because generally known benefits of following a microservices architecture that you'll also find on the internet are these, which is maintainability, modularity, evolvability, testability, and deployability. But the reasons to use microservices architecture goes way beyond that, and that's what we'll be covering in detail in this video. Now, a very important factor that's often ignored for a high velocity startup, right? So an online business essentially is a startup, like a SaaS company or like a e-commerce company. So what's really often ignored is the scalability of the team, because essentially there will be human engineers working on the product, right? Like building features and delivering those features. So you have to think about how the team is supposed to scale. And as the team grows, you need clear responsibilities and KPIs for the team members. And as the team grows, you also need clear separation of concern for all of the team members. So not only do you have to think about how the software is going to evolve, but you also have to think about how the team is going to evolve. And this is what we will also be covering in today's video. Now, there are multiple lenses that you can view microservices from. Okay, so there is the lens of the non-technical founder, or the engineering director. So an engineering director in a company or engineering manager in a company who becomes a director is like a non-technical founder. So in a small company, it will be a non-technical founder, or in a big company, it will be like an engineering director or a manager. Their job is around managing engineering teams and managing engineering processes, and not actual hands-on coding stuff, right? Whereas a technical founder or a CTO will think about uptime or availability. The non-technical founder will be thinking about the team's division of responsibilities, or how the team, or how you divide tasks between the teams and responsibilities between teams. He'll be also thinking about how the team is going to grow, how you can also leverage offshore teams to build features quickly. You'll also be thinking about how KPIs are being met. So now the thing is, with microservices, it's not only technical, it's also about understanding how teams and how structures, how companies, how processes, how the tech industry in general works. So that's why I'm exposing you to all of these topics as well, so that you understand everything from a very fundamental level. So the technical co-founder, the co-founder is going to think about the availability or the uptime of the software, the feature velocity, how fast are you able to deliver these features, the scalability of the software, the reliability of the software, and also the security of the software. And the thing is, we want to explore microservices from all of their perspectives, but I'm just showing you what each person is thinking of, right? So lenses basically mean that each person has a different perspective in the company. Now, an indie developer who owns a company and he's just an independent developer who's building products, shipping products, his responsibility is to divide work into different small microservices and distribute the work across the world to developers. And he doesn't really want to hire large teams. You must have seen indie developers on Twitter, right? These are basically people who are developing products on their own, not leveraging big teams, not building a complete startup. Then there's a software engineer who works in a startup or in a big company, and they are responsible for contributing to a small section of the software only. They're thinking about the life cycle of that particular small section that they're working on, and they're thinking about how to access these details from other microservices, how to access the details. So like, let's say they want to get some task done, they want to get some stuff done. Now they have to think about how they will access information from other microservices, how the data flow will take place, what kind of access and what kind of permissions they'll have. And they also have to think about data retrieval and data storage, or basically read and write from databases of those microservices or of other microservices. That's what the software engineering. So software engineer has a much narrower view, and a technical CTO would have a much larger view, and the non-technical founder would have a very different type of a view, which will be very team focused. Okay, so I hope you appreciate how different people look at microservices in a very different way, or engineering related stuff in a very different way. Now, a tech architect, his job is to worry about what technologies to build with. He's about thinking about how to set up communications either between different microservices or between different technologies, how to set up communications and how to set up maintainability, and what cloud technologies can be used. What technologies to build with and what cloud tech can be used, these are two different things, as you know. Then the DevOps guys are thinking about how will changes and deployments work. And they're also thinking about failure scenario mapping and failure reduction in the software in general, thinking about containerization and orchestration and logging and monitoring. They're thinking about all of these things. So everybody has a different way of looking at things. Now, what our job is going to be is to look at all these different lenses. So I'll take you through how a non-technical founder thinks about things and how he benefits, how he benefits from leveraging microservices, how a technical founder leverages microservices, how a tech architect benefits, how a software engineer, how a indie developer, how the DevOps guys, all of these guys, we look at things from their perspective. So let's get started with the non-technical founder, or you can also call him the COO. So as a non-technical founder, or the COO lens. So from his perspective, before I get into that, I just want to tell you that things will get very technical very fast in this course. But for what we're doing is, let's understand how a startup works. Let's understand how a startup becomes a full-fledged company and how microservices architecture gets adopted first. Let's talk about that. So first, you have a startup that just has 3 engineers when you're starting out in just a very small company, and instead of there are these three engineers that work for this company, and you usually have Alice and Bob. So I just removed them. I've put Alicia and Babu because I'm in India, and these are more culturally relevant names. So you have Alicia and Babu, and there's also me, Akhil, who are 3 engineers working at a startup when the company is starting out. And the company is an e-commerce software backend, like e-commerce software, you can say. And they have these 3 services. They don't have services. They just have these 3 functionalities like orders, products, and users. And or you can even consider that they have these 3 different services, and all of these are handling these 3 different services. Or you can consider that this software has these 3 different features or 3 different main modules, right? So right now the startup only has 3 engineers. That's it. But what happens is the users start loving the product, and suddenly there's a huge demand. And then what happens is, then you get a proper CTO in, like let's say Gordon, and then you put these 3 people who were the 3 engineers, the 3 founding engineers, under the CTO. So Gordon is the CTO, and we all 3 of us engineers are working under him. And now, because we've already built quite a lot of the product, they would probably make us engineering managers, and they will put engineering Golang engineers below us, so that we become responsible for their day-to-day work, and then we report to the engineering director. That's how the company can be set up. This is one very common way of how you set up companies when you start scaling. And at this point of time, let's assume the company has 10,000 daily active users, which are very solid numbers. and $10,000 monthly recurring revenue. This very solid numbers for a very young startup. And later on, when the company scales, so whenever you see this arrow, you basically, what I'm trying to say here is that the company scales even further. Company scales even further, and you get 10,000 daily active users, which is the same as before. Same with 100,000, MRR. But you've scaled in the sense of the amount of money raised. So you've just raised $10 million. And now when you have raised that kind of money, what you want to do is you want to have different KPIs people responsible for different KPIs, because you have to think of company in different chunks or in different modules in different business units. So there's one business unit responsible for orders, because there's going to be order dispatching and order canceling and people placing orders. You want to have all of that as a separate business unit. You want to have products as a separate business unit, because products are related to the inventory, the catalog of the products, and if some products are damaged, or basically managing products. And then everything will be related to users' personal information, their addresses, all of that, their authentication. So there are 3 different business units with 3 different KPIs. And what you can do now is, so we had that earlier, like we knew that the 3 different modules were there, but now they can be treated as 3 different business units with 3 different KPIs. And what you can start doing is you can start dividing that software into, you can give that software to 3 different people. So Alicia, who is the engineering lead now and who has 2 Golang engineers under her, she will be responsible for the first KPI, which is responsible for everything related to orders. And Babu is is responsible for everything related to products, and Akhil is related to everything related to users. So that's how it's happening right now. Now it makes sense to break down the software into smaller parts with clear responsibilities for the team. So so we had the e-commerce software backend, and now we have orders, products, and users, 3 different independent components maintained and managed by different teams, which now comprise the software. So this is what is happening here, right? Now you get a 10x growth in the revenue or the users in the software. So once you do that, you also raise a $40 million Series A round. So we raised a $10 million seed here. We raised a $40 million Series A round. We have now $1 million MRR and 100,000 daily active users, which is a huge number for a very fast growing startup. But now you want to start thinking about a lot of things, and especially once you raise this kind of money, like $42 million worth of Series A, you have to start thinking about growing the team exponentially, because you want more people responsible for handling this kind of growth, because you can't take chances anymore. You can't be like, okay, one developer is sick today, so we're not shipping features. You can't do that, right? Or one developer is not, has gone on vacation, so now suddenly, these users, they're not able to use the product. You just can't have that. So that's why you have like multiple developers. And now what's going to happen is when you have to grow really fast, mostly you don't get resources of the technologies you want. And you might end up hiring other resources. So if you remember, we were hiring mostly Golang engineers. We had mostly Golang engineers earlier. But now, because the speed required is very fast to grow the company, because we have $40 million, and you want to hire resources, but there are only a limited number of Golang engineers in the market, and you can't just hire them in 1 week's time. And you don't want to also do that because you want great engineers. You don't want just good Golang engineers, but you want great engineers, period, in the sense who can transfer into different technologies. So that's how companies think about things. They hire great engineers, not great Golang engineers or engineers of a particular technology. So you might end up hiring other tech resources, like maybe even Python or Node.js, because of availability, and even cost considerations. Because like, let's say a Golang engineer is $150,000 in the market. A Python engineer would be $120,000 in the market. So you save that $30,000, but you have one extra person who can be responsible when the software goes down. So you want to have like more heads in the software team. So it makes sense to further divide the microservices into smaller parts. Now you had the e-commerce software backend, and then in the previous stage we had 3 microservices: orders, products, and users. And now what you can do is you can divide the orders microservice into something called as order placement. So that becomes a separate small entity. And then, because orders has these three things, right? And there's also this invoice generation that's happening, and there's order tracking that's happening. So there are 3 different things. happening inside orders, and you can divide orders into 3 different things. Similarly, with products, you can divide that into catalog, into inventory management, into product recommendation. Okay, these can be 3 different individual independent services in, from products that are being derived. And then you have users, and users can be divided into user management and authentication. So users information, all of the users information and CRUD related stuff, and authenticating and maybe even authorizing the user can be something separate. So this way, now that you saw that the way that I'm dividing these services further into smaller parts, it might look random to you, or you might think that, okay, these are the different parts I can divide orders service into, and these are the things that I've written down here. But it might look random, but it is not random. It's a complete science, and we'll cover that in the decomposition section. So there's a complete section dedicated to how you start with monolith and how you start dividing that into microservices, right? So it looks random, but it's not random. There's a complete science around it. So what's happening here, when you have like $1 million MRR, raising a $40 million seed round, you'll have these 3 KPIs, responsible for orders, responsible for products, responsible for users. But Alicia, who had 2 Golang engineers under her, they become responsible for order placement. So if you remember now, because orders now has order placement, invoice generation, order tracking. So she has 2 Golang engineers working on order placement, 1 Python engineer working on invoice generation, and 1 Python engineer working on order tracking. Because so this can become this is a different microservice, this is a different microservice, and you can have this in Python, you can have this in Python. It's not a problem, and both of these Golang engineers work on order placement. Okay, and then Babu, who had 2 Golang engineers under him, now also has a Python engineer under him, but he also has a Node.js engineer under him. So the Node.js guy can work on inventory management, but the Python engineer can work for product recommendation. Now, when you see stuff like recommendation, when you see stuff like machine learning, AI, stuff to do with data science, Python is the right language to go for that, because Python has the most amount of libraries available. And we're working with backend services. Golang is a great option. Sometimes Node.js is also a great option. So that's why, depending on what kind of stuff you're doing, you'd want to use that language. And that just works really well, because we anyway had different types of engineers. So we have 2 Python engineers working on authentication, 2 Golang engineers working on user details here under Akhil, who's responsible for users, right? So users. So now when you think of the microservices, how they're divided, you also start completely equating that with the engineer. So this engineer is working on this, whereas the guy on top of him is responsible for this. So responsibilities are directly being mapped to the people in the organization, and that's a great way to look at things. And this makes everything very, very easy and very easily manageable for the non-technical founder, because now he can set different KPIs, he can make people responsible for different things, and he knows who to get in touch with when something doesn't work. And that's a great way to manage a company. So that's why it was important for us to look at things from a non-technical founder's perspective, because now you know how Monolith becomes a microservice, and how, from a team's perspective, everything starts looking, everything starts making sense. And now it's time to start looking things from a technical founder or a CTO's perspective. And now let's look at things from a technical founder or a CTO's perspective. So you have users. The users are making requests to our e-commerce software and getting back a response. But even if there's one bug, let's say in the entire software, and then that's particularly in the orders module, code of the orders module, even if there's just one bug there in just one place, the entire software becomes unavailable. Okay. And the user will keep making requests, but will get back no response from the e-commerce software. So technical founder, as you know, or the CTO, as you know, is more responsible for the reliability and availability of the entire system. So from his perspective, if you take the software and you have the software into multiple microservices, which is orders, products, and accounts, and now the user can make a request to the front end can make requests and get responses from each of the microservices. And then if there is a bug in the orders service and the order service go down, still products and accounts can still keep on going. That means the user will be able to come, he'll be able to authenticate himself because all the information is in the accounts, and then he'll be able to check out the products at least, and he won't be able to place an order, which is completely fine. At least the service is available. It's not like the website is showing a 500 error, right? And here, this is exactly what I've mentioned. I've mentioned that only the orders microservices goes down. Orders microservice goes down, and the software is still available. Like the entire website is still available. Users can log in, they can browse and add the items to cart, which is pretty good. Like it's half of the journey for buying. They just can't place the order right now, which is much better than having no website being shown to the user. So at least, because we don't even know if the user is going to buy or not, right? He's probably just going to browse through the products and add them to cart for later on. So at least those, users don't get a bad experience. So just by converting this software into small microservices, like 3 microservices there, you have exponentially enhanced the user experience already. Okay, because even if one thing goes down, the rest of the software is available. So now, let's say in the products service, when there's a hack going on, right? So if there's like a hacker trying to hack, look at the products, and then he's trying to call the products API, checking out, or trying to steal the list of the products, and maybe some competitor wants to do that. Some competitor hired a hacker to steal all of the list of the products, something like that maybe. You can isolate that. You can isolate the hack that's happening into that one microservice, and it doesn't affect the rest of the project. So, and most importantly, this is the one that you want to, isolate really well, the accounts microservice, because you don't want it to spill off into the accounts microservice, which actually has personal data of the users. And the other thing that you get a lot of help with when using microservices is the upgradability, because the CTOs are responsible for ensuring that the software is updated, right? And here, let's say if there's the accounts microservice, which is using GoGin, and the new version of GoGin is out, and you can isolate and only upgrade the accounts microservice. You don't have to upgrade the entire software, otherwise you'd have to upgrade everything else. Here you can isolate and upgrade just the accounts microservice without creating conflicts in the other microservices. That's very easy upgradability. And then the CTOs are responsible for innovation or new types of things coming out. So new innovative features, like for example, trying out Gen AI, where a user's video can be generated, where the user is wearing a dress, or a product recommendation AI. All of this can be done very easily with microservices. So innovation sometimes needs to be isolated as it moves at a different pace and velocity than the rest of the product. So what does that mean? That means that basically you had these 3 microservices, the orders, products, and accounts. And now the products also has one more microservice attached to it, which is the product recommendation, which takes in information from the products microservice. And then depending on the user's information, which it'll get from the accounts microservice, based on that information, it'll recommend the right products to the user. Okay, so you have your products microservice and your accounts microservice. And then there's one more microservice, which is an AI microservice that will check the fit for the user. So it generates the video for the user wearing that particular dress. And so these kind of innovative microservices, you can basically innovate without disturbing the rest of the software. So that's one more benefit of the microservices. So this is what it looks like from the technical founder's perspective. So now let's look at the same thing from the perspective of the technical architect. And now what he can do is he can have different types of databases for different types of services. So let's say if it's a payments microservice, he can use SQL for asset transactions. If he has the product details microservice, he can use a document DB because he needs a lot of information for the products, right? A lot of descriptions for the products. For the analytics microservice, he can use time series database, and for the products microservice, he can use NoSQL. For users, he can use the SQL database again. So this is a pattern called the polyglot persistence. I will talk more about it either in this video or in some other upcoming video, but this is what, in a very short way, if I had to explain to you, this is what it would look like. This is what the tech architect can now do. He can have different types of databases for different types of microservices, and this basically makes every single microservice more powerful, because you get like for payments you have something very specific, for analytics you have something very specific that's built for analytics, like time series. It really helps with analytics, right? And now the tech architect can also think of having different microservices for different types of different technologies for different types of microservices. So if you have the recommendation service, so since we will use machine learning libraries, it is best to use Python, since a lot of libraries are easily available in Python. So you can use Python for the recommendation service. You can, for the Gen AI service, for the innovation part that we talked about in when we were talking about from the CTO's perspective. So for the Gen AI also, you can use Python, because we might use the SDK for OpenAI or Anthropic. And the SDKs for Python, if you have noticed, are always the most updated and the most feature-rich compared to all other languages. So that's why it's a good option to use Python when you're experimenting with Gen AI as well. And let's say you want to scrape competitors, their e-commerce website. You want to scrape all of their products for pricing, so that you can optimize the pricing on your website based on how they're pricing their products. Then you can use something like Golang, because it has you're able to spin off hundreds of concurrent workers very fast with Golang. It has concurrency built in, and you can have a lot of fast scraping going on with the help of Go routines. So Golang is an easy pick here. So this also empowers the tech architect to not just select specific purpose-built databases for those particular microservices, but also he's able to pick different technologies for different microservices as well, based on what will help them perform better. So you don't have to build the entire project in Golang. You can build a specific small part in Python, small part in Golang. Now, with the help of microservices, the tech architect can also think about multi-cloud. So he can have AWS, since EC2 and API Gateway are available. So you can have the public APIs along with orders and products on AWS. You can have GCP for recommendation. So let's say you're building product recommendation. You can use GCP because you get Vertex AI, and has really good support for training your own models with the help of your own data. So I at least use Vertex all the time. So you can use a multi-cloud or multi-cloud configuration where you're using AWS at the same time you're using GCP, and using the choicest services based on what you want. So you could use, now you would argue that, hey, if I wanted to use API Gateway, why wouldn't I use GCP's APG, right? Because APG is like significantly more expensive and more difficult, or at least takes more time to set up than the API Gateway. So I end up using API Gateway all the time from AWS, and I like EC2 machines, the flexibility that I get there. From GCP, I always use the Vertex AI. And I use Azure for OpenAI, because I get OpenAI credits there. So for the Gen AI stuff, I'd use Azure. They have like really good support there. So this is what microservices enable. You can have multi-cloud. You can have different languages for different technologies. You can have different databases for different microservices. Amazing, right? So this gives you so much flexibility from a technical architect's perspective. Now, even from a communication perspective, so if the technical architect is now thinking about communication, you can think about gRPC. So let's say if you want to, you want to have communication or interactions between your products and recommendations, you can use gRPC there. Within orders and users, you can have gRPC there. But another way to do that would be you want to have recommendation, you can have products, orders, users, and if you have more microservices, you can just have Kafka there directly instead of streaming with gRPC. So you get more flexibility with communication. You can change the patterns easily. You can mix things up. You can actually use both at the same time also. And if not this video, then we'll talk about that in another video, how you can have different types of communications. You can even have synchronous and asynchronous communication at the same time in the same architecture. That is something that I talk about in this video at least. So you also have different types of data sharing patterns. So because the tech architect is now thinking about how each microservice is set up in terms of the kind of data that's going to hold. So for example, the orders microservice has the user ID, or at least it needs the user ID so it can get it from the user's microservice if it's storing the user ID. And then for that user ID, because that order it belongs to a particular user, and that order has a list of products. So if you want to get list of products ordered by that user, so you want to order that information from the products microservice. So how this information is going to be shared across different microservices, that's something, again, the tech architect needs to think about. This is something that they need to think about. And also the order in which the information flows. So for example, first you'll have authentication, then you'll have authorization, then you have the user's data. After the user has been authorized, so their email and their name, or email I think you've had before because of authentication, but yeah, any other information about them. the catalog of the products that you want to show to them, their particular cart and the orders that they've placed. So the information is moving in a particular direction. It's flowing in a particular direction in an e-commerce platform. So that is something also the tech architects are thinking about. So this is what microservices looks like from a technical architect's perspective. It gives them a lot of freedom for communication, cloud, languages, and database, and also they have to. It gives you a lot of flexibility and basically, yeah, flexibility for data sharing and data flow, but also it requires a lot of work to think about how it's going to happen. Now let's start thinking from the software engineer's perspective. The software engineer has to be mindful of many things because he's responsible for creating the actual schema for the microservices. So creating the schema for the microservices is a slightly challenging task, as you can see, because the databases are distributed across different microservices, right? So creating schemas for the databases can be challenging. And the focus is on keeping as less references as possible to avoid latency and complex nested schemas. So because you have data distributed across microservices, so getting access to data when you have to aggregate data, that leads to a lot of references and also leads to a lot of latency to access that data. And you end up with complex nested schemas because of the relationships between the data. And the CRUD operations on overly nested schemas can become difficult later on as the software scales. And then you also have to make the JSON ready for front-end display, which is a huge challenge because otherwise, in your front-end servers, if you do a lot of data processing, then you would risk overloading the front end. So you want to have as structured and as organized JSON data as possible from the back end being sent to the front end. And in many of the cases, when you're using different types of front ends, like for example the mobile front end and a web front end, you want to send different types of data. Maybe to the mobile front end, you don't even want to send all of the data, right? So the software engineer, even though he's focusing on a small part in the microservices, he's having to deal with the ugly details or the day-to-day of the microservices, which is like schema creation, JSON data, and CRUD operations, avoiding complex nested schemas. This is the work of the software engineer. Then the software engineer is also responsible for the project structure, because the project structures need to be very deliberate and meticulous to accommodate scaling of the code. Now, so not only is your infrastructure scaling up, not only are your number of microservices scaling up, not only is the amount of data in the microservices scaling up, not only is the communication between the microservices scaling up, not only is the team scaling up when you are scaling up the software, but also the code is scaling up. Number of files, the number of folders, all of that is scaling up, right? So this is why the project structure needs to be very deliberate and meticulous to accommodate the scaling of the code. One huge challenge with this is repetition of code across microservices, because once you have a little bit of code in the orders microservice, a lot of that is going to look very similar to the code in the products microservice, at least some of it. So there will be repetition of code across microservices, and a little bit of repetition is acceptable, but you need a predictable way to organize code across different microservices, or probably package the code into modules and then re-import them into different microservices instead of writing that code again and again in all microservices. Project structure needs to ensure new team members are productive as soon as possible after joining. So the thing is, what happens with companies is when a new team member joins, the new team member ends up taking a lot of time to understand the project structure and then start getting productive. What do you mean by productive? It's a huge metric. It basically means how many number of days did it take for the new engineer or new joinee to start writing some code or start making some meaningful contribution to the code base. And that's called as being productive. So it's a huge metric and a huge KPI for many managers to make the team members as productive as possible. And for that, they do all sorts of things like documentation, ensuring all the APIs are structured, maintaining proper API collections, all of that stuff, and obviously project structure. And this is a serious art in the sense it's not to be taken lightly. It takes a long time to ensure your team members become as productive as possible after joining. And best is to rely on industry standards. So what I recommend doing with project structures is that what you might do when your company is scaling is that you try to figure out an approach from scratch where you think that let's evolve the code base and then let's see what approach works for us. But instead of that, rely on what people have already done before and what works in the industry, because those industry standard best practices exist for a reason, because people have already had those challenges before you, and so you just adopt them rather than figuring out things from scratch. Because I have made this mistake multiple times where I thought, oh, I'm smarter than everybody else, I don't have to rely on the best practices set by other people, and I don't want to take inspiration, I'll just figure out stuff on my own as we grow. But it doesn't work. It's best to put your ego aside, and it's completely all right if you take inspiration, if you copy other people's work, completely all right. When it comes to project structure, I mean, at least how to organize your code, it's completely all right, not a problem. And for structuring a small scale project, you have to check out my recent Go microservices project. So if you are struggling with this, if you're struggling on how to structure a small scale project, right, you have to check out my recent Golang microservices project that I talked about, which is the 56th video, I think, in that 56 Golang project course. And then for medium and large scale projects, I'll be showing you these kind of projects in the future on how to organize them. Okay, but there are multiple different project structures that exist. Make sure you check out and check those out. And then if you go to GitHub and look at some great projects, you will automatically understand how they organize them. Then the developers are, the software engineers on a day-to-day basis, they have to worry about implementing the actual user flow. Now, the product manager, along with the user UX designer, they design the user flow. But implementing that user flow is the responsibility of an engineer. So even if you're not a front-end engineer, you have to think about, and if, let's say you're not a front-end engineer, you're a back-end engineer, you have to look at the screens, you have to think about how the user is flowing through those screens, because that's how you'll build your APIs, because that's the information you want to show in those screens, right? So that's how you'll build your APIs, that's how you'll interact with the front-end engineer, sit down with them, and then understand what kind of data they need, and then you'll bring about that kind of data. So the implementation is the responsibility of the engineer, and this is what the user flow would look like. User will log in, view personal profile or change password, view other people's profile, add friend, block user. This is like a very social media-ish user flow. So, but when it comes to microservices, special care is required because of the components. So in front-end design, right, the designer would create some components, and the front-end developer would be working on some components, and he'll be responsible for showing some content for that component. So as software engineers or backend engineers, probably, you'll have to think about which components data is being fetched from which microservice, because now we don't have like a monolith project, monolith software, we have microservices, and each microservice has probably its own database, which is also called as a database per service pattern. I don't cover that in this video. For that, I might have to make another video for those patterns. Like sometime back, I also talked about one more pattern, right, which is the polyglot persistence. Yeah, so for database per service pattern, what basically that means is you have multiple databases. You have a particular database for a particular microservice. So each microservice has its own database, and so now you want to have to worry about for that component how data is fetched from different microservices. Okay. And processing the data efficiently to put as less load as possible on the front end. So you want to be able to process the data efficiently, and you want to put as less load as possible on the front end. Okay. And for simpler fetching of information, so you can keep the logic on the front end super light, a great practice is to use GraphQL. Now, the reason GraphQL language was not language, the GraphQL, like the standard for building APIs, why, even though it's called the graph query language, why the standard was created was because they wanted to keep the front, like the mobile front end very, very light at Facebook. So they created it so that they don't have to send a lot of data, and then you can have like the mobile front end can stay very light, basically, right? So like in case you want to use, if you want to learn GraphQL, I mentioned that I have shown how to use that in practice in the Golang microservices project that I launched a few days back on YouTube for free. So check it out for the actual implementation. So yeah, that's a great practice to use GraphQL. And then I always recommend using GraphQL, because if you have a front end that's calling microservices, you don't want the front end to be struggling a lot with trying to call data. But I don't recommend exposing GraphQL if you're integrating with third-party software. For that, use REST, because that's just much easier, and that's the industry standards followed to interact with other third-party services. But yeah, if you have a front end that's interacting with a microservices background, GraphQL is pretty a very good way to go. So now, not only does the software engineer have to worry about implementing the actual user flow, they also have to worry about repository and contribution management. So how are people going to contribute to the repository? How are they going to merge the changes? And basically setting up the Git flow, that's in essence, that's what you have to worry about. So this is everything from the software engineer's perspective, because all of these things that we talked about, like thinking about how the front end is going to process the information and access it, and how the actual user flow is going to be implemented based on the screens and the components, how the repository and contribution management is going to go. All of this is going to get affected because now we have microservices, and the project structure, the actual schema, all of that requires a lot of changes and a different way of thinking, because now we are going to be following microservices, right? So the next is from the perspective of the indie developer. Now the next is the perspective of the indie developer, and indie developers are people you've seen on Twitter, mostly people who have a very small team or sometimes no team at all, and they're just building softwares and building multiple products, launching quickly and building in public, those people. And they build mostly everything on their own, but occasionally take the help of other engineers across the globe. That's how their model works. And their budget is very low, usually very low, because they're mostly bootstrapping it. They don't really raise any capital. And their budget and also their resources are quite low. They also face big threats from VC-funded competitors. So they need to be nimble. Nimble basically means they need to be really quick. They need to keep shipping features, but and also they cannot give access of their entire repo to another developer. So they need to be careful. They need to give access only to the parts of their software to other developers. They can't give access to the entire project. And they need to maintain a level of abstraction between different engineers working on different features. So because many times the engineers who are working on the projects, they don't know each other. So they want to maintain a level of abstraction between them. So coming back to low budget and low resources, since they have low budget and low resources, you might think that microservices are not possible because they require more budget and more resources, but that's not actually true. Microservices can actually be a great option even with low budget and low resources. So let's take a look at how microservices benefit indie developers. So smaller microservices basically mean that they can distribute work across the globe. So somebody sitting in the US, an indie developer sitting in the US or in Europe, they might want to get people from the Philippines or Thailand or from India to work on their microservices because of the arbitrage, as you know. So let's assume let's consider a CRM software which has all these modules: contacts, accounts, leads, and deals. And if they want to update anything in the deals logic, they can give access to they don't have to give access to the entire code base and deployment for the project to an external member. They don't. But if this was a monolith, they would have to give access to the entire code base and deployment for the project to an external member. But we don't want this to be a monolith. So what we'll do is we'll divide that into multiple microservices. So the microservices will now be accounts, contacts, leads, deals, and sales intelligence. And if there are any important updates to the deals, like here, we were considering, if there are any important updates to the deals logic, in this case, it will be the deals microservice. Here, they had different logic, but it was the same monolith software. So here, that particular microservice can be updated in Philippines. And there's another microservice called the sales intelligence microservice, where some predictions need to be done on how many deals you'll close this month, that kind of stuff. And that new microservice to be developed can be sent to India to like really high quality developers, AI developers or whatever, machine learning engineers. So you can, now you can give access to only a particular microservice, and as an indie developer, you want less headache. So you can give end-to-end responsibility of a microservice to an engineer across the globe. So that means that the person in India doesn't need to know how the rest of the software works. They can just give them the sales intelligence piece and tell them that, hey, you'll receive this data, and then you need to do these calculations and get this output. Similarly, with the deals guy, you just need to give him this access to this deals, and you can give him end-to-end responsibility of the deals microservice. So that's how you can divide work across the globe, depending on where you find what talent, depending on the pricing of that talent, and so on. So the other benefit that you get is modularity, which means that all pieces of the software fit together nicely like a puzzle. So I've shown a hexagonal kind of a application architecture here, where you have accounts, contacts, leads, and deals. What that means is everything is modular and compatible. And how do you ensure modularity or easy compatibility of microservices when working at scale? When working at scale, in this case, I don't mean scale at like millions of users and hundreds of team members. What I mean is, even if like there's like 7-8 microservices, that's completely all right. At scale, what I mean is like at a global level, you have outsourced work. So what you can do is you can think carefully about the data that will be shared, what will be the fields, and you can think carefully about how the schema is structured. A lead and a contact both have email details, for example, and where would you want to store it? So saving email twice may create data integrity issues. So what I'm trying to say here is that in a CRM, leads and contacts. So contacts after a while actually turn into leads. You know, once contact is somebody you meet, let's say at a conference. Lead is somebody who's actually interested in buying your product. So it takes a lot of warming up to make somebody from a contact into a lead. And both of them have email addresses. So do you want to store it twice, like in the contacts microservice database as well as the leads microservice database? Do you want to store it twice, or do you want to store it once? If you want to store it once, where do you store it? But ideally, you'd want to store it twice, but that may lead to data integrity issues. So you want to resolve all of that. You want to think of all of that, because you are distributing work across the globe to different people who don't know each other, different developers, and you don't want, you want some layer of abstraction between the developers. So how do you create the microservices to be so modular that even if this developer doesn't know about this microservice and this developer, they're still able to work on the same project together without creating data integrity issues? That's the whole art here. Then you want to also have you also want to have similarity in the file structure across services. So because when you work with multiple engineers who don't know each other and who come from different cultures or from different type of companies or different skill levels, they work with different project structures, right? And so that means if you have given one microservice to an engineer in India, another microservice to an engineer in the Philippines, and they're responsible for the end-to-end delivery of that microservice, they would start creating different file structures. So you'll end up with different file structures across services, but what you want is similarity in file structure across services, because so that you can predictably find the file and function you could require quickly whenever you want to update later on, or when you want to transfer the work to somebody else, so that the entire software to you as the indie developer looks consistent. So that is also a skill set, right? And obviously the word modularity comes from modules, meaning sharing functionality across microservices, but by isolating important functionality into modules. So you'll take some important functions, you'll package them into modules, and those modules can be imported into different microservices. So that just makes things easier for different people working on the project. And in case of indie developers, it makes sense to have same language across services. So remember, previously I mentioned that you can have Golang, you can have Python, you can have JavaScript, different types of languages across different microservices. But if you are an indie developer, you don't want to have the hassle of learning multiple different languages, because at the end of the day, even if you have developers working for you, you might end up making changes to those microservices on your own later on when you don't find the right talent or you run out of budgets. So that's why you might want to have the same language across services. So that's how microservices look like from the perspective of an indie developer. And you'd want modularity, you'd want to divide into multiple microservices, so you can divide work across the globe depending on your budget and your resources. Then comes package version management. So you need to give detailed thought and you need to have clever management of packages, external libraries and SDKs used. You cannot have different versions used across different services, because that takes a lot of maintenance. So if you're having multiple microservices, you need to make sure that Gin is in the same version. You can't have Gin 2.3.5 in contacts microservice and deals will have 2.4.7 and leads will have, because that will create a big problem later on for the maintainability of the software. You want to ensure that all of these are running at the same version. So yeah, so those are two big changes that indie developers need to think of. One is that maintaining the same versions across different microservices, and the other is sharing functionality with the help of modules, and also having the same language across services. Okay, so that's everything from the perspective of the indie developer. Now, the other is the last perspective is from the perspective of the DevOps guy. Now, from the DevOps engineer's perspective, this is what's happening. So for the DevOps engineer, they get something called as ease of deployment, because now you have multiple services but each service can be contained inside one container. So it'll be very easy to know how containers will be set up, because you can have different containers for different services. So each service will have their own container. So for example, there can be one container running the leads server, the another container running a deals server, right? So you have CRM, you have leads, deals, you have the front end, which is React.js. So container 3 will be running the front end. Then there will be two more containers which can run the database servers, which these will interact with. And because of microservices pattern, it just makes it very easy to distinguish and to differentiate which servers are running on which containers. So you could be using Docker Compose or Kubernetes, doesn't matter. Whatever you're using, you can have multiple containers, but whatever you're using, you can use these to orchestrate those containers. And what you get is you get ease of scaling. That's the second thing you get. So that means if the leads server, this one, is getting more load because leads are exponentially higher in number than the deals. Okay, so what happens is when you have a CRM, and when you build a CRM, you have a lot more number of leads than number of deals, because not all of the leads lead into deals getting converted. So that's why the number of leads would be exponentially more than the number of deals. And that's because only a tiny fraction of leads end up in deals. So specifically, lead server can be scaled. So I don't want to scale up my front end, don't want to scale up my deals server. All I want to do is I want to scale up my lead server, because that's where a lot of data is being generated, right? And because let's assume I'm a salesperson, I'm adding thousands of leads, but only a few of those, after I have warmed them up enough and I've followed up enough with them, only a few of those will actually lead me to closing some deals. So these will be exponentially more in number. And let's say I create one more. So I had like 5 containers here. I create one more container called container number 6, and that will house another lead server. So I can scale. So here you can see that leads, there was only one container. Now there are 2 containers, so 2 different lead server running, and they're both talking to the same MongoDB server. Here they were talking to the MongoDB server. The container 1 was talking to MongoDB server. Here both of these are talking to the MongoDB server container. Okay. And the deal server is connected to the Postgres server. So I'll just complete the diagram here as well. So lead server was talking to MongoDB. Deal server was talking to the Postgres. This was connected like this. So here all that's happening is we are able to scale very easily, just increase the number of containers, the number of servers running inside the container also. So basically, because there's one server per container, so you have 2 containers, that means 2 different servers running for leads. And that ways we can handle the number of leads being generated. And then you also have extreme flexibility. So now let's say multiple lead server containers, but limited database containers can lead to slower reads and inconsistent writes. So I can, so now you just saw that I have 2 different lead servers and only one MongoDB server. And then because I said the number of leads being generated are a lot, so you can create a larger machine. You can shift this from a container. So you can remove the container aspect. You can shift this directly to an EC2 machine, the MongoDB server. So you can do that. So you can switch to a full server for MongoDB, or the second option is I can use a fully managed Atlas server from MongoDB itself. So there's extreme flexibility that I have. Not only do I have the ability to scale, I also have the flexibilities that I can switch from a container to a server directly, a full machine, or I can switch to a fully managed Atlas service. So I have all of these options available when I'm using microservices architecture. And then you have distributed tracing, and when I say microservices architecture, I'm saying that I'll have this independence for all of the different microservices, right? So one microservice could be running with the database on the server, one microservice could be running on the database on a container, like it's happening here, another like it's happening here, and another microservice could be running with a database that's fully managed, right? This is something you can't do with monoliths. Now the other benefit you have, other thing that you want to think about is distributed tracing. So you want to collect logs from all of these different servers, but you need something called as central monitoring. In the sense, the DevOps team needs a central dashboard where they know what's happening in which server, where exactly. Okay, so that's kind of important. So you might think that when the software is a monolith, we know exactly what's going wrong where and where, because it's a single unit. But in reality, it's much simpler to detect, locate, and isolate issues in microservices with the help of distributed tracing, where you are creating detailed logs of each service. So what basically what we are saying is, that we might think that monoliths are easier to manage and it's easier to generate like collect data and collect analytics and collect logs from monoliths and to know where the issue is, but in reality it's actually much simpler to detect, locate and isolate issues in microservices because we have the help of distributed tracing, and you can create detailed logs of each service. So what's also important is central monitoring, meaning having a unified dashboard, this one which I've shown in the diagram here, where you can identify the issues taking place in the various services. So even if you have like multiple services, you don't have to go like log into this server and know what's happening, like check out the logs there, on log into this server and then check out the terminal and see the logs here. You can have like a central database, and all of this is getting reported to the central dashboard, sorry, I meant. And the other best part is you have granularity of reporting and levels. So we can set logs at any level and at any detail. So you can have Kubernetes cluster level logs, okay, or you can have Docker container level logs. You can have server level logs. You can have the actual server, which is Go or Docker, running on the container level logs, and you can have the server OS, whatever OS is running, that level of logs. So you have different levels and granularity, like how much detail you need and at what level you'll be able to get all the details that you need. So that's from the perspective of DevOps. So by now what we have done is we have covered quite a lot of stuff, and we've seen microservices from the perspective of all of these different people, from the perspective of a non-technical founder, from the perspective of a technical founder, indie developer, software engineer, tech architect, and DevOps. And what that means is you now have a great understanding of what microservices are and why they're helping all of these people, and why they help companies, and why you would want to go for microservices. Now in the next half, like going forward, we are going to get a bit technical. So we're going to talk about decomposition by different methods. We're going to talk about inter-service communication and scaling client problems and solutions to those, and then events and event-driven architecture. So a lot of stuff, a lot of technical stuff coming up. So brace yourself. And then a little bit of event processing and how that differs from batch processing, scaling event-driven architecture. But before I get into all of that, just want to tell you that I'm working on a course, and it's called the Ultimate Golang Bootcamp. So as you know that I have 56 Golang projects playlist on YouTube, but what I've never taught are the basics of Golang. So if you've ever felt like you're working with Golang, but you don't like grasp all the concepts at the fundamental levels, and you need to polish those basics up, so that you'll be able to build anything in the future, like because you have strong fundamentals. And this course is going to help with that. And I'm building this because I have a lot of demand on my Discord community for this course. Everybody's asking for it because a lot of people have built all those projects, but they still struggle with some of the basic concepts. So what I've done is I've created this table of contents, and where we're going to cover the basic language foundations, functions and closures, pointers and methods, file and image handling, data manipulation, error handling, advanced type system, concurrency and parallelism, control flow, logging and testing, networking, project structure, dependency management, performance optimization. So I've started working on this course already, and you can pre-register for this course. So this course will be priced somewhere around $150 or so, and it would be more than 8 to 9 hours, between 8 to 10 hours, or could be less, depending on how much time, but I think it would be around 8 to 10 hours because there's a lot of stuff to cover. And what you can do is there will be a Google form link in the description of this video, so you can click and fill the form to show interest, because I've not finished this course yet, it's not released yet, but if you pre-register for this course, you get a 25% discount right off the bat, like no questions asked. So because it just shows me that you're interested, and and also you get to kind of define the roadmap for this course. So in that form, you can tell me what do you want me to cover. If you want me to cover anything else apart from this, so let me know anything special that you want me to cover, and I'll do that. So that's a great way for you to learn, great way for you to polish up your fundamentals. So the link for the form is in the description of this video. Make sure you fill that form up if you want 25% discount on this course. And now what we can do is we can go in like head first into the technical stuff. So this is the million-dollar topic, which is decomposition. And what this means is, how do you move towards microservices? So when you have a monolith project, how do you decide what are the right microservices to create from that? And you can't go about it in a very random manner. You have to, there's basically a science around it. And the first method that you use is something called as decomposition by business capabilities. So let's say you have your entire backend logic. This is your monolith. And your monolith can have different business capabilities. So for example, subscriptions and invoices is a completely different business unit. Video streaming is a different business unit. By business unit, I mean, like let's say they have their own KPIs, they have their own set of functions, because let's say subscription invoices, these will be people who will be responsible for ensuring that the software does not have any churn. Churn basically means that users falling off in the next month. They're ensuring payments, they're ensuring reconciliation with the bank. So they're ensuring all of these things. So that's subscription and invoices. And the video streaming people would be like a separate business unit which are responsible. I'm giving you the example of, let's say, something like Netflix, right? So video streaming are people who are responsible for doing partnerships to get more videos and shows, more movies and shows onto the platform. So that could be one business unit. And then admin and operations could be another business unit. So these three different business units can, like let's say if they exist in the company, then you can start breaking down your backend logic into these three different microservices. So automatically they have like a one-to-one relationship with the business units, and that's how you get these three different microservices. So you decompose business by business capabilities. Now I've shown you only 3 microservices here, but a business, an actual running business like Netflix, like a big company, or even a smaller company which is like Netflix, like a video streaming service company, they would have many more business divisions, right? So you'll have, based on that, you'll have more different microservices. So that's one, which is decomposition by business capabilities. And then you have something called as decomposition by subdomains. So in between those business capabilities, you'll have more divisions. So for example, with subscriptions and invoices, you'll have 2 types of things. One is recurring payments, retries, discounts, and the complete logic. And the other side could be invoice generation, formatting of the invoice, emailing those invoices. So that logic basically. So inside subscription invoices, you have 2 different logics. So you can divide that with the help of those subdomains. And video streaming would have multiple logics, like for example, there will be metadata, there would be video encoding and transcoding, there would be the thumbnail generation logic, there will be captions generation logic. So so yeah, all of these are different subdomains within the same business capability. So you start with business capabilities and you reach this stage, and then you take that forward and you decompose with the help of subdomains. So subscription invoices, you got 2 more microservices here, and from video streaming you got 4 more microservices here. And from admin ops, you'll get the logging, monitoring, and reporting. So that's a function of admin and operations. Then you get the video uploading. So you have the videos, but uploading them and ensuring that everything, like all the data is there. And usage-driven dashboards for each of those videos. All the analytics, archiving all of those videos, etc. Those are all admin and operations functions. So that's how you're decomposing with the help of subdomains. Now there's one more method called the decomposition by transaction. So the first step is to figure out all the actions that take place in the software. So for example, in an e-commerce, you can think of these different actions that are taking place. So yeah, so there are these 2 ways, which is with the help of business capabilities or subdomains, and the other way is with the help of transactions. So you can think of all of these different actions, which is creating an order in an e-commerce is one action, updating the order is another action, canceling the order is another action. Then you have deduction from item count for that inventory, the product that you just purchased. So that's one action. Then you can restock the item once it's back in stock. That's another action. Then you can create the shipment. You can update the tracking info. Then you have order confirmation, shipping notification, and delivery confirmation, all of these different actions. Then you have processing the payment and refunding of the payment. So all of these different actions in an e-commerce platform. Now what you do is you start grouping up these actions together. So creating order, update order, and cancel order, all of these can be grouped into an order microservice. And the deduction from item count and restock item can be grouped together into an inventory microservice. And creating the shipment and updating the tracking info for that shipment can be a shipping microservice. So what you're doing is you're just taking all the actions and then grouping them together into microservices. And you have order confirmation, shipping notification, delivery confirmation, all grouped together into the notification microservice, and process payment and refund payment into the payment microservice. So this is what it looks like now. So e-commerce will have the order microservice, inventory microservice, shipping, notification, payment. So so this was a very, very quick and very, very nice way, which is decomposition by transaction. This is what I really like. This is what I use most of the times, because even if, mostly I've built startups and I've mostly worked at smaller companies, startups mostly. So I've not had, but I've had clients which were Fortune, 1,000 and enterprise clients. There you could do all of this, but mostly in the companies that I've worked in, the startups that I've built, mostly this is what I've done, because we have not had like different business units and different business functions, right? We had like a very small team of, let's say, 10 people. 8 of them were developers. Just two people were like designer and marketing people, and even those 10 people were not like on full-time payroll. Some of them were freelancers and working on contract, right? So this is what you would ideally want to go with when you're working with smaller teams and startups, and like a very quick way to find out which microservices to have. So this is a great way to determine that. Okay. Now the next thing I want to cover is the strangler pattern. This is something that's very important. Now even though all of this might seem like all of this is like you're not learning much. You might feel like that right now, but in reality now, when you go out into the world and you want to take a monolith and divide that into microservices, now you have like a real actual framework on how to go about doing that, and it's actually very powerful. When you start applying it in the real world, you'll feel like you know a lot now. So it's just one of those things. When you feel like, when you're learning it, you feel like, oh, it's not that much. But when you actually apply it, you come to know how powerful it is. Now, the next thing is something called as a strangler pattern. So this is, I have included this here because I've had so many questions around it, and I've had so many problems around it, that when you actually have a monolith software and you want to divide that into different microservices, how do you do that? Because do you suddenly just take a monolith software and suddenly 3 days later it's all microservices, and now when you already have users, already have systems that are working, suddenly so many changes, how will the system take so many changes? And that's where strangler pattern comes in. So you have your monolith functions, features, and along with that you start making your microservices coexist along with those monolithic features. So you don't completely just delete or eliminate your monolithic features. You bring your microservices along with the monolith. They both coexist at the same time for some period of time, and then you can eliminate your monolithic features. So during the decomposition phase, you decided to introduce new microservices, but how will they be introduced into the cloud infra from a DevOps perspective? Because it's risky to suddenly introduce a big change. So this is solved with the help of the famous strangler pattern, where monolith features and microservices can coexist for some time, and then slowly the monolith feature is removed. This ensures no sudden jerks or shocks are introduced into the operations, and your users don't start facing those login problems, or suddenly your data is not there. They won't face those kind of problems. Now, the other pattern that I talked about earlier, like about 20-25 minutes back, I talked about this. This is called the database per service. This is what I usually use a lot from personal experience, which is each microservice will have its own database. It's just much more stable. That's what I've found. And the benefits of that is that your microservices become like very loosely coupled. So you don't have a lot of interdependence between the microservices. So you can choose different databases everywhere. So you can have Cassandra in one microservice, Redis in one microservice, CockroachDB another, CouchDB another, MongoDB another. So depending on the use case, you can have a different type of database. So let's see what I've written. So I've written that you have decomposed the monolith into microservices. Now each business unit might be having different type of data and would want to store it in a different way and also run different types of operations on it. And how do we reconcile these differences? So with the help of the database per service pattern is how we reconcile those differences. So let each business unit own their own data. So all of these, like the payments is a different business unit if you're thinking from the business capabilities perspective. Invoicing is a different business unit. Metadata and authentication could be different business units. So let each business unit own their own data, because some of these units have sensitive payment related information, right? So this business unit will have sensitive payment related information. You don't want to, that to be exploited. Or PII, which is personally identifiable information, which will be in the user's microservice, which might need added layers of compliance. So you would want to have added layers of compliance for your payments microservice and added layers of compliance for your authentication microservice. Now, you need to know that compliance is extremely expensive to maintain over the entire architecture, because you have to do some things monthly, repeatedly, to ensure that your architecture is compliant. But with compliance, what you can do is you can have in some cases you can have compliance like very strict, let's say GDPR compliance only on the user's PII data, and you don't need that on metadata or invoicing, maybe. So in that case, what you can do is you can have added layers of compliance only on some microservices, because it's extremely expensive to maintain over the entire architecture. So it's always wise to isolate compliance by simply using the database per service pattern. So what's the added benefit? You can use, so I think I've mentioned that already. You can use Cassandra, Redis, Cockroach DB, blah 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 blah, for different microservices. All right, so this is what we wanted to cover, which is decomposition. So now you know how to decompose with 3 different methods. So you have with business capabilities, with subdomains, with transaction, and you know how to bring about how to introduce those microservices into the cloud infra slowly over a period of time by making them coexist with the monolith, and you know the benefits of using database per service. All right, so that is decomposition. Now let's talk about ideal microservices characteristics. All right, so let's look at the ideal microservices characteristics, or basically how each microservice should be. So each microservice, this is basically on what I believe what each microservice should be. So each microservice should be easily or highly testable, and it should be loosely coupled. We've already determined that. I think that's already discussed. And this is important. It should be independently deployable, in the sense when you're deploying one microservice, that should not need you to change or redeploy any other microservice. So it should be its own independent thing, right, when it comes to deployment. So this just makes it really simple for you to remove a microservice or add a microservice or redeploy a microservice. It just makes it very easy from a DevOps perspective. Then you have organized around business capabilities. We've discussed this and how you go from monolith and you take business capabilities and how you start dividing that into microservices. We've just discussed that. And then you have your subdomain driven and DDD. Now DDD is something that I will have to cover in a different video, in an architecture video. I have that at the back of my mind. I could have covered it here, but the thing is, it's just more related to architecture and it just requires a little bit more time to explain. Now the last thing is that each microservice should be owned or could be owned by a small team. And we have seen this in the example where we saw, where we were looking at microservices from the perspective of a non-technical founder. We saw how small teams can be organized around microservices and how you can make a small team responsible for a microservice. So those are the ideal microservices characteristics. According to me, this is at least what an ideal microservice should look like, or how it should be organized or developed from the ground up. Now, this is one very common question. So I've talked about microservices in the past on some popular edtech platforms, and the kind of questions that I used to get was, is there like a limit on the number of microservices, because you can end up creating a lot of microservices, right? And you must have heard stuff like this. If you go to Medium and read a lot of articles on Medium, you've seen something like this, which is Netflix has 1,000 microservices and Uber has 4,500 microservices, right? So like what's happening here? Why do they have so many microservices? Is there like a limit on the number of microservices you can possibly have? And that's something to think about, actually, and that's why I have these 8 points that I want to take you through, because this question will keep coming up again when you build microservices. So one thing is managing microservices at scale is not very straightforward. So it is tempting to subdivide functionalities into more microservices. So once you do that business-driven thing, business capabilities thing, and then you do the subdomain thing, and then you probably, or you take the different approach for the transaction-driven thing, you reach a number of microservices, and then you think, okay, even this I can apply the same framework, and I can reduce that also into smaller microservices. And it is tempting to keep subdividing functionalities into more microservices as the company grows. But just be careful, at no point should you have more microservices than you can handle. So what that means is, what I've realized over the past decade is that for an indie developer, like an independent developer, a sweet spot is 6, because they have a very small team, like maybe 1 or 2 full-time engineers, and then rest of the team is freelance or contract-based or task-based even. So sweet spot is 6, because even if you had to do all the work yourself as an individual person with no support, you can still handle about 6 microservices from personal experience. This is like from personal experience. But if you're a small startup, like let's say you have 2, 3, 4, 5 engineers now and a small marketing team and all of that stuff, then 8 to 9 is a good number, assuming you know what you're doing. Okay. And is there such a thing as too many microservices? Because like I said, Netflix has 1,000, Uber has 4,500. So the short answer is there is no such thing as too many microservices. It's just disproportionate to the size of the team and the users. So you can have like 1 million microservices. There's no limitation, but is your team proportionate to that, and is the number of users you have, is that proportionate to that? Because you possibly can't have more users than Netflix. I mean, unless you are bigger than unless you are a bigger company, and then there's only that like a finite number of people on the globe, right? And Netflix has quite a lot of users. So there's no such thing as too many microservices, just disproportionate to the size of the team that's handling the microservices and the number of users that you have. Meaning, if you have a team of 2 engineers but you have 100 microservices, that's very, very wrong, because they obviously can't handle that kind of work. Or if you have just 10 users and you have 25 microservices, that's also very wrong. So it's always about disproportionate. So there's no absolute limit. It's just very relative to how many users and how many team members you have. So this could be a question. So like, let's say if you are appearing for the role of a very senior engineering leader in a large company, this could be a kind of question that would be asked to you. So if microservices are so great, then does that mean monolith is an anti-pattern and monolith should not be used ever? So the answer is no. When you start learning how to build things, like let's say if you go to YouTube today, you start picking up a project, you start building along with it. Even my projects, the 55 Go projects, for example, from my YouTube, what we've built monolith projects. That's what we've built, right? And the 56 project obviously is the microservices one. That's why I'm talking about 55 projects from those 56 are monoliths. Now, but when you start to scale them in terms of users, data, team, or just traffic, and the frequency of users and the APIs being called scales up as well. So not just the number of users, the amount of data, and the amount of the number of your team, or just the traffic, which traffic includes the frequency of users and APIs being called. You might like to introduce microservices. So when you're starting out, when you're building stuff, when you're just messing around, microservices is not really important, but once you're starting to scale, that's when it's important. So it's important to note that a microservice should only exist to solve a problem and not just randomly. It shouldn't just randomly exist. Okay. Now, there are some challenges with microservices. Okay, and these are just some of the challenges that we're talking about. But the actual challenges we're going to cover much later on, which is here in the somewhere around here, which is all the challenges with microservices. We're going to discuss them here, which are a lot, but that'll come after some time. But these are like some of the challenges that I want to talk about, because this kind of leads, this actually leads into a very big topic, which is inter-service communication. So that's why I wanted to just highlight some of the challenges here. So don't think of this as the exhaustive list of challenges, because we'll cover that actually towards the end of the video. So some challenges with microservices. So before we dive deeper into microservices more, we need to know that it's not a perfect solution and it has various challenges. It's best to know that now so that we can find ways around them. And here you see all these microservices, but what's actually happening here is this is called as the big ball of mud of communication. So if we are not careful about how communication between these microservices, because you know microservices don't really exist in isolation, right? So if there's an e-commerce platform and you have the orders microservice, the authentication of the users microservice, and you have the products microservice, they all need to talk to each other and they all need to discuss and share data. So the user, the order belongs to the user is browsing the products and adding them to the cart, right? And the one order has multiple products. So all of these are linked to each other and they don't exist in isolation. So they will have to communicate a lot with each other. And so if you're not careful about how communication between microservices has been set up and microservices are requesting for information from each other, it leads to something called as the big ball of mud. And I was going to write something here but it doesn't matter. So all you need to know is this is called as the big ball of mud, okay? And this is going to lead us into the inter-service communication, and I'll talk about that in a while. But before that, we'll just cover a few more things. So this was one challenge, the big ball of mud communication, and we'll solve that because we have a complete section just around discussing that. But before that, I want to talk about the second challenge, which is called as latency due to data sharing between microservices. So like, let's say this is your front end, this is your back end, this is your database. So everything is fine here because this is this is a monolith, right? But the number of calls increase after a while, plus the amount of interactions between microservices lead to more calls, because let's say if there are 2 microservices or 3 microservices and they all have to call each other, and it's just an exponential number of increase in the number of calls that are happening between the microservices. And this increases the calls exponentially, right? Exactly what I've just said, as compared to monolith. So this leads to increased latency. Just one second. Okay, so let me move myself out. I just happen to see myself in the window, so I just moved myself out again. All right, so this is your front end, and this is your API gateway, and these are your microservices, and each microservice is calling the database. Okay, so microservice 1 calls the database, microservice 2 calls the database, microservice 3 calls the database, microservice 4 calls the database. But all of these microservices have to interact with each other, as you can see here. They're all interacting with each other. The front end is lucky enough to be using API gateway, because with the Hello API gateway, we are being able to call the different microservices. All right. Now there's something called as the service discovery at runtime, which is microservice 1 usually communicates with other microservices during runtime to access information based on other user actions. Since the latest deployment last night, the IP address of microservice 3 has changed, and microservice 1 is trying to hit microservice 3 but not able to get back a response, as the team managing microservice 1 wasn't informed about the update. So you can read this on screen right now. Let me take it here, but I'm going to explain it to you, right? You can keep reading it if you want, but I'll just explain this to you, what's happening here. So what happens is you have these 4 different microservices, okay, and they all are interacting with each other. But the microservice number 3, right, the deployment for this was changed last night, okay? And when you change the deployment, that means the IP address has changed, the port number has changed, all the information has changed. And now the microservice 1 knows where microservice 2 is, it knows where microservice 4 is, but these 3 microservices now, because the IP address of this microservice has changed, they don't know where microservice 3 is, like what's the IP address and what's the port number. So this is a big issue, right? And this might sound like a stupid mistake, but you'll be surprised at how common this is. This happens all the time, where the DevOps people, with deployments, basically this is very common. This happens all the time. and you end up messing up the IP addresses and port numbers. And so it might sound like a stupid mistake, but it's very, very common. So this is something that's solved with the help of service registry, which we will talk about later in the course. So there are these challenges. The first challenge that we talked about was the big ball of mud communication, which we'll discuss how to solve it. Then we discussed about latency due to data sharing between microservices. Actually, this is something that, again, I'll show you how to fix with the help of something called as event-driven architecture. And then I just showed you how an API gateway is used, because all of these microservices, the front end had to otherwise call all of these microservices on its own. Now the API gateway does it for the front end. But again, the number of calls between microservices has gone up, so we'll figure out how to fix that. And then we have this service discovery at runtime issue, which again is a problem, but this again can be fixed with the help of service registries, right? So we'll talk about API gateways, service registries. We'll talk about event-driven architecture to reduce latency, and we'll talk about how we can get rid of the big ball of mud of communication, okay, with the help of sync and async communication. Anyways, now I talked about API gateway, but I didn't give you a lot of details, right? So that's what I want to give you in the next section here, which is the scaling client problem. So let's talk about it properly, what happens and exactly where API gateway comes in, how it helps us. So let's look at this diagram first, okay? This diagram, where you have the front end, and the front end is calling all these microservices, the clients, users, and projects. And then you have the external APIs, which are also calling the projects microservice only. Because let's say, you're using Zapier, and then you have connected your projects to your Slack, so that every new project, whenever a new project starts, you get all the details into your Slack. And similarly, if a project ends, you get all the details into your Slack. So you're interacting with external APIs for just the project's microservice, but everything else is being queried by the front end. Now the front end has to make requests. Let me zoom this in. The front end has to make requests to multiple microservices to get the data it needs. Okay, that makes sense to you, I think, because we used to have let me show you another diagram which will make it very clear. So you would have just one backend when you had a monolith, but now, because you have microservices, you will have almost like multiple backends, right? Multiple different places where you want to get the information from to show in the front end, because a front end has, let's say, has a component which is showing the orders. Now for the orders, you need information about the products, the user for which this order is. So you have to get all this information from multiple microservices. So the front end has to make requests to multiple microservices to get the data it needs. And at the same time, there could be other clients like the external APIs making requests. So we just talked about how this could be connected to Zapier, and via Zapier could be connected to Slack. So there could be external APIs making requests to the microservices as well. And they would also have to integrate with each microservice. So both the external APIs and the front end, they will have to integrate with all of the microservices instead of just one backend that used to exist when we had a monolith architecture. So this creates a big issue. The complexity at the client side becomes exponentially high and slows down the client because of excessive logic written to be able to access data effectively. So imagine you had your front end earlier, and with the component, because you had to load one component with some data, you had from the front end, you just had to call one backend and you would get all of your data from that. But now you're having to access APIs from different microservices, and this means that and you're not very sure on how the data format looks like from each microservice. That means you're having to process the data also at the front end side after making those requests and calls, and then aggregating the data, organizing it properly, displaying it in the front end. That just means that the complexity at the client side becomes exponentially high. It puts a lot of load on the front end, makes it really slow. And so because you have to write excessive logic to be able to access data effectively. So that is called as the scaling client problem, okay? Let me take a quick sip. Sorry, I have to keep speaking for hours, so I'm just sitting with a huge bottle of water. And then you have more clients, okay? So the scaling client problem says that with the same clients, when you have to interact with multiple microservices, that's problem number one. But what if the number of clients themselves have to scale, right? So the client is scaling in terms of complexity in the first instance here, and the number of microservices it is talking to. In the second instance, it's scaling in the number of front ends themselves. So we have now a web front end, we have a mobile app front end, we have a wearable watch, we have industrial IoT, or for example, if you're building a project management software, you have attendance machines, which are basically IoT devices connected to the project management software. And then you have other third-party apps that we discussed, like Slack, Discord, Telegram, all of that stuff, okay? So all of these things are connected now to our project management software. And at some point of time in the lifecycle of the software, the number of clients would need to increase, right? And that's what's happening now, because now we have that IoT device, we have the mobile app, we have the web app, we have the watch interface. And this can lead to even more issues because each client is having to access information from each microservice. And the number of connections and API calls increase exponentially. And this leads to increased latency. And increased latency is something as engineers that we must fight. We want the software to work as fast as possible so that customers can or users can get information as fast as possible, and that doesn't lead to a break in the customer or the user experience. Now, if you are not very sure about latency and all the other words that I'm using, availability, reliability, resilience, all of these words, these are like real system design concepts. These are not just English words. These are like technical concepts in system design. There is a system design series that I have, but I'm not sure if I've taught all of this there, but don't worry, I will come up with a huge system design video, and like let's say a 10-hour system design video, something like that, and it'll cover all the concepts. If you want to see that, if you want me to cover all of that, and because I'm assuming there's a lot of system design content on the market, on the platform, on YouTube already, but in case you feel like you're not very clear with system design, do let me know in the comments and I'll make that video. Increased latency is something we must fight, otherwise the customer experience gets really bad really quickly. Okay, so just to quickly recap, we had our front end and we had our external APIs, and these had to talk to multiple microservices now because we are not following monolith architecture. And so the number of calls were increasing exponentially, and so was the complexity at the front end side was increasing exponentially. But now, because we have more clients, that just leads to increased latency because now all of these clients have to make all of these different requests to all the microservices. So what's the solution? The solution for the scaling client problem are the API gateways, which we just discussed here like a minute back. And I introduced API gateway, but I didn't tell you exactly why I'm introducing API gateway. And this comes from the scaling client problem because the API gateway makes things very simple. It just acts as a unified central interface between your front end, all the different front ends, and you can have even more number of clients, but they'll all make the request to the API gateway. And the API gateway will handle all the complexity because it's a backend running server application. So it will handle all the complexity of making calls to the different backends, different microservices, and getting all the data for you, and then assimilating it, and then getting it delivered to all your front ends. So this will handle all the complexity for us. So if the microservices need to increase in number and the clients also need to increase, let me make the text slightly bigger so you can see it. Yeah, if the microservices need to increase in number and the clients also need to increase, it's wise to have a central interface between the services and the clients, and the central interface is called the API gateway, which is responsible for interacting with the microservices. The clients don't have direct access to them. This is quite great. So what you might think, when you're starting out in your career, you might think that, oh, my front ends don't talk to my back ends directly anymore. Why is there this something in between called the API gateway? They don't have like direct connection. Shouldn't I have direct connection because that'll be like much faster? But that's the wrong way to think about things, because the clients, even if the clients don't have direct access to your microservices, it's actually quite great even from a security perspective, because security is enhanced because now you have to go through the API gateway where you can have rate limiting and you can have IP blacklisting, all of that stuff. A compromised client doesn't bring the backend down. So if just one of the clients become compromised, this one, let's say the mobile app is compromised, it can't take the entire backend down now, right? So because all the requests have to go through the API gateway. So you can have a lot of logic there. And the problem with a centrally available API gateway is just that it's centrally available. So now earlier you could, from the front end web app, you could talk to different multiple microservices now, but you always have to go through the API gateway. So as somebody who's starting out in architecture, you might think, oh, but if this is like a central API gateway, if this goes down, then doesn't that mean that I lose access to my entire backend, and doesn't that mean that availability of my software was much better earlier? You might be right for a short while, right? Because I've not introduced the next stage yet. But if the API gateway goes down, all clients are left hanging, right? This is what you would think because it's centrally available. Not only that, there's one more challenge, which is the web front end is usually more robust and can handle bigger JSON objects, whereas you might want to keep the mobile app super light and send very less data in the response. This is even more true for wearable devices. How do you reconcile this, right? So what I'm saying here is the first challenge is that API gateway is centrally available. And the second thing I'm saying, the second challenge is that the data that the API gateway is fetching from these microservices and sending to these clients, the data is great for the web front end because it can handle like very large JSON objects, and it can work with that kind of complexity and process that information, show it. And on the web, you definitely have more space. You want to show like so many more fields. But in the mobile app, you don't have a lot of space. You want to show very few fields. So would you keep sending all of those data points and all of those fields again to the mobile app, and then make the mobile app struggle and handle only the fields that it wants? So if you're using showing only 3-4 fields in the mobile app, would you still be getting those 30 fields from the backend? That's the question. And the other question is, if you have like, let's say, a wearable watch, you want to show just one field, would you still be getting the entire response, which will have those 30 fields, which was a great response for the web front end or a great response for third-party apps, but not a great response for the wearable watch? So these two problems, we have these two problems, right? One is the API gateway being centrally available, and if that goes down, the entire access to backend is lost. The second is the amount of data that we are sending in each JSON object, and how those responses are structured. So this is why the advanced solution is something called as backend for frontends, or the BFF pattern, which basically says that for each of your clients, each of your front-end clients, you want to have a separate API gateway for them, right? So it's not like that if this goes down, you lose access to the entire system, nothing like that. So mobile app has access to its own mobile app gateway, and this can have logic to process the information and then show less information. So what I'm showing here is that it's accessing gRPC or GraphQL APIs. The right way would be accessing GraphQL APIs, and then you have the wearable watch, which is accessing the GraphQL API. Third-party apps are accessing REST APIs, and the web front end is accessing REST API. So you have your microservices. The name of the microservice is clients, users, projects, and invoicing, because a project management system would have your clients, and the projects would belong to the clients would give you projects, and users will be the team members working on your project, and then invoicing would be invoices sent out when some milestones are hit in the project. So these are your microservices. These are you can have different technologies. So the big benefit of using these backends for front end pattern is that firstly you have a specific a different API gateway for a different client. That means that you can get specific data. So like, let's say if you want, if you can handle big JSON objects in the web and third-party apps, it's completely okay. You can do that. You can have, because you have different gateways. And if you need like smaller JSON objects, because you don't need all the fields that you have, you can use mobile app gateways, and they could call GraphQL APIs instead. And the other thing is you can you are protected from a lot of failure, and you have a lot of failure resilience, because even if one gateway goes down, all the other clients are working perfectly fine. They're getting information perfectly fine. So if your website is not working, but your mobile app could be working perfectly fine. And the third benefit is that you have way more flexibility. You can use REST APIs, you can use GraphQL, you can use gRPC. So you have like 3 really big benefits by using this advanced solution, which is backends for front ends, which is a BFF called the BFF pattern. Now this is one of the only patterns that I discuss here in this video, because for microservices there are like hundreds of patterns, right? I won't say 100, more like at least 30 patterns. And you have all these patterns, right? You have the ambassador pattern, asynchronous request apply, bulkhead, choreography, circuit breaker, CQRS. Maybe you know in some of these, event sourcing, index table, polyglot, persistence. I briefly touched upon this one some time back. You have the rate limiting retry. You have the saga pattern, right? You have all these patterns, sidecar, strangler fig, throttling, API composition. You have all of these patterns, and even for deployment, you have some different patterns. And I plan to cover this in a separate video altogether, because otherwise this, like the video that we are in right now, this will never end if I start covering all these patterns. And these actually come under microservices, but like specifically event-based architecture microservices. So I will create a dedicated video for this, and I will call it the event-based architecture. So if you're on my Discord, you can join in the discussion, and you can let me know what else you would like in that video. That is also going to be a very detailed, very long video, because I'm going to be talking a lot about all these different patterns, and some more details that I'll be covering in that video. All of these details like ETLs and monitoring, eventual consistency, distributed transactions, so many more advanced topics. Because otherwise this board will never end. And actually I'm feeling issues right now. I'm facing issues right now because Whimsical, the software that I'm using to create these diagrams, it's not able to handle boards of this size, and I'm already facing a lot of issues where my mouse stops working and I'm not able to drag things around. I'm not able to put more things there. I think I've reached the limit on the number of amount of diagrams it can take. So I just cannot like add more stuff to this board anymore. Anyway, so let's read through what I've written about this thing that we just discussed, which was the backends for frontends pattern. So it says, having separate gateways for separate clients adds a whole new dimension of scalability. And not only that, it brings with it flexibility and also added benefits in uptime. So uptime is what we want to enhance. We want to reduce the latency. We want to increase the resilience and reduce instances of failure, and enhance the uptime, which is basically our availability. And then the second thing you get is flexibility, because now you can share GraphQL APIs with the watch and mobile. This keeps the client super light and can even and the clients can even interact with using gRPC with the backend, which is pretty awesome. Or you can have the microservices talking via gRPC, whatever. Like, doesn't matter how you set things up. You get a lot of flexibility. So benefits is high uptime. If one gateway goes down, other clients can still keep functioning. High flexibility, you can use gRPC, GraphQL REST, whatever you want, wherever, all of that in the same architecture. You have high scalability because the number of microservices and clients can both increase without impacting the speed. And low latency, because front-end clients complexity reduces significantly now, because your front ends don't have to do a lot of the work. The API gateways, which are specific to each of these clients, are doing most of the work which was supposed to be done on the front-end clients. And so front-end clients complexity reduces significantly along with the number of connections. So earlier you had to have connections between every single client with every single microservice, and all the clients had to do all the work to get all the data. And now each client is just talking to the specific API gateway that's meant for that client. So thereby it leads to lower latency. So you have all of these benefits. So why wouldn't you use this kind of a pattern, right? Obviously you'd use that kind of pattern. But this was the advanced solution, right? So the solution was API gateways. Then I showed you an advanced solution, which is backend for front end. And the only reason why I've shown you 3 different solutions for this same problem, which is the scaling client problem. And I've shown you 3 different solutions, which is the expert level solution. And then there's one more solution, which is the over-engineered solution, which is something you shouldn't do, but you would see this in production in many companies. But anyways, we'll talk about that in a while. So the reason I show you multiple solutions is because to solve any problem that you might have with engineering architecture, you can go with different approaches. You can go with, depending on the resources you have, depending on the team size you have, and depending on how much budget you have, you can either go for a very basic solution, which is just using API gateways. So if I had like a team of 5 engineers, this is what I would do. I would go for backends for front-end pattern. If I had a team of like more than 25-30 engineers, this is what I would be doing. And then expert level solution is a distributed API gateway. I would do this if I had a lot of users, like maybe more than 100,000 users. This is something that I would think about, and I had like really good revenue. Most importantly, then I would do something like this. So how does this work? Let's see how this works. So let's look at the expert level solution. And this solution has is called the distributed API gateways. So what that means is that we're going to have multiple gateways for each client. So earlier we had one API gateway for each client, but then we thought that maybe even if one, that API goes down, that client won't have access to data anymore. But here we're solving that. We're saying that even if a particular gateway goes down, there are others to handle the request. This is a pattern that's commonly used in products that have a good number of users. Okay, and what that means is that earlier you had one gateway for web front end, another gateway for the mobile front end, you had one for the variable, one for the third-party apps. And now you're going to have multiple gateways for each front end. So for example, I've shown 2 here, there could be 3. So even if just one goes down, you have 2 more to handle the request for the web front end. And similarly for the mobile app front end, you have multiple API gateways for that, for variable. Now that means that these API gateways need to be like really light, and that can be managed, not a problem. These can be optimized. At least these ones will be really optimized. This one would still be handling a lot more data than these ones. But yeah, this is a very, very common pattern for products that have a good number of users. So you have multiple API gateways. So it's called the distributed API gateways pattern. And this is like an expert level solution. Nobody's expecting you to do this if you have like a small team and a few number of users only. And then you have the over-engineered solution, which is load-balanced distributed API gateways. And believe it or not, I've seen this in production in a client's product, a client who was, an enterprise company, not a Fortune 1000 company, but an enterprise company, and they were following this kind of a pattern. So what was happening was they had these multiple front ends, but all the requests were going to the load balancer, and the load balancer was deciding which API gateway to send the request to, and there were like multiple API gateways. And from those, the API gateway's job was to determine which request from which client should go to which gateway. So there are like all these multiple gateways for the web app, the mobile app, the variable gateway, and the third-party gateway, like we had earlier. But in this case, there are 2 more gateways, which are, even if one gateway goes down, there's still one more. And this gateway's job is to just route the request to the right gateway. All of that being handled with the load balancer in the beginning. So this is an over-engineered solution, because you don't need this level of you don't need this level of preparation to handle a lot of traffic. I think this is very over-engineered, and then obviously from the API gateways you're sending the traffic to the right microservice. Yeah, so like I said, it's over-engineered, but people are using this. I wouldn't recommend using this unless you have like, even if you have like a lot of users, still I don't think it's that level of control is required. All right, so now this is the billion-dollar problem. So earlier we looked at the million-dollar problem, the decomposition. Now we're looking at, then we talked about the ball of mud, which leads us to solving the ball of mud, which is the inter-service communication. Now this is a billion-dollar problem. I call it the billion-dollar problem because just to solve this problem, there have been billion-dollar companies built. So if you've heard about Apache Kafka, you've heard about Redis, you've heard about RabbitMQ, all of these companies are solving this problem, and they're all billion-dollar companies. Confluent, at least, is a billion-dollar company that uses Kafka, okay, which is around Kafka. I'm sure you know about Confluent. Okay, so the inter-service communication is a huge problem, and a lot of companies solving it. But let's try to understand what this is, because if you understand this really well at a fundamental level, then you'll understand how to set up your microservices and how to set up the communication, because communication between microservices is everything. That's how you're going to get access to data. That's how the services are going to get access to the data from another microservice. The front end is going to get access to the data from the microservices. All of that is set around this, because we have to think about availability, low latency, all of those amazing things. Okay. So before I start talking about that, I want to take you through these 6 steps, which is the general life cycle of a system. So monolith systems with some microservices, or not a pure monolith, this is what it looks like. So things usually start off as synchronous systems with HTTP, but HTTP requests start having lags and delays. So you know that we have these HTTP requests, but they start having lags and delays. So in traditional systems, client makes a HTTP request to a server and then gets a response back. But we can have something called as streaming systems, which make it easy for everyone to be in sync without specifically making a request. Now, I do mention this line, but I talk about streaming much later on, because to be able to discuss streaming, we have to go into something called as event-driven architecture, and then we'll talk about events and message queues and streams and all of that. So I'm using this line lightly here, but trust me, I will explain everything to you in much more detail. But yeah, the solution to that big ball of mud is this is like one legit solution, which is streaming systems make it easy for everyone to be in sync without specifically making requests. So systems tend to become more and more event-driven. Now this word also I use lightly, but I talk about, like, there's a whole section that I've dedicated just for that, so we'll be covering that in this video. So systems become more event-driven with time as traffic and data increases and number of requests start burgeoning, which is basically they start increasing exponentially. So for a while, architects also try partially being request-driven and partially being event-driven. So there are you can have you can be hybrid. You can have request-driven architecture, you can have parts like event-driven architecture, and you can have a mixed match between them. And I've also shown you this is what it looks like. This is what it looks like, having a stream and then having these request-driven architecture. Now this won't make any sense to you right now, and that's completely all right. But when I've explained to you all the other topics, which is where we'll talk about synchronous versus asynchronous communication, we'll talk about that in a while. And when you come back to this after a few days, once you've understood that, then it'll make a lot of sense to you. But what I'm trying to say here is that you can have hybrid architectures where you have partially request-driven and partially event-driven. And we'll discuss this in this video in a lot more detail in just a few minutes. So don't worry about trying to understand this word or trying to understand this. But if you already know about these three things, like streaming systems, event-driven, and hybrid systems, which have synchronous as well as asynchronous communication together, that's really good. But if you don't know them, please don't worry, please don't take a lot of stress, because I am covering everything in this video anyways. So so you can have these hybrid systems, but eventually the best way is to have everything completely event-driven. But we'll talk about that again as well. So microservices, when teams grow and the product matures and the traffic increases, these are independent events, but mostly happen at the same time. And this calls for a new way of dealing with this challenge, right? So we have a lot of events. Event is a word that, again, you might not understand right now, but we'll talk about just events and event-driven architecture in some time. And what I'm basically saying here is when teams are growing, your product is maturing, and your traffic is increasing, you will have a lot of events being developed in the architecture at the same time. And you'll have to find a way of dealing with this challenge. And there are different technologies that are great for different services. So you may want to build services heavy with competition Go. So we saw that, right? We saw that some time back where we said that, okay, you could have some microservices with Golang, some with Python, right? So you can have, I've mentioned here, scraping services in Python, competitions in Go, and general services in Node.js. You might also get few engineers of a technology that you'd want to keep your system language agnostic. For such evolved systems where there's loose coupling and high separation of concern, you'd want to consider microservices, and that's exactly what we're doing. So for such evolved systems, when there's loose coupling and high, again, I think it's been repeated. Sorry. So architecting REST API-based microservices or synchronous microservices is easy, straightforward, and at a small scale, the right thing to start, and at a small scale, everything looks perfectly fine. So what am I saying here? What I'm saying here, let me show you the diagram. So if you have a microservice which is, or maybe do I already have a diagram like that here? Oh yeah, I have it here. Okay. So maybe I have this project management software, and it has these three microservices, which is teams, it has tasks, and it has projects, right? So one project consists of multiple tasks. That's how project management works. And each project, there are teams, there's a particular team that's working on a project, okay? That's how project management works, right? Again. So all of these microservices are having to make requests to each other and getting some response. So they're making requests, getting response. So this is a request response kind of a format. This is called as synchronous, because you ask for some information, you get it back after some time. That's synchronous. Now the problem is this doesn't scale well, and it leads to what we've already seen, the ball of mud communications. And that's exactly what we're saying here, which is architecting REST API based microservices or synchronous microservices. It's easy because that's how you start out, right? You know how to make requests and how to get back responses. And it's straightforward, and at a small scale, it's the right thing to do, but and at a small scale, everything works perfectly fine also. But soon there will be challenges with synchronous microservices. All microservices exclusively own their own data. So if one service wishes to access data held by another, it must do so by using an API call, right? So what we're saying here is that each microservice, this is at a small scale because there are just 3 microservices, and let's say the number of users are also very less. So and the amount of data that each of these microservices holds is also very less. So there will be very few number of calls between these microservices. But and this is perfectly fine. This kind of communication is perfectly fine when it's at a very small scale. But when you start scaling up, there are many challenges, and especially because all of these microservices own their own data exclusively, and they have to get access to the data from other microservices with the help of API calls. So when numerous services access the same piece of data, things get very tricky. So to complicate matters further, you may have microservices that utilize heterogeneous databases, i.e. multiple types of databases like SQL, NoSQL, time series. Now we've already seen this when I touched upon polyglot persistence in like a very short, we talked about in like very small details. So maintaining data integrity can be an issue when the requests don't scale from APIs. And instead of API calls, we want the systems to being driven by events, where events are streamed between the microservices and they pick up events that are important to them while ignoring the others. Based on the events, there could be triggers to take specific action. So this line, number 8, it talks a lot about event-driven architecture. Even though this diagram doesn't show that, but I've shown this diagram because this is the difference between a monolith architecture and microservices, and we're just showing here how microservices are interacting with each other, and each microservice is having its own database. But what I've not shown is the event-driven architecture, which I'll basically show you here what starts happening. So when you have a lot of when you have microservices and you want to start scaling up the inter-service communication between them, you can't just keep relying on request-response-driven systems. The first solution you can do, the first stage that you enter into is called the caching stage, where you want to reduce the number of requests between the microservices. So you start using cache. So let's say you're using a Redis cache here. So you don't have to always hit the microservice, that means, and you can use caching so that latency isn't compromised. Instead of calling the microservice, getting some data back, you can just hit the cache, and cache already has that information, and it's an in-memory database. So accessing that information is much faster. So the latency doesn't get compromised, and cache can be updated at a later time. This also means that the load on the microservices doesn't increase a lot. They don't have to do a lot of processing, and that means they can handle a lot more requests at the same time. And that just means that scaling becomes much easier. Latency doesn't get reduced because of just using this cache. Okay, now the next thing is, redundant data storage. So what does that mean? That means that you don't have to always hit the microservice. You can, by mistake I mentioned the same thing again. Okay, so here what we said is we can maintain details of tasks and projects so that we don't have to access these repeatedly. Even though some data will be redundant, it at least reduces the number of requests. Okay, so we started with just making requests to each microservices. Then we started introducing caching so that we don't have to make requests to the microservice directly. We can get the data from the cache, at least in some of the instances. The next stage is using redundant data storage. That means even if you have some data in one of the microservices, you can still store that in another microservice. So let's, for example, your projects has all of this information. Now you have project name here, but because in the teams, and the tasks, the task has a name. You can have start date, end date, status. You have all these details in the task and projects. But the team has an ID, and you can have the project ID also. But you can also store the task name and the project name in the team's database itself, so that you don't have to always keep taking the ID of the team and then going to the projects and getting the data of the project and the task, task details. So you can just maintain the name of the task and the project in the team. So we can maintain details of the task and project so that we don't have to access these repeatedly, even though some data will be redundant. Like this will be redundant because the task name already exists in the tasks database. You don't have to maintain the name of the task here. And similarly, the project exists, the project name exists in the project's database, and you don't have to maintain the name of the project here in the team's microservice. But still, you do that because it reduces the number of requests, and you don't have to end up getting that repeatedly. Now, this is what I was talking about, streaming between services. So this is the 8th point that we were talking about, that instead of API calls, we want the systems to be driven by events. And events can be streamed between microservices. So like I said, we'll talk about event-driven architecture in just like the in the next section. But for now, all you need to know is that we can have something called as streams. We can stream data between these microservices. So instead of making synchronous requests, like asking for some data and getting back that data, you can just start streaming the information unidirectionally or bidirectionally between these microservices. So you can start streaming information between the microservices. This suddenly makes our architecture asynchronous, because we're not asking for some information, whatever is happening, whatever event is taking place. Like let's say somebody just logged in, or somebody just purchased something, somebody just added something to cart. All of these become events, and they start going across the microservices, and the microservices can start consuming these events. And with the help of this, we can start sharing large amounts of information. But here, many things can go wrong if we are not careful. So let's see why that is being said. Because here what we're doing is we're streaming between the microservices, but there's no unified central platform we're using to stream between, or an interface that we're using to stream between the microservices. So that's why we can use something called as an interface, which is this line here, this thick line here. What we're saying that this is an interface that can be used to stream between different microservices. And what I'm saying here is that using an interface like Kafka or RabbitMQ, which is a queue, we can send events. Now, this type of a format is called as a publisher-subscriber model, where each service can publish some events, and all microservices can subscribe to the type of events they want to listen to. So we will understand this in more detail shortly. This is the most important part. So if you don't know how this works, how Kafka works, or how RabbitMQ works, how queues work, how events work, how streams work, not a problem. We're just covering that in the next section. So the other thing I want to talk about is that you can also stream data between the front end and back end. So not only are you streaming information between your microservices, you can also stream information between your front end and back end servers, because you don't have to rely on synchronous communication. So you don't have to just stream events between microservices. We can also stream events between the front end and the back end for faster updating of the front end, which reduces the number of API calls to the back end. Also, it's easy to set this up using sockets. So if you've used sockets before, web sockets, it's very easy to set up communication with the front end and the back end. Okay, so this was our microservices, inter-service communication, beginning of our inter-service communication. But the real magic happens here with the help of event-driven architecture. So in the event-driven architecture section now, which is we're going through right now, we're going to be talking about events. We're going to be talking about how different type of events look like, talking about how to design events. We're talking about how message queues work and their benefits, their features, their use cases, right, and their components and their benefits, all of that. Is benefits twice? No. Yeah, sorry, this is the benefits of pub/sub, and this is the benefit of queues. So yeah, two different things. And then we have the event stream, everything about event streams. So let's dig into that, and then event load problem, and then queues versus streams. So a lot of stuff to be covered, and then I have this special section for takeaway on what do you basically want to take away from event-driven architecture. So let's get started with this. Let's learn about event-driven architecture, because this is very, very important for microservices. Now, whenever you build microservices, you wouldn't like in 2024, let's say if you're building microservices, you wouldn't want to stay with synchronous communication for very long, right? Even the projects that I'm showing you, I'll probably be showing you Kafka, I'll be showing you RabbitMQ, and all of that is event-driven, all of that is asynchronous communication. So we'll be leveraging a lot of all this. So let's get into it. So event-driven basically mean that there will be some events that will be taking place in the architecture, in the software. And one of the microservice, let's say it's called the authentication microservice, and a user logs in. So when a user logs in, this event will now be emitted by this microservice, the authentication microservice, and that event will traverse through the system, and some other microservice can pick up that event, and it can do something, like it can do something in response to that event. So for example, if somebody has logged in, and then the cart microservice has to emit all the things that are there in their cart. You want to send that to them. So So we'll say that this person has logged in, and these are all the products in the cart. Actually, this wasn't a great example. A better example would be, let's say somebody has just purchased something. So user A purchased 5 products, and the order number is this. Now this big event with the user ID, with the list of the products and the order ID, and the price amount, the amount of money they paid for buying all these products. This big event will traverse across the microservices, and then the invoice generation microservice will pick up this event, and it can use all the data that is there in this event to generate an invoice. And then once the invoice is generated, then the emailing microservice can get triggered with the data of the invoice, and it can create an invoice template, like a PDF template, and it can send it to the user. So all of this can happen in an event-driven way, rather than having a cron system which checks if an order has been placed, then process this order. All of that, you don't have to do all of that. Okay, that can be done. It's called batch processing. We'll talk about that also, but right now I was just giving you an example of event-driven architecture. So what is an event? So before you talk about event-driven architecture, I'll just also have some water. So I just want to tell you that this is like really detailed stuff, and concepts like this is very difficult to find, because it takes weeks to make content like this in a board, because it's very easy to show you code, right? Because I can build on the spot, and I can make changes on the spot. I can improvise on the spot. But this I have to plan like completely in the beginning, and I have to like create these boards, and I have to also research a lot, think about how to teach you guys. Everything should connect, right? So this just takes a lot of time to build. So that and it also takes a lot of time to and energy to show you in a video, because you have to be constantly talking. So yeah. Anyways, so before you talk about sorry, I just want to tell you that so I hope you appreciate that you're getting a lot of information, a lot of conceptual information that probably won't exist on the internet. So this is like a great resource. That's what I want this to be, a great resource that you can always come back to. So you have event-driven architecture, but what's at the center of event-driven architecture are events. That's what is at the center. So events, an event can be anything that has happened within the scope of the business communication structure. So for example, receiving an invoice, booking a meeting room, placing an order, or making a payment. All of these are legit events that can be emitted onto the stream. Okay, and events are data. They're not just signals. So like you have to send some data in that event. So like I told you, when a user makes an order, places an order in an e-commerce platform, all the data, like for example the order ID and the products that he would purchase, and his user ID and probably his username, all of that will be required by the invoicing microservice. So that's why you'll have to send all of that data in the event. So event is not just signal, hey, this happened. That's not an event. Event is like, this happened, but all of these are the details for the thing that happened. So instead of sending an event that simply signals order placed, right, which basically adds no value to our architecture, the event could include order details such as the order ID, the customer ID, the items that he ordered, the quantity, and the timestamp. This allows downstream services. So downstream service is any service that's going to consume these events and make something happen, or process this event to trigger some kind of a response or some kind of an activity. For example, like the example I gave you, which was when an order is placed, then the inventory microservice that has to reduce the inventory, shipping has to get in action, and billing has to directly use the data within the event, and the invoicing, which has to generate the invoice, and the emailing service, which has to send the invoice in a particular format, in like let's say the PDF format. So rather than needing to fetch additional details from other sources, right? So now this line, it's very light, but it's also very important, right? So I have to highlight this line somehow. So what this is saying is that when I'm sending an event, now this is an art, right? Designing an event is an art, because it needs to have enough information so that my microservices are not struggling for more information. If I didn't send the items, then even though I've sent the order ID, customer ID, quantity, and timestamp, or maybe not the quantity also, I've not sent the items and the quantity. Now my microservices are struggling for information, and then this means that somehow it has to get access to that more information, and that just leads to more time being spent, more communication being done, and more and increase of latency. So that's why designing events, you have to be very, very careful. It's an art, because it has to have the complete information that's required. So that's why I've written rather than needing to fetch additional details from other sources. Okay. And I'm sure you will read this and you'll ignore it and you'll forget it for now. And then when you're actually building microservices and you're designing events, you'll face these problems like throughout the life cycle of an event-driven program project. You'll face this problem so much that, hey, I should have put this information in the event, or maybe you end up adding even more information in the event. And it has taken me years and years to get this right, and I can't stress on how important this is. Then you are also saying that an event is also a single source of truth. So that means a payment processed event with details such as transaction ID, order ID, amount, and status can act as a source of truth for payment status. That means that payment has been made, that is being told through that event, and that is the single source of truth. So any service that needs payment confirmation or history, e.g. customer support analytics, can rely on these events instead of querying multiple services or database to verify payment status. So this becomes really serious, right? When you're sending a payment processed information event, so that just makes it very serious, because you're saying that you don't have to rely on other things like querying multiple services or database, because usually you would want to query a database to get information about whether a payment has actually been processed or not. What we're saying here is we're tipping that on its head. We're saying that even if just a event is sent out with all these details, that can act as a source of truth for the payment status, and that's completely all right, and the services can rely on this information. So to make this information reliable, you also have to put in a lot of thinking. And the final points about events is the consumers of the events. So each event, when the event is emitted by a service, there is another service that will consume that event, and that's called as a consumer, so event consumer. So consumers encapsulate their own business logic. So that means as consumers of events should handle the specific business logic relevant to them. They interpret events according to their needs, allowing each service to stay decoupled and independently function without relying on other services or process to modify the events. So let's take an example. In a retail system, a product added to cart. So this is an event. So like, let's say, when I say a retail system, I mean an e-commerce software. So product is added to cart. This will be a event which may be consumed by multiple services. So why is an event consumed by services? Because they want to do something from that event. They want to trigger some kind of a process based on that event. So for example, the example I gave you about invoices being generated based on somebody purchasing something, that is the invoice microservice consuming the event for the purchase happening. And in this case, in this particular example, we are taking the example of a product added to cart event. And when a product is added to cart, there are multiple services that need to take some action based on that event. So the first action will be taken by the inventory service. So it decreases available stock based on the item quantity. And the second pricing service checks for promotions or discounts on the product that has been added to the cart right now, if we can give some discount or promotion. And then third is the recommendation service. So based on the product that was added to the cart, is there some other related product that we can suggest to the user? So each of these services encapsulates its own logic, right? So they have, all of these services have their own logic to be able to respond to this event in their own particular way. And they react to the same event. Event is the same, product added to cart, but they are reacting to it in very different ways. So this reacts in a different way, this reacts in a different way altogether. So without requiring knowledge of how others handle it. So this microservice doesn't need knowledge of how inventory service is handling it. This service doesn't require knowledge of how pricing service is handling it. This modularity enhances scalability and resilience. So this is also an important point about events. So now that we understand what events are, we understand that events are data and not just signals, and they have these kind of fields, and this data that is in the event can be used by multiple services, can be consumed, the event can be consumed, and different services can take different actions. So now that we know that, now that we have clarity on what an event is, the event can take multiple forms, right? So we can have something called as an unkeyed event, so where the key has the event has some value, like the timestamp, ISB, and all of those, but the key does not exist. So unkeyed events are used to describe an event as a singular statement of fact An example could be an event indicating that a customer interacted with the product, such as a user opening a book entity on a digital book platform. So that could be an event. The second type of event, which is the more common type of event, are keyed events. So these kind of events have keys along with the value. A keyed event contains a key but does not represent an entity. Keyed events are usually used for partitioning the stream of events to guarantee data locality within a single partition of an event stream. So this is a keyed event. And then you have something called as an entity event, unkeyed. Okay, so I think I've said entity event, but I've by mistake I've mentioned the name for the same text for the unkeyed event. So just to ensure the board is accurate and updated, I've just updated this text here. So an entity event is in event-driven architectures is a message triggered by a change in a specific entity. So for example, if an order or a user profile or product is changed in the system, this event is triggered. It represents a state change. So anytime when a state is changed for any of these entities, then you get an entity event like order placed or user updated, which other services can listen to or react to, enabling loosely coupled interactions across the system. So this is, so now we know that we know what are events, and we know the three types of events that usually exist. And now the important thing that I was saying, which is designing events. Now you can't create events randomly. You have to think about how do you go about it, because designing events is an art. If you don't pay attention to this and do a shoddy job, this affects your system's scalability, reliability, all of those things. And also it leads to increased latency. So you have to be very, very careful about designing events. And I just talked about that like a few minutes back when we were discussing events, why it's important to design, to pay a lot of attention to when you're designing events. So what do you need to think about when designing events? Now this is an important topic, so I'm going to go a bit slow because you need to pay a lot of attention here. So you need to have singular event definition per stream. So suppose you're building an e-commerce application with multiple microservices, including the order service, the payment service, and the shipping service. We are assuming 3 different microservices, which are multiple microservices in an e-commerce application. Each service needs to respond to certain events generated by other services. That makes sense, right? Because the order service needs to respond to some events, payment service responds to some other events, shipping service needs to respond to some other events, and it's possible that all of these are responding to some common events, but in different ways also. Now, if you have a single order events stream, so we're now considering how many streams do you have. So for each, like events, they go in streams, right? So we create streams for these events to traverse. And so if you have a single order event stream that contains different event types like order created, order updated, order canceled, and order shipped, all of these events are mixed into the same stream. A consumer, such as the shipping service, needs to listen to order events and filter out the order shipped events while ignoring the others. This setup increases processing time and makes the logic more error prone. Now, what's happening here is that we have a single stream, okay, and the stream is called the order events stream, which will have all the events related to orders. And there are going to be different events being created in that stream, like the order created, order updated, order cancelled. These are like 3 very common types of events that are around orders, and even order shipped. And all of these events are mixed into the same stream. But there will be services, a downstream service like a consumer service, which is going to take some action based on this event. And we are assuming right now a consumer such as the shipping service. So this shipping service consumer or microservice needs to take some action based on the order events. So it's listening to order events, but it doesn't care about order created, order updated, and order cancelled. It only cares about order shipped. That's all it cares about. So it's listening to all the order events, filtering out only the order shipped events while it has to ignore all the others. While this is a great approach, but this setup increasing process time because the shipping service is having to do a lot of work, and it has the logic becomes more error prone. So in this case, every time shipping service receives an event, it must check the event type field to determine if it's an order shipped event or not. This extra filtering logic can lead to issues if the new event types are added, and it's easy to miss an event by mistake, right? So this is a huge challenge. This is what you need to think about when you're designing events, that you need to have singular event definition per stream. You can't be having different types of order events going across in the stream. Let's look at another example. So what you can do instead is you can define a separate stream for each event type. So for example, order created events will be a separate stream, order updated events will be a separate stream, and order shipped events will be a separate stream, and each event stream can only have one type of event. Now, shipping service subscribes directly to the order shipped event stream, receiving only relevant orders. That makes sense, right? Because earlier our shipping service was having to just listen to order events and then filter out only order shipped and having to ignore all the other ones. But now, since we have separate streams for all of these different types of events, like created events are different. Here we only had order events, like all types of events. Here we have order created events, order updated events, and order shipped events. So we have different types of events now, different types of streams for each types of events. So each event stream has only one type of event now, and shipping service that was having a lot of problem earlier because it was having to do a lot of processing, now just has to subscribe directly to only the order shipped events. That's it, not to the any other events. So only to this stream we'll subscribe to that, and we'll receive only relevant events. So here the shipping service no longer needs to filter events by event type, reducing the risk of processing irrelevant data and simplifying event handling. So this structure also makes it easier to scale the system, as each event stream has a dedicated purpose and new consumers can subscribe only the specific streams they need. Okay, so I hope that makes sense. Now our shipping service won't have to subscribe to all the events. It only has to subscribe to one particular stream, which is going to have events of a particular kind. So that means it saves us all the time for processing those events, and that means we reduce the risk of processing irrelevant data by mistake and simplifying. We have now simplified the event handling, and we now no longer need to filter events by event type, which we were having to do earlier. Okay, so this is one such factor, and the benefits. Now the benefits of having singular event definition per stream is that we have reduced consumer complexity. So each consumer only receives relevant events and doesn't need to check event type fields. We've already established that. And we have improved data integrity, so fewer chances of processing irrelevant events or encountering unexpected data. And now code maintenance becomes easier because we can change to one event type that are isolated and doesn't affect other events in the same stream. And also we get an added benefit of scalability, because with separate streams, adding new event types or consumers becomes easier. So if we have more types of events, like let's say we were talking about order created, updated, cancelled, order shipped, and there's one more event which I'm not because we've already covered CRUD, so I don't know. Maybe let's say it's order read, maybe order or order completed. Even after order shipped, there would be order completed. So there's that new event. Now it's very easy for us to add this new type of event because we can create a new stream, and it's possible to scale each stream independently. So it's just about adding a new stream. And now simply just like we followed through with this stage, and now we understand why designing events can be challenging, because and how to think about designing events. So one way is to think of singular event definition per stream. Similarly, we'll cover all of these points as well quickly, because designing events is an important topic. Now we do have a few more points to discuss about designing events, but before we do that, just wanted to show you what an event-driven architecture looks like. So because we're discussing event-driven architecture and we're going step by step, we looked at events, we looked at what type of different events are there. Now we're looking at how to design events, but what will the architecture look like? So basically you'll have producers of events, like for example your website, your mobile app, your point of sales, and new order, question about stock, return. All of these events are getting here to an event router, and then these events are going to the right consumer. So for example, the warehouse management database is getting the return, new order, and question about stock events, and the finance system is getting about the events about the return and the new order. So basically we're deciding where to send the right event to using an event router. So this is what a sample event-driven architecture looks like, found on the AWS blog. Now in our case, we won't be using this kind of an architecture. We'll be using a different approach, but I just want to show you what it looks like. I've left the link of the article here. You can check it out in more detail. But the one that we'll be following is more it will be just a little bit more robust, the kind of architectures that I'll be showing you. But before that, we have to go through all these details. Like, for example, how do you design events in the first place? So now the next point I want to discuss with you is using the narrowest data type. So for example, instead of using a general data type like string, use int for numbers or boolean for true false values when possible. So what happens is, whenever we are designing events, we just tend to use something like string, and then that kind of acts as a catch-all. So it doesn't matter if it's a number or a boolean, we start using string for all of these to cover all the use cases. But but a good approach is to use narrow data types for, like, for example, int for numbers and boolean for true false values, because narrow data types also improve clarity for consumers. If there's a consumer waiting for some kind of an event or some kind of data, it's great for them to know that this is a number, this is a boolean, and not everything is a string. So they'll expect, or they'll understand what kind of data to expect, and this just makes the system more efficient. So that's why I've mentioned use the narrowest data type possible. And then you have keep events single purpose. Now, when you look at all these different points, for example, the first one that we covered, which is singular event definition per stream, and using the narrowest data type, and now keep events single purpose. What you notice is that they're all talking about efficiency, right? At the core of all of this is efficient, like how to ensure an efficient system so that you design these events and your system doesn't get overburdened, right? And it stays efficient. That's the heart of all of this. So keeping events single purpose sounds a lot like singular event definition per stream, right? But this is to do with stream, whereas this is something else. This is about the event itself. So let's see how this works. So suppose the best part here is that I've explained all of these topics with the help of actual examples. I've not just given you definitions, because then that doesn't resonate with you, right? So all of these are with particular examples, and it took me a lot of time to make these examples, think about these examples, so that it's easier for you to follow along. Now suppose that there is a microservice called the order service, and it embeds an event called order event, and this particular event includes information about the order status and inventory adjustments in just one message. So then there are these other microservices like the inventory service, which is like a downstream service consuming this event and listening to this event to adjust stock levels. So that is going to listen to this event from this particular microservice that originated from this particular microservice. It's going to listen to this event to adjust its stock levels of the inventory. And the notification service, which is listening to send an order confirmation email based on this event. Okay, so this event combines two distinct purposes. Okay, informing about the order status and adjusting inventory. So this means that notification service has to ignore the inventory adjustment data, while inventory service has to ignore the order status data. I hope that makes sense. Let me draw a diagram to show you what is being said here. So here is your order service, and it's emitting this event. I don't, maybe message is the right, yeah. So it's originating this event which has a lot of data. And because there are two microservices listening for this event, the first microservice is the inventory service, and the second one is the notification service. So what's being said is that the inventory service is supposed to take some action from this event, based on this event, and the notification service is supposed to take some other action. So the inventory service is supposed to take adjustment about stock levels. So I'll mention here adjustment of, and this is supposed to send a confirmation mail. Okay. So you're supposed to do these two different things. Now what that means is that this information that is being sent, the event which is being sent, is the same event being sent to both of them. It's going to have information for adjustment of stocks, and it's going to have information for which will help the service send a confirmation email. And what that means is that when this service gets this event, it has to ignore all the details or all the data that was meant for this microservice, which has data related to adjustment of stock levels. Whereas when this event goes here for the inventory service, it has to ignore all the information that was supposed to be for the notification service, which was supposed to help notification service send a confirmation email, right? So this is what exactly is being said here, which is, this means the notification service has to ignore the inventory adjustment data, whereas the inventory service has to ignore the order status data, leading to unnecessary complexity and potential confusion, right? So if you don't handle these events well in these services, and because these events have a lot more data than necessary, which is not meant specifically for this microservice, it can lead to a lot of confusion down the line. Let's say somebody new joins in your team and they don't know how to handle this data or why this particular event is being emitted. It might lead to issues and confusion later on. But right now itself, without there being a new member in the team, right now itself there is a lot of unnecessary complexity which can be completely avoided. So here is a solution. So now not only I have created these examples for you, examples for you, but I've also created solutions on how those examples can be fixed. So here I have these solutions, which is that instead the order service, the order microservice, can emit two separate single purpose events. So one event would be order processed event and the other would be inventory adjusted event. So instead of sending the same event, which was the order event for both of these microservices, now instead we have a order processed event and inventory adjusted event. So here we'll have inventory adjusted, and we have order processed. So we have two separate types of events now. So the order process event, this event only contains information related to the order status and items. It's intended for notification service. Okay. So the order process is intended for the notification service because it has only the information about the order status and items. Whereas the inventory adjusted event, this event is solely focused on inventory changes and is meant for the inventory microservice to adjust stock levels. Okay. So this is meant only for the inventory service because this has data about the adjustment for stock levels. So now what happens is that each event, because now instead of one event, which was the order event, now we have two different types of events, which just makes the system again a little more efficient. So I'll remove this from here because I just drew this to explain the concept to you, and I don't want this diagram to get overly complex. But I just want to explain to you with a small diagram. But I hope now this makes sense to you what this means, keep events single purpose. And now I hope you also understand what each of these points are trying to say, that make the event as specific as possible, and this should ensure a high efficiency in the entire system and less confusion and removing unnecessary complexity. That's the whole idea. The next one is minimizing the size of the events. Okay. Again, we are still following the same approach or the same philosophy of reducing complexity and reducing size, increasing efficiency. So here we're saying that to minimize the size of the events, let's say you have a purchase completed event in an e-commerce application. Instead of including detailed product descriptions, images, and user device data, you only send essential details like order ID, user ID, and a list of product IDs with their quantities. This way, the event stays lightweight, improving speed and efficiency across the system. Okay. So what this is trying to say is that if you have an event about a purchase that's completed in your system, you don't have to send unnecessary stuff. You don't have to send details about product descriptions. Like that's a lot of data. You don't have to send images. That's again a lot of, that's like, maybe 200 MB images or 500 MB images. You don't want to send that. And even the user device about, what device was used to book this or to make this purchase. You don't want to send all that. You only need to send essential details. Like for example, the order ID, the user ID, because this is the data that will be used to process. So downstream services or the microservices that are consuming these events to take some action based on these events need to have only access to this kind of information so that they're able to take those actions. And all you can do is you can send a list of product IDs with their quantities, right? So an order, whenever an order is placed, you just need this information: order ID, user ID, and a list of product IDs with their quantities. So this way the event stays extremely lightweight. You improve your speed and efficiency across the system. Now the next point, which is considering consumers in event design. This point and this point, minimizing size of events, it's quite similar. It's going to be very similar, but they're not completely the same. They're similar, but they're not the same, okay? And the confusion here would be that to minimize the size of events, you would reduce the number of fields in that event. But it's not only that, it's much more than that, right? To make an event lightweight is not just reducing the number of fields, but there's a lot more things you can do. Here, what we're saying is that you want to consider, when you're making an event, when you're designing an event, you want to think about the consumers as well, as in who's going to consume that event. And here also you talk about optimizing that event, but from the perspective of a consumer. So for example, if multiple services rely on an order shipped event to update order status or notify customers, right? This is the exact same example that we had like just 2 points back, which was about the notification service and the inventory update service, where we were having that event to update order status and notifying customers. But here what we're saying is make sure that this event includes only the relevant data they need. Like for example, both of those microservices probably just need order ID and shipping date. That's all they need. And what we have to ensure is we should have to ensure that we avoid overloading the event with unnecessary details. Because if there are multiple services relying on an event, we need to avoid overloading the event with unnecessary details. And this ensures it's easy for consumers to process and avoid confusion. Okay. So this is quite similar in the sense it's both talking about how to optimize the event with as few fields as possible, but this is talking about it from a consumer perspective, the consumer of the event's perspective. This is talking about how to reduce the size of the event in general. And the next one is avoiding events as semaphores and signals, where event is data. And this is actually the exact same point as here, which we discussed, which was events are data, not signals. So it's the exact same point that I've mentioned here, which is avoiding events as semaphores and signals, because event is actually data. So I've given an example here and described it in more detail, which is an event inventory updated, an inventory updated event should carry information about what items were updated. It shouldn't just be a signal like inventory check complete. Shouldn't just be a signal. It should actually have what all items were updated as part of the event itself. So we have to treat events as data, because then you avoid dependencies on specific workflows and make sure your system is more robust and adaptable to different consumer needs. Okay, exact same point as before. But now, so this is, we're getting started with event-driven architecture, but now you know quite a bit. You know about events, you know about how different types of events look like, you know how to design events. And you know that designing events is an art, okay? So I'm not sure if you appreciate how important this information is, but whenever in your life, in the future, whenever you work with event-driven systems in the future, like asynchronous microservices, or you're designing, event streaming led communication between the services. Now you have like a complete solid base understanding of how to go about it, right? You have a great understanding of how to go about things now. So the next thing, now we know about events, we know a lot about events, but how do you deliver those events? Now there are multiple ways to deliver those events. One is obviously message queue, then the other are the streams. That's why we have been saying message streaming, event streaming. And this is the most common way to do it. But you don't always have to pick up streams, because if your system isn't big enough, queues are just the way to go. And there are use cases for queues and use cases for streams, even though I use streams a lot, but queues are like equally widely used in the industry. And they're like a really good way forward if you have the use case for it. Now let's go through message queues completely. Then let's go through event streams completely, so you understand the differences, and then we'll compare both of them, and then you see what's right for you, and then we'll go to the next topics. So what is a message queue? Message queue is a lightweight buffer which temporarily stores messages. Okay, this is what it looks like. Temporarily stores messages, and it ensures that consumers can read off from those messages. Now there are these producers that create those events. So we talked about microservices which will create an event. Like for example, the order microservice will create an event that, hey, an order has been placed. And there are other microservices like the inventory microservice or the notification microservice or the invoice generation microservice, which will read off from these events. And those downstream services which pick up these events, read these events, they are called as consumers. And the microservice like the order microservice, where the order is generated, is called as the producer. Producers are writing these events on the queue. Consumers are just reading the events from the queue. That's all the message queue is. It's just a data structure or just a technology to help us read messages or interact, like produce and consume messages. That's about it. Produce and consume events. Events is the right word for it. So the queue is a lightweight buffer which temporarily stores messages. So that's it. If you want, the definition is just this, which temporarily stores messages. That's it. And it also has endpoints that allow software components to connect to the queue in order to send and receive messages, right? So this is exactly what's happening here. Not only can it store messages, but it also provides these two connectors. The first block and last block are these two connectors, which help the other software components to connect to it and then either publish messages or read those messages. That's all the queue does. The messages are usually small. So whenever you, let's say you open up any industry article on queues or streams, they talk about messages. They don't necessarily say events, right? But it is understood that these are events because you'll be sending events. Could be any message, but mostly it'll be an event because we are learning event-driven architecture. So the messages or the events are usually small and can be things like request, replies, error messages, or just plain information. In our case, those will be events. To send a message, a component called a producer adds a message to the queue. The message is stored on the queue until another component called the consumer retrieves the message and does something with it. And many producers and consumers can actually use the queue, but each message is processed only once by a single consumer. Okay, so that's what's happening here. Many producers and consumers can use, as you can see, the message queue, but each message is processed only once by a single consumer. Okay, and all of these points, right? The message is stored on the queue until another. The message is stored on the queue until another component, which is the consumer, picks up that message. So it's just defining that same diagram that I just showed you. So all these points are defining that diagram. And for this reason, the messaging pattern is often called as one-to-one or point-to-point communication because the messages is processed only once by a single consumer. Now, when a message needs to be processed by more than one consumer, message queues can be combined with pub-sub messaging in a fan-out design pattern. So what is pub-sub messaging? It's a completely different topic, right? Pub-sub messaging, where you have like multiple publishers, multiple subscribers, and they're able to process events multiple times. But we'll talk about that in just a minute. We'll talk about pub-sub because pub-sub is somewhere between queues and event streaming, so somewhere between that. And pub-sub is a very, very widely used topic, and there are like billion-dollar companies built just from this pattern called the pub-sub pattern. Okay, but let's first discuss queues in detail. So you have, this is what a queue looks like: producer producing event, going to the queue, storing these messages, and the consumer consuming the events. So what are the benefits of using queues? So there are two things I want to cover about queues. The one is the benefits, and the other are this, which is the features of the message queue. So first, let's talk about the benefits. Then let's talk about the the features, and then everything else that you see here on the screen. Everything else here that you see, the 4 components, benefits, use cases. That's all related to our pub-sub because pub-sub and queues are very closely linked, and it's just like a much better version of queues, like a more complex variation of queues. But let's first talk about queues a little bit more in detail. So queue. The benefit of using queues is better performance. So queues enable asynchronous communication, which means that the endpoints that are producing and consuming messages interact with the queue and not with each other. Okay, so what we're saying here is that these endpoints which are producing the messages, in our case, these are the producers, And the endpoints which are consuming the messages, in our case, we are calling them the consumers, they are not interacting with each other directly, right? So we've already seen before with microservices patterns that I was showing you that when they talk to each other directly, it just leads to more complications. So we need like an interface, right? So if you remember, let me actually take you back there so that you remember that we want to be using interfaces to be able to communicate between microservices. We don't want microservices directly communicating with each other because it just leads to a lot of connections and it starts becoming a pain. So that is the whole point. That's what we're trying to save here, do here. So you have this, which is they interact with the queue, not with each other. Producers can add requests to the queue without waiting for them to be processed. So they can just fire and forget, right? They can just add request on the queue, forget about it, and consumers can process these messages when they're available. So it becomes asynchronous. So what is the difference between synchronous and asynchronous? Synchronous is that when you are on a video call with somebody, they're there with you, right? Their time is also open, your time is also open, and you are facing each other, and then you're talking, and then you ask them a message, you get a reply back. That's very synchronous, right? Request and response. Whereas asynchronous is when you send them a message on Telegram or on WhatsApp, and then whenever they're available, they reply back to you. So you're not dependent, or you're not waiting for their message back, right? You know that whenever they will be available, they will message you back. So that's a very asynchronous way, and that is what we are building. So we are building asynchronous microservices or event-driven architectures where everything is getting triggered with events, and no microservice is actually waiting for a response back. Okay, because if you're waiting for a response back, that means your connection is open for that time. Just is not a very efficient way of building systems. So consumers can process the messages only when they're available. So no component in the system is ever stalled waiting for another, which optimizes the data flow. And this is exactly what we want. And with the help of queues, you get something called as increased reliability, where you make your data persistent and reduce the errors that happen when different parts of your systems go offline. Okay, so data is persistent. Why is data persistent? Because the data is getting stored onto the message queue. Data is getting stored on the message queue. So even if one of the producers go offline or the consumer goes offline, and when they come back, they can again access the information that's on the queue because the information is persisted there, it's stored there, right? But if they were talking to each other, then if the consumer goes offline, it's a big problem, right? So by separating different components with message queues, you create more fault tolerance. So if one part of the system is ever unreachable, the other can still continue to interact with the queue. The queue itself can also be mirrored for even more availability. What does the mirroring of the queue mean? That you can have more instances of the queue. So we have shown only one queue here, but imagine there could be like multiple queues here. And with that, you're basically mirroring the queue so that you have even more queues. So even if one goes down, you can have multiple. And that just increases the availability of the platform as a whole. Then you have granular scalability. So we make it possible to scale precisely where you need to. So when workloads peak, multiple instances of your application can all add requests to the queue without risk of collision. As your queues get longer with these incoming requests, you can distribute the workload across a fleet of consumers. Producers, consumers, and queue itself can all grow and shrink on demand. Okay. So now here, when you look at the diagram, you see that one producer is like really big, two are really small. And there's only one consumer, but there could be multiple consumers, and some could be big, some could be small. Right, so that's basically showing that you can scale up producers or scale up the number of producers, scale up the number of consumers as well, depending on the amount of workload. So that's what you get a lot of scalability, but also flexibility with scalability, and that's called as granular scalability in the sense which is selective scalability, right? Which is what happens with Docker. The first thing that we covered about microservices was one of the first things was that with Docker we can scale up and scale down as many number of microservices instances we need for each microservice. And then you have something called as simplified decoupling. So we can remove dependencies between components and significantly simplify the coding of decoupled applications. Software components aren't weighed down with communications code and can instead be designed to perform a discrete business function. So this is the exact definition of how we've defined microservices, that software components can be divided into different like into different units, and they can all work independently of each other. That's how we have defined microservices in the beginning. So to transport events between the microservices so that they're reliable to communicate easily, we can use queues. So what are they? And we've already discussed what they are and their benefits. Now let's talk about the features of messages or of queues, message queues, or how they work, right? So the thing is, all of these are like really deep topics. Push and pull delivery, schedule or delay delivery, at least once delivery. These are like really huge topics. What I've done is I've only kept only very light details about these. If you want, you can search about them. You can read more about them. But this is what I've covered. I've covered like from a very like a 10,000 feet perspective about these topics. Because you don't have to know these. If you don't want to know these, you can still start using queues, but I'm just covering these features so that you know more. But if you want to deep dive into these, you'll have to search them out on Google. So let's look at the different features for message queues. The first one is the push or pull delivery. Now, by features, we basically mean that this is how queues work. And we're just going through each of these points, which basically show us that queues can work in these different ways. So the first way is push or pull delivery, and what that means is pull basically means continuously querying the queue. And if you work with API polling, or if you've polled any APIs, that basically means that you keep calling the API and keep checking if the information has changed or not. So that's basically the pull approach, which is you continuously keep querying the queue for any new messages. And push means that a consumer is notified when a message is available. So when it's pull, you're checking the queue for new messages, but push, basically you tell the consumer that, hey, new message is available, please check it out. But this push is also called pub sub pattern, which we're going to take a look at in some time, as you know. Then it's schedule or delay delivery. So many message queues support setting a specific delivery time for a message. So you can set that, hey, at this time, this message needs to go. It doesn't have to, this event or message doesn't have to go right now. It can go after some time. So if you need to have a common delay for all messages, you can set up a delay queue. Then you have at least once delivery, where message queues may store multiple copies of messages for redundancy and high availability. So earlier we were talking about how the consumers can go down, the producers can go down, and even the message queues can go down. So message queues, you can have mirroring there. So even if one goes down, there are others there. Producers, whenever, or consumers, whenever they come back after they've gone down, whenever they come back, they can read messages off from, the consumers can read messages off from the message queue. But what happens if the messages are deleted from the queue itself, or how do you prevent that from happening? So you plan for it by having multiple copies of the messages. And even though there's redundancy, but it basically leads to high availability, even because you store multiple messages, so that will lead to redundancy, but you'll have still high availability. And you can resend these messages in the event of communication failures or errors to ensure they're delivered at least once. So this is what queues focus on, at least once delivery. They make sure, with the help of, by storing multiple copies of the messages, they make sure that the messages are delivered at least once. So that's at least once delivery. And then, or you could have exactly once delivery as well, where duplicates can't be tolerated. So you use FIFO message queues will make sure that each message is delivered exactly once by filtering out duplicates automatically, right? So you can have, so you can set the queue to be to do at least once delivery, or you can do it exactly once delivery, depending on how much consistency you want in the platform. So like, let's say if you're working with banking systems and you have debits and credits, or that kind of financial information, that you would want to have exactly once delivery, where you don't want it to be more than once, or you can't afford failure. But if it's like, let's say something to do with product added to cart, you can get around with at least once delivery, to make sure the products are added to cart. But with orders, you can't do at least once delivery with orders, because you can't afford to have multiple orders of the same thing generated multiple times in the system, right? So just selecting which approach you go with can make a lot of difference to how your system responds, and it has to be done based on what kind of use case you have. And then you have queues which are first in, first out, where In these queues, the oldest or the first entry, sometimes called the head of the queue, is processed first. So these messages, the ones at the beginning, are processed first, and the ones at the end are processed at the end, and not in a random order. So those are the first in, first out queues. Then you have dead letter queues, where which is a queue to which other queues can send messages that can't be processed successfully. So let's say if there are some messages from this message queue that are not being are random, or they have some issue and they're not being able to they're not getting processed properly. So we can send all those messages which have not been processed properly to another queue called the dead letter queue. And this makes it easy to set them aside for further inspection without blocking the queue processing or spending CPU cycles on a message that might never be consumed successfully, right? So there could be an error, some issue. You don't want to keep trying to process it again and again and consuming resources, and you don't want to block the queue processing or spending CPU cycles. So it's better to keep it on a separate queue. Then you have the ordering. So how do you want to order those messages? So most message queues provide best effort ordering, which ensures that messages are generally delivered in the same order as they're sent, and the message is delivered at least once. Okay, so here, whatever order they've been sent in, most of the message queues, they try to process those in the same order, and they ensure that the message is delivered at least once. And then you have poison pill messages. So these are special messages that can be received but not processed. They are a mechanism used in order to signal a consumer to end its work, so it's no longer waiting for new inputs. It's similar to closing a socket in a client-server model. So think of it more like a graceful shutdown, where we're telling a consumer that, hey, now you can stop your work because it is no longer we're no longer waiting for new inputs. So it's similar to closing a socket in a client-server model. It's like a very graceful shutdown kind of a process, right? So this is what are the different features of message queues. So this leads us directly into the pub sub, right? So that we were discussing earlier. Now this is what pub sub looks like, which we have seen. We have these topics, we have publishers and subscribers. So now let's get a little bit into it. This is what pub sub is. So publish subscribe messaging, or pub sub messaging, is an asynchronous communication model that makes it easy for developers to build highly functional and architecturally complex applications in the cloud. Okay, so at a 10,000 feet perspective, all this is doing is it's making it easy for developers to build highly functional asynchronous communication, which even Q is doing that, but it's just PubSub just takes things a little bit to little forward. So PubSub messages provides instant notifications for these distributed systems, and supports scalable and reliable communication between independent software modules. So these are all independent different software modules, the subscribers and publishers. These are all of our different microservices. And PubSub basically helps in supporting reliable communication and scalable communication between these independent software modules. What are the use cases of PubSub? The use cases are that you can perform parallel asynchronous processing. It doesn't have to be in bold, so I don't know what this is in bold. I'm not able to change it anyways, no problem. So you can perform parallel asynchronous processing. Okay, so all these events that are being generated here on our queue, we'll be able to perform we'll be able to process them parallelly, and then we'll be able to deliver application and system alerts. Okay, that works with queue as well. We'll be able to manage asynchronous workflows. So the whole point is managing asynchronous workflows when it comes to asynchronous communication like PubSub or queues or event streams. And then you're able to balance workloads. You're able to log to multiple systems. You use fan out for replication, and you coordinate serverless applications. So these are the use cases. So if you want to do all of these, then PubSub is the right approach for you. Now, these are the 4 key components of PubSub. So let's take a look at that. So you have messages or events, basically. Anything that you're sending on to the PubSub is an event or a message. So a message is communication data sent from sender to receiver. Message data types can be anything from strings to complex objects representing text, video, sensor data, audio, or other digital content. So those are the messages, right? It can be anything. And every message has a topic associated with it. So the topic acts like an intermediate channel between senders and receivers. It maintains a list of receivers who are interested in messages about that topic. So if you look at this diagram more carefully, you see that this is a table. This is actually a table and this table has two different topics going on. So depending on which subscribers are interested in which topic, so maybe subscriber 1 is interested in topic number 1, subscriber 3 is interested in topic number 3. So publisher 1 is publishing to, let's say, topic number 2, subscriber 3 is reading from topic number 2, and that's how communication can go on between topics. So I'll repeat it again. The topic acts like a channel between senders and receivers. It maintains a list of receivers who are interested in messages about the topic. Receivers basically are the consumers. A subscriber, so we have these subscribers and then we have these publishers. That's why it's called as pub sub, or producers and consumers. It's the exact same concept. You can call it producer, you can call it publisher, or you can call it consumer, you can call it subscriber. The subscriber is the message recipient or the consumer. Subscribers have to register or subscribe to our topics of interest. They can perform different functions to do something different with the message in parallel. Okay, and publishers is the component that sends these messages. So these publishers, they're producing these messages, and subscribers are consuming these messages, and it creates these messages about a topic and sends them once only to all subscribers of that topic. This interaction between the publisher and subscribers is a one-to-many relationship. The publisher doesn't need to know who is using the information it's broadcasting, and the subscriber don't need to know where the messages come from. Okay, so what this last sentence means, which is a very important, the last two sentences, which is like really important. What this means is that there is no direct communication between the publishers and the subscribers, right? So that's what we have been trying to decouple from the first, from the beginning, which is that we don't want our microservices to be able to interact with each other too much, because that just leads to a lot of load on the system. That's why we have these interfaces between them. And what we're saying here is that the subscribers don't really care where the messages are coming from. They're just subscribing to the events. So that's why it's event-driven architecture. Similarly, the publishers don't care about who is consuming their events. They don't have to have the knowledge of that. They're just publishing the event onto the queue or the stream, and that's it. They're done. Okay, so these are the key components. So now we can talk about the features of PubSub, and then we'll talk about the benefits. Okay, so in the features of PubSub, you have you always have push delivery. So basically, we mean that PubSub messaging instantly pushes asynchronous event notifications when messages are published to the message topic. And this is the most important part, where the subscribers don't have to worry about getting the messages from the queue again and again. The subscribers are actually notified when a message is available. So that's called as push delivery. And then you can have multiple delivery protocols in PubSub. So topics can connect to multiple types of endpoints, such as message queues, serverless functions, HTTP servers, and email addresses. So so these topics, the things that are listening to these topics can not only just be other message queues. You can have other message queues there for the endpoints. You can also have serverless functions getting triggered. You can also have HTTP servers getting triggered. You can also have email addresses there. And fan out. So this scenario happens when a message is sent to a topic and then replicated and pushed to multiple endpoints. Fan out provides asynchronous event notifications, which in turn allow for parallel processing. Okay. And then filtering. The filtering feature empowers the subscriber to create a message filtering policy, so they'll only get the notification they're interested in. So remember earlier with queues, we had to think about how to filter those events, and then there'll be a lot of problem, because if you had these subscribers, they would have to then filter all those events, and they would, because they're only interested in some particular events and not all. So PubSub technologies, they do provide filtering where the subscribers, they don't have to receive every single message. They can only receive messages that are meant for them. And then you have multiplexing. In some cases, publishers can also be subscribers. So here it says in some cases, but when we learn about streams, which is the next topic, you'll learn that all microservices are publishers as well as subscribers. Like they can publish event and they can subscribe to events. But here, in some cases, publishers can also be subscribers. You can multiplex message streams and create systems that link together in an internally consistent manner. Okay, so you have multiplexing, filtering, fan out, and then you have multiple delivery protocols, and then you have push delivery. So these are the PubSub features, which may or may not be important, but what's really important are the benefits. Like how do, why would you use the PubSub pattern? So you remember that in queues, you have either the pull method or the push method. Push, when you use push, that's basically PubSub. And with push, you don't have to poll the queue. The subscribers don't have to check the queue for new messages. They are notified whenever there are new messages, right? So that basically eliminates polling. So polling is when the subscriber is checking again and again, asking the queue whether there are any new messages for me. So message topics allow instantaneous push-based delivery, eliminating the need for message consumers to periodically check or poll for new information and updates. So this promotes faster response time and reduces the delivery latency that can be particularly problematic in systems where delays cannot be tolerated. Okay. Then you have dynamic targeting. Okay, so I hope eliminate polling is clear. With dynamic targeting, what we are saying here is that there is something called as a topic in PubSub, right? And because of that topic, you don't have to, the publishers don't have to worry about the like which consumers are going to pick up which events. So the discovery of services becomes easier, more natural, and less error prone. So you don't have to maintain a roster of peers, and an application can send messages. The publisher will just post the messages to a topic, and then the subscribers who want the topics can just tune into a topic and get all the messages or all the events relevant for that topic. And this makes it easier for multiple subscribers to change, upgrade, or disappear, and the system can adjust dynamically. So that's called as dynamic targeting. Then you can this is quite self-explanatory, which is you can decouple the services and scale them independently. So PubSub makes the software more flexible because publishers and subscribers are decoupled and they work independently from each other, which allows us to develop and scale them independently. So each of these publishers and subscribers, they are all independent. We can scale them, remove them, scale them up or down completely independently. So they're all decoupled. And you can decide to handle orders one way this month and the another way the following month. And adding or changing functionality won't send ripple effects across the system because PubSub allows you to flexibly change how everything works together. So and the other thing is we can simplify communication. So the publish-subscribe model reduces complexity by removing all the point-to-point connections with a single connection to a message topic. The topic will manage subscription to decide what messages should be delivered to which endpoints. Fewer callbacks result in looser coupling plus code that is easier to maintain and extend. So what you're saying is with the help of topics, because you have these topics, the publishers, they are only responsible for publishing to a particular topic, and then subscribers can pick up from a topic. This just makes it easier to code things. It just simplifies communication, and the topics then ensure the subscriptions and decide which messages to be delivered to which endpoints. This leads to fewer callbacks, looser coupling, and code that is easier to maintain and extend. Then you have the durability. So because PubSub messaging provides very high durability, and you have at least once delivery with PubSub. So you can be sure that your messages will be delivered at least once, because you're storing copies of the same message on multiple servers. Then you have security, so message topics authenticate applications that try to publish content, and that allows you to use encrypted endpoints to secure messages in transit over the network. So what you're saying is that you can't just create a publisher, or you can't just have a publisher that comes to the platform or our system and just starts publishing new events. You can't do that. The publisher will get authenticated, and that means you can have your own kind of encryptions in place, and this makes it more secure. So we have covered the message queues. We have covered the queues, the features of the queues, and we have covered the benefits of queues. And then we looked at PubSub. We looked at what is PubSub, looked at the use cases of PubSub features. We looked at the 4 key components of PubSub, which is messages, topics, subscribers, and publishers. And we looked at the benefits of PubSub. So by now we have covered quite a lot of stuff. We have covered a lot about events and designing events and PubSub and queues. But now, because we have all of this knowledge and we are kind of warmed up, we can go into the actual topic because it's event-driven architecture, and we would like to use event streams because that's just a much better way to manage our events. So we're going to talk about the key components. We're going to talk about how it works, the features, the kind of message delivery options that we have, right? We have the delivery models. Again, we have the push versus pull and the connection initiation, all of that. And we have all these advantages. So we'll look at all of that. And then there is something called as the event bloat problem that I want to take you through. Then we'll just compare queues versus streams. So that's the agenda for the next few minutes. So let's get started with streams. Now streams are all about the continuous delivery of events. So you have the event source, could be microservices, publishers, basically, and you have the event stream, and you have the applications that are reading all of those events. But the events are being streamed continuously. So they're unbounded, sequential, real-time flow of events is what's happening on the stream. And events can undergo different processes in a stream. So you can have, not only are these events on the stream being transmitted or being carried from the publisher to the subscribers, but they can also undergo different processes. Okay, so this is a very, very important part and very important reason why I use streams and why streams are the industry standard for processing or for working with events. And we have the next entire section is about events getting processed, okay? And that's a huge, like a very important topic. For now, I'm just like introducing you to event streams. So that's why I've just mentioned that you can process events in an event stream. Like for example, and I've even given you examples. So one example is aggregations. Aggregations is like, I'm not sure if you've worked with MongoDB, but aggregation is like aggregating data from multiple different databases or multiple different tables and creating like data that you need, almost like joins in SQL. So that's aggregation. So you can perform data calculations like means, sum, standard deviation, which are all types of aggregations. Or you can have ingestion. Ingestion is basically adding data, streaming data to databases. So that's ingestion. I'm sure you've heard these words before. Maybe you've seen them on Twitter or LinkedIn or YouTube. Somewhere you've seen these words where people talk about ingestion, which is somehow being able to stream a lot of data to databases, because storing data to databases is not straightforward when it comes to like a lot of scale. When you scale up systems and you're using these microservices and you're using event-driven architecture, so you would then have to stream data to databases. That's the whole idea. Now there are some key components that streams have. So the first, there are these four things, and if you've worked with Kafka, Apache Kafka before, you've probably seen these four things. You probably know what these are. Even if you don't know about these four things, I'm going to take you through them. So brokers are the servers that run event streaming platforms. So message brokers enable applications, systems, and services to communicate with each other and exchange information by converting messages between formal messaging protocols. Now there is a video that I have on Golang and Apache Kafka. If you want more understanding of how brokers work, of how topics work, how partitions work, and how offsets work, you can check that out. But in the very near future, I have a new video coming up, like I told you about, which is this. It has all of this information, along with all the information about how Kafka and RabbitMQ work from the inside, like deep. As you can see here, this is the agenda for the next video, which is deep dive into Kafka topics, concepts, and RabbitMQ concepts. I'm not doing that right now in this video, because otherwise this video will never end. And as you can see, it's already quite a long video. And if I make the video any longer, people will drop off, and people won't make it till the end. So I'm just covering these four concepts, and I'm just touching upon them like in little details. But then there's a complete 2-hour video that we can make on just these topics, on how Kafka actually works from the inside, okay, and all the various concepts around Kafka. But I'll do that. Like I said, in the next video. It could be the next video, it could be the next video, but that video will come up, which is all about event-driven concepts and patterns and all of that stuff. So brokers, again, enable applications, systems, and services to communicate with each other and exchange information by converting messages between formal messaging protocols. So this allows interdependent services to talk with another directly, even if they are written in different languages or implemented by different platforms. So that's brokers. Then you have topics. Topics is something we've already talked about just some time back, which is they are categorizations. Like, if you're sending out events onto a stream or onto the message queue, you have the topics or categories of different types of events. So the consumers can listen to a particular topic, and they can subscribe to multiple different topics based on what kind of events they need. They don't have to subscribe to all other type of topics. And this just makes the system much more efficient and just makes it more maintainable, scalable, and so on. So topics are categorizations or feed names. So we think of it as a feed or a channel, basically a topic, to which events are published, providing a way to organize and filter events within the platform. They act as a subject. So there are multiple names it can have. It can have the name of subject, name of topic, or the feed name is all the same thing. They act as a subject for events, allowing consumers to subscribe to topics and receive only relevant events. So when you are able to subscribe to only relevant events, that just makes the system much more scalable and more efficient. It's efficient, so that's why it's much more scalable. What are partitions? So topics can be further divided into partitions, allowing multiple consumers to read from a topic simultaneously without disrupting the order of each partition. Okay, so it's just a way to further divide topics and just make it easier to consume from the topics. Then you have offsets. Offset is a unique identifier for each event within a partition. So you have topics, and then inside topics you have partitions, and then for the events you have these unique identifiers called the offsets, which mark the position of an event within the sequence. Consumers use offsets to organize the events they've processed. So for instance, if a consumer disconnects from an event and later reconnects, it can resume processing from the last known offset. So almost like you have IDs and key IDs in databases, so almost like that, because you would want to keep a track of which event was processed previously, and a consumer disconnects. So this might sound weird to you, but this happens all the time. So when there are consumers in the system, when they're consuming events, they might go offline, and a failure might happen. But what's important is how we handle that failure, and when the consumer eventually does come back online, what happens is it reconnects, and then it can resume processing from the last known offset. When you say offset, it just means the last ID that was processed, for the last event ID that was processed, so the next event starts getting processed. So these are the 4 topics. Like I said, I have covered a little bit more detail about these in the Golang Kafka video, because that was more specific towards Kafka. But in the next video also we'll talk. We'll do a really good deep dive into how all of this works, right? So right now I just want to cover a little bit in detail that these are the key components of streams, because right now in this video our priority is to understand what streams are, what they do with the data, how are they different from queues, why are they a great way to handle events. That's what we're focusing on, and not the exact implementation of how you would go about microservices and how to set up those streams. We're not doing that in this video. Okay. Anyway, so now we've talked about what streams are. We've taken a look at a stream diagram. We have seen the 4 core key components. Now let's see how it works. It works. These are the 6 different things that are happening. So you have generation of the event, publishing of the event, storage of the event, consumption of the event, delivery of the event, and processing of the event. These are the 6 things that can happen in a stream. So the first thing is event generation. This is when producers send events to the event streaming platform. So when an event is generated, like for example, an order has been placed. So this is the order microservice, and a user places an order in an e-commerce platform. So that's the order placed event. That's the one that we are generating. So the event is generated. So that's event generation. Event publishing. So using client libraries, producers publish the event to a specific topic within the platform at which point they become available for consumers. Now, when we publish this event to a specific topic in the stream or in the platform, that becomes order published. So that's the publishing of the event, and now it becomes available for consumers. So the event is available for consumers to consume. Then you have storage. So all of these events are stored on the stream up until the point the consumers will consume those events. So the platform stores the events for a predetermined period or until they're consumed. That's more important. This is how at least I do it. With brokers managing the event storage and retrieval processes. So the brokers, there will be brokers here. They will manage the event storage and retrieval processes. Then you have event consumption. So when an event is being read or consumed, that's the event consumption process. So consumers process event data to initiate other events. Depending on their purpose or configuration, they can act upon events immediately or as they arrive, storing them for later processing or compile them for batch processing. So they can do, when somebody's reading like a consumer or a downstream service, which is dependent on the event that's being sent, they can take multiple actions. They can perform another action based on this event. They can perform an action, or they can just store them for later processing so that they can be processed later, or they can compile them for batch processing. Now, batch processing is something that you don't know about yet, but we'll talk about that in just the very next section. Event delivery. So the event broker delivers events to all subscribed consumers. Delivery semantics can include at least once delivery. We have talked about this, right? That at least once the message will be delivered, where events are guaranteed to be delivered but may be duplicated. So they get duplicated. So that's why we are able to guarantee their delivery. Or exactly once delivery, where each event is delivered only and exactly once. This is for higher consistency if your system requires higher consistency, or any other type of semantic. So that's the delivery mechanism. Then you have processing. So once the initial event is consumed and delivered, event data is processed for several downstream actions, including transforming the data, aggregating it, and triggering complex workflow. So the data can be processed here. So let me put it here. So data is first consumed. So that's why I've shown you how it can, how this envelope is opened here, and you see this love icon there. I couldn't find a better icon here actually. It just shows that the event is consumed and it's opened, and now it's processed, and this processed event can be used for further downstream actions. So this, I just drew this very rough diagram just to show you how event is generated, published to a topic, stored, then consumed, opened, processed, and processed for later retrieval for other downstream processes. So this is how, in short, this is how everything works. This is how streaming works. So what are the features? So we have exactly once processing. We've talked about it, but let's talk about it again. Exactly once delivery semantics ensures that each event in a stream is processed exactly once, an essential feature for preventing duplicate and lost stream events. So most event streaming systems include mechanisms to provide exactly once semantics regardless of failures elsewhere in the system. So even if there are failures elsewhere in the system, most streaming services will have mechanisms for including exactly once semantics. And as you know, exactly once is to ensure extremely high consistency across the system. Like if you're working with banking related or payment related systems, you would need high consistency. And then you have back pressure. Back pressure is when downstream components, when we talk about downstream components, we're talking about microservices that are dependent on the events, and when they read those events and then they process those events and then use it to trigger some actions. When they're not able to keep up with the incoming event rate. So let's say a lot of events are being generated, like purchased happened, like that. Many suddenly, you know, there's some kind of a New Year's sale or a Christmas sale or a Diwali sale, and so many things are getting purchased on the platform, and so many events being generated, and downstream components won't be able to keep up with the incoming event rate. So back pressure prevents streams from overwhelming the system. So with back pressure, a data flow control mechanism. So back pressure is a data flow control mechanism, which basically means that you know, your microservices that are consuming the events, they don't get overwhelmed. So we've built a mechanism to prevent that. Consumers can signal producers to throttle. So if you've worked on web systems, if you built backends, you know what throttling already is. If you worked on the cloud, again, you would know what throttle is. So we will be able to throttle or stop data production when they're overwhelmed, so with data processing or unable to keep up with the incoming. It's just a way to ensure that the consumers don't get overwhelmed. Then you have consumer groups. Even consumers often work as part of a consumer group to accelerate event consumption. So because consumers can get overwhelmed with the number of events getting generated, so we have consumer groups and not just a consumer, so that we can accelerate the consumption of these events. Each consumer in a consumer group is assigned to a subset of partitions to process. Partition, as you know, is a part of topics, as a further subdivision of topics, and parallelizing consumption for greater efficiency. So we, as fast as we can consume those events in a parallel manner, we're able to achieve greater efficiency. Then we have watermarking. Event streaming often means processing data in a time-sensitive manner. So let's say an order has been placed. Now the next thing to happen is an invoice getting generated or an event notification email getting sent to the user that, hey, you have purchased this, right? So that's a time-sensitive thing. You can't send an email like 5 days later telling them, hey, you had purchased this on our platform. Till then, the user is in anxiety thinking, hey, when I sent them the payment, did they receive it? Did they get my order? When will I get my order? All of that is time sensitive. So event streaming often means processing data in a time sensitive manner. So watermarking enables progress tracking. So you can have a feature called watermarking, which is available as part of event streaming. So watermarking enables progress tracking by using event time in stream processing system. It enforces a completeness threshold that indicates when the system can consider data has been fully processed. So it's just basically ensuring or checking the progress that has the event been fully processed or not. And then you have something called as data retention and compaction. So most event streaming platforms offer customizable data retention policies that allow developers to control how long the events are available for consumption. Is it available until they have been consumed, or for a particular time, like let's say 1 hour, 5 hours, or many days, because you can't indefinitely have events onto the platform because that will just create a lot of load on the stream. So data compaction, however, is a process that removes redundant or obsolete data from topics. Now, just like garbage collection in programming languages, you need to have mechanisms that ensure the memory is freed up. You can't just always keep having events on the topics. So that's why you have a process called data compaction, which removes redundant or obsolete data. So you keep the storage footprint minimal while preserving essential data. So this also ensures efficiency of the entire system. So these are the features for streams. So now we have looked at the core components. We have looked at what streams are, how they work. With a small diagram, we saw that features. And now we have our message delivery options, our advantages, and our delivery models. So let's look at all of those. Now these are the 3 different message delivery options available to us, which are either all the subscribers. So you know that subscribers are subscribed to a topic as part of the entire event stream. They're not listening to all the events. They're only listening to events of a particular topic, right? That's what ensures the efficiency of the system. But here the first option is that all the subscribers to a topic will get all the events for the topic. So when all these subscribers are getting all the events. The second is that only one out of the topic subscribers, so there are multiple subscribers subscribing to a topic, only one of them will get an event. And the third one is that the subscribers will be grouped into groups, and all the groups and only one subscriber per group get an event. Okay. So let's talk about all 3 of these. So I think I should explain this to you with a diagram, because this is important. And yeah, let me actually do that. So this is the stream, and then you have these subscribers. So since we're not talking about consumers here, talking only about subscribers, this is the stream, these are the subscribers. So in the first one, there is, let's say this is the first topic number 1, and this is second topic number 2, and then you have topic number 3. And this is the first topic, right? Sorry. Oops. So you're subscribed to the first topic, and let's say even this service is also subscribed to the first topic. Now, both of these subscribers will get the particular access to this event. Even this will get access to that event, even this will get access to that event. So this is the first scenario. Okay. The second scenario is that, so without this it doesn't make any sense actually. Let me remove these 3. Bring it here. Okay. And now in this case, right, in this case, this should be layered on top. not working out. Let me just extend it anyways, like this. Okay, they're both listening to this topic. In the second case, where only one of the topic subscribers gets an event. So only one topic subscriber, which is the first one, gets the event. The second one does not get an event. And in the third case, what happens is you will have subscriber groups. So you'll have, let's say this is one group number 1, and then you have a second group, group number 2. Let me change the color of these. And only one subscriber per group gets access to the event. So in this group, only one subscriber got access to the event. And here, only one subscriber, which is the second one, got access to the event. So these are the three options that we have, right? First is where all the subscribers get all the events from the topic. Second is only one subscriber get that event from the topic. Third one is a bit hybrid, where you have consumer groups, and in each group only one will get access to the topic. Okay, so I think I can remove this now, because now you would have understood it, and I don't want to like clutter up this board too much with too many diagrams. So now that you have a visual on that, so this is useful for use cases where there is no shared state across consumers, right? Because there's no shared state, so all subscribers can have access to all topics. And chat applications running on client devices are good fits. So let's say you have a chat application and running on client devices, like let's say on mobile phones. This is a good fit for that model. Here, event processing requires updating different states, that of the chat app in client devices whenever a new chat message is sent. So when all subscribers to a topic are getting all the events for the topic, that just is a good use case for places where there's no shared state and all the clients are working differently, and all clients can show the message when a new chat is sent. But this model is commonly used for use cases when event processing involves shared state. So by shared state, what you mean is, in this case, let's say sending an email. So let's talk about that. So as multiple subscribers, processing an event would result in inconsistencies. A common example would be subscribers that send an email when an event occurs. So for example, new user signs up. Now, if there are multiple subscribers that are running and all subscribers process the event, then multiple emails would be sent. But because there's a shared state, so we don't want that to happen. All right. So this is great for chat, great for email, because we don't want that to happen twice. Now, having subscribers grouped up into groups and having all groups and only one subscriber per group get an event. And this allows multiple processing actions to occur at different points in time and has many instances of each subscriber type per group to scale processing capabilities. So I like this a lot because this is like a hybrid. You can have multiple consumer groups, which is anyways really good for scalability. And then you have only one member in each group getting access to the event, which also is great for efficiency. A drawback compared to the previous model is that it requires additional coordination mechanisms, which is a problem between brokers and consumers for group membership and group message processing. So because you've created these consumer groups, so you need now better coordination mechanisms because there are these groups. And so brokers and consumers have to have like a group membership because the entire group subscribes to a topic. And the group needs to have message processing capability. So we have these three different types of message delivery options in event streams. And we have two different types of delivery models. And now that we have discussed the message delivery options, let's talk about the delivery models. There are two delivery models with streams. One is the push versus pull model, which we have already seen before. And then there's this new one, which is the connection initiation. So let's look at the one that we've already seen before, which is the push versus pull model. But here is just much better described because I have these two nice diagrams to show you. So in the pull model, what happens is the subscribers keep making calls to the broker to check if there are any new messages for the subscriber, and then you get the messages, and then you get the subscriber sends an acknowledgement saying that yes, I have received the messages that were meant for me. But this is not that efficient because you always have to keep making this pull call all the time to the broker. And then you have the push model where the broker directly sends the messages to the subscriber. And then the subscriber sends back an acknowledgement saying that yes, I got the message. So it's just lesser steps. In the push model, much better. So let's just quickly go through what I've written. In the pull model, subscribers send a message to the broker when they want to receive events, and only then the broker sends them data. Subscribers need to maintain the state to know what topics exist and what data to ask for. For example, where to read from in a particular topic. In the push model, the broker determines when to send data to subscribers based on its own logic. Subscribers do not need to maintain state or implement special logic to coordinate amongst themselves. Okay. Now the other one is the connection initiation. So you understand the pull versus push. Now let's understand the connection initiation. So the connection between broker and subscriber can be either subscriber initiated or broker initiated. Broker initiated models require the broker to know about existing subscribers. This can be achieved either through static registration, which is webhooks, or a service discovery mechanism. In subscriber initiated models, subscribers need to be aware of the broker's address. These models are more convenient when there are many dynamic subscribers, especially in environments when service discovery is not feasible. So what's being said here is that in this connection initiation delivery model, what happens is that either the broker or the subscriber can initiate the connection, right? The connection between the broker and subscriber can be initiated by anybody. And then there are these, then there are obviously two categories, the broker initiated ones and the subscriber initiated ones. And the broker initiated ones, it requires the broker to know about the existing subscribers, the list of the existing subscribers. And in the subscriber initiated ones, the subscribers need to be aware of the broker's address, okay? And if the subscribers are not aware of the broker's address, then obviously they won't be able to get any messages. So these models are more convenient, okay? So that's why you would prefer subscriber initiated ones, because they're just more convenient. All right, now let's look quickly at the advantages of using streams. So we already know why we're using streams, right? One is decoupling, of course. Then the teams can work independently on different microservices and different things at the same time. So that's team independence. And then you have reliability, because once you are sending messages through streams are durable, so things become more reliable. And then you have real-time feedback, because constantly the events are being streamed. Now let's look at what is decoupling. So as an implementation of the pub/sub pattern, you decouple publishers from subscribers. There's no need for publishers and subscribers to know about each other or keep up to date with membership lists. Then you have team independence. So decoupling brings team independence. So different teams can work on subscribers for the same type of events without needing to coordinate. Reliability. So suppose consumers, suppose the consumer is down and the events are not lost, you might still incur processing delays if you lack consumer or downstream capability. And then you have real-time feedback. So you can have state changes to an entity's state, allowing for real-time experiences. You can have that because you can process events. The users don't have to wait minutes or hours to see their operations take place. So as soon as you send an event, you quickly see the response to that event, which could be a microservice taking some action based on that event. So these are the advantages for using event streaming. So by now, we have spent, close to 4 hours, and especially in the last 1 hour, we have been discussing about event-driven architecture. And we have learned quite a bit. We have learned about events. We have learned about different types of events. We've learned about how to design events. We have learned about message queues. So what are queues and features of message queues and queue benefits, pub/sub features, use cases, and core components and benefits of pub/sub as well. So with pub/sub, we have seen the 4 key components: benefits, use cases, and features. And with event streams, we have looked at the components, how it works, the features, message delivery options, delivery models, and advantages. So we've covered quite a bit of stuff now. And now let's talk about the event bloat problem. Now, event bloat problem is everything that we have been trying to reduce with the help of. So when we covered the designing events topic and the characteristics of events topic, all the things that we were discussing was basically to avoid event bloat. But this is something that you need to know about. So that's why I have like a separate, I'm talking about in like a separate section here called the event bloat problem. And event bloat occurs in event-driven architectures when events, they start carrying excessive, redundant, or irrelevant data. So of course, like events, like I said, they're not signals but data, and they are supposed to carry some amount of data which microservices can use to take actions. But you can't have the microservices carry, the events carry excessive redundant or irrelevant information, because if you do that, that makes the events unnecessarily large. And this can lead to performance issues, increased network latency, and higher storage costs. So there's an example here. These are the three problems that happens: performance issues, increased network latency, and higher storage costs. So for example, suppose an order placed event includes not just the necessary order details like order ID and product list, but also includes the entire customer profile like name, address, purchase history, etc. This data may not be needed by all services consuming the event, especially if they only require specific information such as the order ID or item details. Okay, so what we're saying here is, that the order place event has a lot of extra details, like for the customer, like the name, address, purchase history, and you might not need all this kind of information. So this data may not be needed by all services consuming the event, especially if they require only specific information. So for example, they just need order ID or item details. That's it. They don't need all of that. So what you can do, so that means the event is bloated, right? It's having information that's not needed by anybody else or any other microservices. So how do you fix that? So you only include essential data. So limit the event payload to only the information needed by consumers. So for example, the order placed event might contain only order ID, customer ID, and product list, leaving out the complete customer profile. So you can do this. Or you can reference external data. So instead of embedding large data chunks, include reference or IDs to retrieve the data if necessary. For instance, instead of including the full customer profile in every event, include a customer ID. And consumers can use that to fetch additional details whenever they're required from a separate service if required. Okay, so you can include only the essential data. You can reference external data later on, or you can use event envelopes. So if an event must handle multiple use cases, use an envelope with metadata to let consumers know what parts of the event to process. This avoids sending multiple redundant events and ensures efficient event processing. Now this metadata, if you look at this, this metadata is to let consumers know what parts of the event to process. So even if the event is bloated and has a lot of data, which probably is not required, you can use event envelopes, in the sense which envelope basically means metadata, so that consumers know what parts of the event to process, so they don't have to go through the entire event data and then process everything. They just know exactly what to process. This avoids sending multiple redundant events and ensures efficient event processing. So that's the event bloat problem and how to solve the event bloat problem. The reason I covered it is because once you start building event-driven systems, you will face this problem, especially once the systems have matured. So you won't face this problem in the beginning, but once the systems have matured, you will start facing this problem, and then you'll have to worry about how do you go about reducing event bloat. So that's why I've given you this solution already. The next is the difference between queues and streams. So we've been learning about queues, we've been learning about streams, and now it's important to look at their differences so that we can find the right use case for the right technology. But before we do that, just want to tell you about my private mentorship. So I provide private mentorship, and I've been doing this for quite some time now. And this is only for senior engineers. It's not for junior roles. If you're a senior engineer with more than at least 8 years of experience and you're looking for engineering leadership positions, this is the right mentorship for you. And this is like a private mentorship with me, and we'll have weekly deep dive private video calls for 3 months where we'll solve real world assignments, and there will be some assignments that you'll do on your own, some that you'll do with me. This contains a lot of distillation of decades of knowledge that I've gained building scalable systems. It's complete, and it'll be completely customized for you. It's not like a random program that we'll be following. It'll be customized based on your goals. And we'll be working on all of these things. We'll be working on your architecting knowledge and architecting skills. We'll be working on your system design skills. We'll be working on your scalable systems knowledge, your data intensive systems knowledge, how you manage teams and technology. We'll then deep dive into disruptive tech, whatever is new on the horizon, like Gen AI, LLMs, AI agents. And it contains a lot of support. And the outcomes will be that you'll do extremely well in your engineering career. You'll know everything about building scalable systems, and you'll excel at senior level interviews, which have a lot of system design and architecture and data intensive questions. So this is what's all about. If you're interested in this, if you have like 8 years of experience or more, and you've been in technology for a long time, and you want to know how to, get your next play, how to take it up a notch. I'll be sharing a form in the description of this video, which will be the engineering leadership form. Make sure you fill it, and then we can get on a call, and then we can discuss on how to tailor this for you. All right. So now let's go to our queues versus streams. So queues, you would see technologies like RabbitMQ, IBM MQ, AWS SQS. Those are queue technologies. And for streams, you have Kafka, Pulsar, Flink, and Kinesis. And streaming and queue consumers are different in terms of delivery. So queue delivers given message to only one consumer, whereas streaming broker sends it to all subscribers. Moreover, once delivered, queue message is lost. So if once the queue message is delivered, it's lost. On the other side, since streaming broker is a big distributed log file, the consumers are able to move back and forward and reprocess already received messages. So there's a lot of reprocessing possible when we're working with streaming. So the throughput of streams can be high. Throughput basically means that the amount of events that they're handling can be high, and your individual components connected to the stream can get overwhelmed sometimes. So that's why we learned about back pressure, right? So you can decouple processes using queues. So what we're saying is that we can have streams but also use queues at the same time. So instead of publishing and consuming directly off of a stream, you can implement queues to push data to and subscribe to. The queues can be connected to the streaming system. Now this point I would like to say is very, very important, because this is something that I do a lot in production, where you use queues and streams at the same time. You don't want to connect your services directly to the stream. You can have queues to help reduce back pressure. So now when I'm talking about this, I'm talking about systems that are at millions of users. That's where you would want to do something like this, where you have queues to deprocess, to decouple your processes. Okay. Then your queues keep the data in proper order, whereas in a stream, the order doesn't have to be proper, because there's a lot of reprocessing and you don't lose the events and all of that stuff. And event streaming, consumers can use a pointer offset. So we learned about offset, right? So we are able to go back and forth between messages, whereas with queues, consumers read a message from the queue and gets deleted after they process the messages, because they're getting processed sequentially. Event streaming, different consumers can subscribe to the same channel and get notified about the same event. And in message queues, high load tasks can be distributed via horizontally scaled consumers, so the consumers can share the load. Now, and in event streaming systems, message ordering is not a key feature. It can also be established on a partition shard level. In the sense, we learned about message ordering, and then that in streams you don't have to have it, but it's not a key feature, but it can be established if you wanted to. In message queue, you can enforce message ordering with FIFO queues. We learned about FIFO queues already, and process the tasks in the right order, in the first in, first out order. In event streaming, it's also a good fit for the systems that rely on immediate action on data. So event streaming is a good fit for systems that rely on immediate action. So like real-time systems work really well with event streaming. And like in the near future, I will have a system design video for you, where we'll talk about real-time systems, which is a huge topic. And that's completely linked with event-driven architecture, because you can handle multiple events in real time and have like real-time events, like real-time actions being triggered based on these events. So for example, a stock exchange would be a real-time system. And then you have message queues. So the data doesn't have to get processed in real time. The goal is to process the message in the desired time interval. So you have a time interval, and the message can get processed at that time. So you can have it in a time interval, or you can have it near real time, but it won't be real time. But with event streaming, it can like get very close to real time. And Kafka has replayable logs, so we can go through all those messages again, and can play the role of an event store. So Kafka can also play the role of the event store, a middle ground between a messaging system and a database. So Kafka is not just a messaging system. It's not a database. It's in between. It can have replayable logs. It can send real-time events, but it can also be a database in the sense storing all those events. Where replayable logs decouple services from one another, much like a messaging system does, but they also provide a central point of storage that is fault tolerant and scalable. which is a shared source of truth that any application can fall back to. Okay, and this is all that I wanted to cover. Now there is more information. I don't think that's important at the moment. I don't think that's necessary. So we can skip it. If you want, you can read more, but I don't think that's necessary right now for this video at least. And what we can go to is the EDA takeaway. So we have been learning about event-driven architecture, and here what I've done is I've summarized all the takeaway. So whenever in life, whenever you want to come back to this and you don't want to go through the entire video, don't want to go through the entire board, you can just look at this. This is the takeaway from event-driven architectures. Okay, so there are three things: benefits, when to use, and challenges. So let's look at when to use. When to use event-driven architecture. So you use it when you have cross-account and cross-region data replication. So you must have seen how Netflix and companies like Uber, they have like different regions and different countries where they operate in, right? So you can have an event-driven architecture to coordinate systems between teams operating in and deploying across different regions and accounts, because Uber India works a little different, and they have different features for the users, different currencies, different time zones. A lot of things change based on the region. So you want to have you have teams like an engineering team based in India, engineering team based in the US. They're operating in and deploying across different regions and accounts. So this means that the teams are deploying from different regions to different softwares. Like Uber India is a very different software from Uber US. But this also means that in the cloud, you have like when you go to AWS, you have a different region, like in Mumbai servers or servers in on the west coast of US or in the east coast of US. So you have different regions as well. So by using an event router to transfer data between systems, you can develop, scale, and deploy services independently from other teams, right? So both types of region definitions that I've given you, plus if you have an event router, you can transfer data between systems, you can develop, scale, and deploy services independently from other teams. You don't have to depend on other teams working in different regions. And then you have resource state monitoring and alerting. So rather than continuously checking on your resources, which you don't have to now, you don't have to keep polling, which was the pull-based method, you can use an event-driven architecture to monitor and receive alerts on any anomalies, changes, and updates. These resources can include storage buckets, database tables, serviceless functions, compute nodes, and more. Anything that you want to check on continuously on your resources, you can use event-driven architecture. And fan out and parallel processing. So we talked about this. Parallel processing and fan out helps us process multiple events parallelly at the same time. So if you have a lot of systems that need to operate in response to an event, you can use an event-driven architecture to fan out the event without having to write custom code to push to each consumer. The router will push the events to the systems, each of which can process the event in parallel with a different purpose. So consumer 1 can process it in a different way. Consumer 2 can process it in a different way. So the events can be processed in parallel, but with different purposes. And integration of heterogeneous systems. So if you have systems running on different stacks, like if you remember in the beginning of the video, I gave you examples about how a microservice can be on Python, another could be in Golang, another could be in JavaScript or Node.js, and they're running on different stacks. So you can use an event-driven architecture to share information between them without coupling. So you don't need to couple them. It can be decoupled, and you don't have to share. You can share information between them very easily with the help of streams. So the event router establishes indirection and interoperability among the systems, so they can exchange messages and data while remaining agnostic. By agnostic, we mean like language agnostic. So it can be Golang, Python, Node.js, doesn't matter. So now that we've looked at when to use these, let's look at their benefits, and then we look at the challenges. So the benefits are scale and fail independently. So when you have decoupled your microservices, they are only aware of the event router and not each other. By event router, we basically mean something that's helping us to determine which events go to which microservice. This means that your services are interoperable, but if one service has a failure, the rest will keep running. So this is something we've talked about a long time back in this video itself, where we said that if one service has a failure, the rest will keep running, and that's the whole point of microservices. You can audit with ease, which is what I was talking about a long time back in this video itself, where we talked about it's very easy to isolate issues and determine where the issue is and fix them. So an event router acts as a centralized location to audit your application and define policies. These policies can restrict who can publish and subscribe to a router and control which users and resources have permission to access to your data, and also encrypt your events both in transit and at rest. So you can encrypt your events, but not only that, but you can also you can also have authentication and authorization for your producers to be able to come and then post events onto the stream. And then you can encrypt those streams, those events as well, both in transit and at rest. Then you can also develop with agility. So this we have talked about when we're looking at things from the CTO's perspective or the DevOps perspective long time back, where you can say you can develop and deploy with agility. In this video, like towards the beginning, that's what we discussed. So you no longer need to write custom code to poll, filter, and route events. The event router will automatically filter and push events to consumers. The router also removes the need for heavy coordination between producer and consumer services, speeding up your deployment development process. And you can cut costs. So this way, you're not paying for continuous polling to check for an event. This means less network bandwidth consumption, less CPU utilization, less idle fleet capacity, and less SSL TLS handshakes. Okay. So we've talked about the benefits, when to use. Now let's look at the challenges. The challenges is guaranteed delivery. Sometimes you don't have guaranteed delivery. You don't know if the event will be delivered or not. You don't know if you want to process events in order or exactly once. So each consumer type typically runs in multiple instances for resiliency and scalability. This can create a challenge if the events must be processed in order. Then you have how do you coordinate message across services. So business processes often involve multiple services publishing and subscribing to messages to achieve a consistent outcome across a whole workload. So you're not sure how to coordinate messages across services. Error handling is also a bit difficult when it comes to streaming and event-driven architecture, because we mainly use asynchronous communication. A challenge with this is error handling. So one way to address this is to use a separate error handler processor. So when the event consumer experiences an error, it immediately and asynchronously sends the erroneous event to the error handle processor and moves on. So you need a separate logic to be able to, or a processor to be able to handle errors, because error handling is challenging when it comes to asynchronous communication. And then you have data loss. So another challenge with asynchronous communication is data loss. So if any of the components crashes before successfully processing and handing over the event to its next component, then the event is dropped and never makes it to the final destination. This means that there is data loss. So this is another challenge with event-driven architecture. So this is the complete takeaway. Very quickly, we went through it in like 2 minutes or something. So at least it's very quick to go through in the future as well for you. So at least you can remember that. Now we have been talking about events, but what's important is that events can be processed. So we talked about how you can do aggregations and ingestion. So events can be processed, and transforming events can be transformed. And now all we're doing is we're just going to talk about why would you want to transform an event in the first place, and a little bit about basics of event-driven processing. And we'll talk about batch processing, which is not event-driven processing, which is processing events in a batch when you don't want to put a lot of load on your resources, and you want to keep gathering the events and then process them all together at the same time later on. And once we've done all this, we'll then talk about how do you scale an event-driven system, and then we'll talk about how to scale with service registries. Then we'll talk about a few topics that I want to cover, but I didn't get a nice way to bring them. So up until now, everything is almost like in a story, right? So we are talking about event-driven architecture, then events, how to design events, queues versus streams, the event bloat problem. So everything is going almost like in a story, but these I couldn't fit anywhere, but these are like important topics that we should discuss. So we'll go through these anyways. These are things that we want to cover next. So this is this section, and then the next section is about considerations, like when would you consider synchronous microservices versus asynchronous microservices. And then we'll talk about the hexagonal architecture for microservices. And then we'll talk about failure and resilience in microservices and challenges with microservices, because everything is not rosy. And then we'll talk about something in between, which is the modular monolith, which I've covered in my cloud architecture series. And then we'll talk about when not to use microservices. So that's it, and that'll conclude our video. So now let's start talking about events and how to process them. All right, so now we're discussing about how events can be processed. So one of the main determining factors of event-driven architecture is that the events can transform and they can be processed. By process, we mean transform in the sense the state can change. And by processing, we also mean from the microservice, the downstream microservice, when it gets the event, it can take some action based on that. So processing basically can mean two different things, but they're essentially the same thing. So let's talk about processing. In an event-driven system, when events are emitted, they get processed, which is basically how the system responds to the events, which in this context is talking about how a microservice would listen to that event, would consume that, and then take some action based on that. By processing, this is the second context. By processing, we also mean that an event can be transformed. Inside the stream itself, the event can be transformed with the help of various operations that can be processed on the event, such as filtering the event, mapping the event, or any other type of custom transformation. So not only do you have filter, map, and aggregation, although all those existing transformations, but also any custom transformations that can be done. Okay, so transforming an event is essential to making the event data more useful. So why would you transform an event? Because you want the data to become more useful. It needs to become more understandable for the microservice that's going to consume this, or compatible. So maybe the microservice that needs the data, it wants the data to be in a separate format, maybe a CSV format, maybe XML format, maybe JSON format, and the data is probably not in that format. So you want it to be compatible with the consumers that will process it, or you want it to be more useful or understandable. Okay, by useful we mean it should have more data. By understandable, it means it needs to have more information, and by compatible, it means it needs to be in a different format, right? These are the three different meanings. So now we look at the different types of transformations that you can apply on an event, and also why would you want to do that. So we have the reasons. So here are the different data transformations that can happen, but along with the reasons on why you would want to do that, okay, and how that works. So the first one is data enrichment. So data enrichment basically means adding more data in that event. So enrichment, as you know, is just providing more data or more additional context to the data to an event, helps downstream services make more informed decisions. For example, so I've given examples for each of these. So as you can see here, for example, that I've given examples for each of these. Because I believe with examples you just understand things much better. An order event might include customer details, product information, or pricing data to allow each service to process it fully without needing to make extra queries. Now, if you have another microservice that's dependent on an order event, you don't want it to make extra queries because that just makes the system more inefficient, right? If you are getting some data and then based on that data, some information is missing in that event, and you have to make more queries to just get access to that event. That just sets off a chain of more requests and more queries and more API calls, and that just makes the system less efficient, right? And we don't want that. So we want to include as much data as possible, or at least as much context about the data as possible, so that the service doesn't have to work any harder after it's received that event. The second one is format conversion. So remember I mentioned how the data can be more compatible. So that just means this, which is format conversion. So different services might have unique data format requirements. For example, one service might expect timestamps in UTC, while another uses a local time zone. So transforming the event to standardized formats ensures compatibility and avoids data mismatches. So you don't want data mismatches or data integrity issues, and this is why you would want to follow standardized formats. And it's totally understandable that some services have different expectations of the same type of data, and that's why you would want to have format conversion in the stream itself. Then the next is filtering and reduction. Sometimes not all information in an event is needed by downstream consumers. Removing unnecessary data fields or filtering specific details can reduce the payload size. So we discussed this when we were designing events, when we were talking about designing events and how events should be as efficient as possible, have only the details that are very important. And also then we talked about event bloat, where we learned that an event can become really big if we keep adding unnecessary details. So removing unnecessary data fields is important, and filtering specific information and details can reduce the payload size, which is important because the smaller the payload size, the more events you can have, and the more efficient the system can be. And you can improve processing efficiency and minimize network bandwidth usage, which just makes the system more scalable. Then you have aggregation. So events may be grouped or aggregated to reduce the number of events or summarize information. So aggregation in this scenario is talking about grouping the information or summarizing the information. For example, instead of sending an individual event for every item in an order, a single aggregated event might summarize the entire order, which simplifies processing. So an order, whenever you place an order in an e-commerce platform, or even a food delivery platform, anything to do with commerce, you would order some items, right? So instead of sending each item and all the details of each item, you can just send one event which would have information about the order, and that order can have all the items that were ordered within that order. Okay, so that just reduces the number of events. Then you have schema evolution. So over time, event structures or schemas may change as systems evolve, and that's totally acceptable because your architecture will keep evolving based on the requirements of the customers. Like let's say the users who are using your platform, they might want more features. You'll end up adding more microservices or more features, and the events that are being consumed by those new microservices or even the old microservices, they might need to evolve. So the schemas will change as systems evolve, and transformation allows you to maintain backward compatibility with the older services. So the older services will probably need the data to be in older format. The new microservices will need the data to be in new format. So you can maintain backward compatibility with older services by converting events to a format that legacy services can still process, easing system upgrades and migrations. The other thing that that transformation can help with is security and privacy, because transformation can also be used to obfuscate. Obfuscate basically means randomize information or encrypt information or redact sensitive information, which is like removing the sensitive information, ensuring compliance with privacy regulations. For example, a transformation might mask personal identifiers. Personal identifiers is basically somebody's name, somebody's email, so you can mask all that information before sending events to analytics services. Because with analytics, the way analytics should be that there should be no personal information. Like even if when you open, let's say something like Google Analytics, right? Google Analytics or Mixpanel, you don't see personally identifiable information like this person with this email address with this name is doing this on your website. You don't see that. You just see that a user from India at this time zone at this time logged into the website and did this. So you can have that, and then you have these examples. So imagine an e-commerce platform where an event is generated every time a user places an order. This order event may initially include sensitive data like payment information or internal details that only some services need. So by transforming the event, the system can remove payment information. Okay, this is one thing. You can do one more thing, which is add enriched data like shipping priority based on the customer status for services that handle shipping. The third thing you can do is format dates and prices to ensure consistent data presentation. So here we've given an example that of an e-commerce platform where there's an event, and we can do multiple things to that event. We can remove information, we can add information, and we can transform that information. So 3 different things we're doing to the same event, just making it more efficient. Now there are these different event transformation techniques. So we've been talking about event transformation, but let's also see what kind of event transformation techniques exist. So you have event routers. So even unknowingly, we have been talking about event routers here, right? So here, if you remember in the EDA takeaway, I was talking about things from an event router's perspective, right? So if you notice here, we were mentioning about event routers, okay? So let's talk about what exactly it is. So the event routers can direct events to specific transformation functions based on event type. Okay, that's what they can do. Then you have these middleware services which implement transformation logic in middleware, allows events to be modified centrally before they reach various consumers. And then you have ETL. Now, event routers, middleware services, and ETL, these 3 things I plan to cover in the next video in much more detail, especially ETL, because this is a huge topic. And this is more related to like data intensive systems, big data and data engineering. It's more related to that. So that's why I've not covered this in microservices, because microservices is a very architecture kind of a topic, whereas data intensive systems and data engineering is a very different topic, very different subject altogether. But yeah, so the ETL pipelines are common in data intensive applications where events need to be transformed as part of a larger data processing pipeline. But yeah, these need to be studied in detail. I'm just touching upon them, just telling you what these things are. But like I said, these need to be studied in like much more detail. Okay, so now so we've talked about why would you want to process an event and how events get processed, and we've looked at some examples. And we've been talking about processing events, but now let's see a little deeper. Let's go a little deeper into event processing basics. Okay, so one thing is stateless topologies. So what that means is that the events, right, the way you process these events need to be independent of the past events. In the sense, the past, the event that was there, the one before, that has no connection with this new event. So in this setup, no information is retained between events, meaning that processing of one event has no impact on the next. So it doesn't mean that if the previous event you did some aggregation, this new event that was created, you would also do aggregation on that. Maybe you'll do mapping or filtering on that new event. So they're not related. So this is particularly useful when events are simple or unrelated. So ideally, this would be the right approach. You want to have as less state sharing as possible between the microservices. I'm not sure if that is clear right now, but with microservices, you want to have like stateless microservices. You don't want to have a common shared state between them. I'm not sure if I covered that before, but I'm just like informing you now. That's how you want to build, and that's usually the right practice to build backend APIs and services. So I'm assuming you've been building systems for some time now, and that's probably also how you build APIs and how you build your backend systems. So the front-end system is aware of the state, right? The front-end system is a little smart, but the backend has to be dumb. The APIs have to be stateless. They don't have to share state. That's usually how you do it. That's also how microservices are supposed to be done. I don't think I covered that in this video, but I'm assuming that's how you've been doing stuff up until now. So this is particularly useful when events are simple or unrelated, as it allows for high parallelization and faster processing. So high parallelization is basically you are able to handle multiple different types of events parallelly at the same time, and also able to faster process them. So these two topics, right, higher parallelization and faster processing, I will be covering in just about 10 minutes from now when we talk about scaling an event-driven system. So even if it doesn't make sense to you, don't worry. We'll talk about faster processing and why faster processing is important. How do you even go about it? Okay, so coming back to this, so it allows for high parallelization and faster processing. For instance, in a filtering operation, which is removing events that don't match a specific criterion, each event can be independently evaluated and passed along without retaining context. So you can, when you're performing any filtering, each event can be independent. So each event, you can evaluate each event independently, and you can pass it along without retaining context. Now, when you say retaining context, that is kind of what's being said here is the state. So there's no sharing of state between two different events or retaining of context between two different events. Like they're completely unrelated. That's what's being said here. Then these are the transformations you can apply. So you can, so by now you know that transformations mean that they modify the content or the structure or the attributes of these events, basically state change of the event to fit the needs of the downstream processing. We have already established that in just the previous section. So this can include various operations such as, so these are the various operations you can do in transformation, which is filter, map value, and any other custom transformation that you want. So I've been talking about these things up until now, but we have not talked about what these are. So let's discuss these. So filtering is selecting events based on a specific criterion. So you say that it's almost like when you're in an e-commerce website and you say, I want to only view products that are below $5,000, right? So that's filtering. So we are only selecting events based on a specific criterion. For example, filtering events to only include orders over a certain amount, just like I mentioned. And mapping is each event by applying, transforming each event by applying a function. For instance, mapping an order event to add a discount percentage based on customer data. So if the customer has purchased something in the past or he's a valuable customer, so you can just add a discount percentage based on that. So that's called as mapping an order event. And then you have custom transformations. So these are tailored functions. So you can create your own functions like adjusting timestamps to a different time zone or appending additional metadata to each event. So any type of custom transformations, which is not like a filter map or map values, anything like that, would be considered as a custom transformation. And you can apply any type of custom transformation on the data that you want. And then you have map value. So it's similar to map, but specifically targeting the value proportion of a key value event. So we've seen the keys and values in a keyed event, right? A keyed event, I showed you what a keyed event is, and we've seen the key and value. So here we can specifically target the value portion of the key value event. For example, adjusting only the price value in a retail transaction event. So let's say the product ID is something, and the value, the price is $5,000. So you adjust only the price value in a retail transaction event. That's your map value. All right. Now the next thing is branching and merging streams. So the next is branching and merging streams. So branching allows splitting an event stream. So you have event streams, right? But you can one thing you might not know by now is that you can split these streams and you can also branch them back. So splitting an event stream into multiple streams based on conditions, while merging combines multiple streams into a single output. This is essential in workflows that require different processing for certain types of events or when consolidating information. So when you want to consolidate information, you will combine the multiple streams into a single output. And when you want to process the events differently or separately, then you would split the event stream. So let's learn more about branching. So branching is useful when events need separate handling of paths. For example, a single transaction stream could be branched into high value and regular. So let's say if there's there are more expensive transactions happening, you would want to branch them out into high value stream, and then if there are regular or small scale transactions happening, you can have them in a regular stream based on the transaction amount. And this way you can handle, like let's say that the high value transactions, you can handle them separately, perform different operations on them, or even have more failure resistance there. And merging, so merging is useful when information from separate streams is needed together for final processing. So you have data in multiple streams and you would want them together for some final processing. For example, a payment stream and an order fulfillment stream would merge to create a comprehensive completed transaction. So in a completed transaction, you would need the data from order fulfillment. Order fulfillment basically means shipping it out, and payment when the payment is completed. So completed transaction basically can have both the information from both these streams. So you can merge the streams together. And then we have something called as repartitioning. Now these three things are in italics because these are slightly more advanced, and I was not planning to cover these three today in this video. I wanted to cover that in the next video, where we'll have a little bit more deep dive into how Kafka works and the Kafka concepts. So I wanted to have these there, but I will touch upon them today anyways a little bit, and we can do a deep dive into them in the next video. But let's talk about repartitioning event streams, which is also a advanced topic. So these four actually are slightly advanced topics, and you don't have to know them right now if you're not working with Apache Kafka on a day-to-day basis. So repartitioning involves redistributing events across partitions. So if you remember, you have topics, and inside topics, like at a more granular level, you can divide topics into partitions. And partitions and repartitioning basically means redistributing events across partitions to optimize processing or aligning events according to a new key. So repartitioning is often necessary when processing logic changes require events to be grouped differently for efficiency or consistency. So repartitioning basically means that you changed the key, basically, which aligning events according to a new key. So repartition. So you had partitioned those events going to a different going to a specific partition, and now you just repartition them. That's all that it means. But it has obviously way more consequences and nuances that we can dive deeper into in the next video. So if an event stream was originally partitioned by transaction ID, but processing now requires events to be grouped by user ID. So for example, event stream originally partitioned by transaction ID, and now we want the the events to be grouped by user ID, then we can just repartition the stream by user ID, which will enable us to more efficiently process per user. And then you have something called as co-partitioning. Co-partitioning means that two or more streams are partitioned, which are partitioned the same way, which is crucial when events need to be processed jointly from multiple streams. So very similar to how merging was working, but yeah, it's very similar. For example, if you have an order stream and a shipment stream, co-partitioning by order ID, and yeah, you have two streams, like an order stream and a shipment stream. You can co-partition them by order ID, which will ensure that events with the same order ID land in the same partition, simplifying correlated processing. So you want to process these two at the same time together, so you can use co-partitioning. And then you have assigning partitions to a consumer instance. So in a distributed event processing system like Kafka, partitions need to be assigned to consumer instances to balance the load, right? Because as we know, consumers are the ones that are related to partitions and topics, and they're listening for events. So each partition is assigned to a specific consumer instance to process events in parallel across multiple consumers, increasing the throughput. So this is all about increasing the throughput and how to handle events in parallel across multiple consumers. So for example, if there are 3 partitions and 2 consumers, one consumer might handle 2 partitions while the other handles 1, depending on the partition assignment strategy and the number of consumers available. So it's all about dividing partitions amongst consumers. So in this case, we are saying that one of the consumers can handle 2 partitions while the other can handle just 1. And it depends on the partition assignment strategy. You can change it also at any given point of time, and depending on the number of consumers that are available at that time. So then you have these partition assignment strategies that we were just talking about, and that's assigning partitions. So we talked about partitions, we talked about co-partitioning, and now it's all about assigning the co-partitions with the help of partition assignment strategies, which we talked about here. But these are the 3 ones: round robin assignment, custom assignment, and static assignment. So round robin, if you've worked with the round robin algorithm, what it does is it just assigns evenly across all consumers' instances. And this ensures balanced load distribution, but might not be ideal when events need to be processed by the same consumer due to dependencies. Okay. And with custom assignment, partitions are assigned based on custom rules. So here it's round robin. So round robin, if you've been working with computer systems for a while, you would know round robin is just evenly distributing across. So round robin is a very common strategy or very common algorithm for load balancers. So if there are multiple servers and we want to decide which server the traffic should go to, so we usually go with round robin, so that equally dividing traffic amongst all the servers. So this is the strategy we're following here. Or you can have a custom assignment strategy. So the custom assignment strategy is more useful in specific scenarios where partition affinity or data locality is essential. And then you can have static assignment. The partition is assigned to specific consumers. So static, in the sense we have defined which consumer is supposed to get which partition, and that does not change even if consumers are added or removed. This is beneficial in stable environments. If you require more consistency, then this is more beneficial, where you want stability and more consistency by the same consumer is required. Okay. Now the next one. By now we've learned a little bit about how to process events, and we've learned about the transformation of events, why to transform these events, and what kind of transformations can take place. And then we've also learned about a little bit about event-driven processing basics. Now it's all about batch processing. So I had mentioned that there are 2 ways that events can be processed. One is in real time, which is event-driven processing, and the other is batch processing, where events can be gathered and they can be stored for processing later on. And what this does, what happens with batch processing is it leads to lesser load on your services, because you don't always have to keep running servers at maximum capacity. You can at night you can increase the capacity of your servers, process all the events in one go, and then come back down the next day. So batch processing of events refers to the practice of grouping multiple events together and processing them as a single unit or batch, rather than handling each event individually in real time. So you don't have to be in real time. There's no urgency. That's why you're going for batch processing. And this approach is commonly used in event-driven architectures and data processing pipelines, where processing events in real time is not always necessary. So you can have more efficiency that can be gained by handling events in bulk. If you handle all of these events together at the same time at a particular time in the day, is just much more efficient. So what are the key reasons? Why would you want to go for batch processing? Now, before we talk about the key reasons, let me show you what batch processing is. So you can create these processes and they go to the storage where all the events are stored, and based on that you pull out those events and then you process them together. Okay, so batch processing, you can process huge amounts of data periodically with limited resources. So latency is high because processes have to wait for a pre-designated time. So let's say 12 a.m. at every night, all the invoices that have been generated in the system will be converted from PDF into XML, let's say, for example. So or all the invoices that have been generated up until now will be converted into PDF for sending to the users. So all of those kind of processes are batch processing, and this is very common with image generation, with with video generation. Those kind of let's say if there's a website that helps you render videos, so you can edit, and then when you're rendering, maybe they render all the videos at the same time. So those kind of things can be done with batch processing. And with batch processing, failure handling is extremely simple because you are processing all of the load in one go, and you are aware that the batch is running at, let's say, 1 a.m. and whenever some problems happen, you can easily fix them, because in real time you always need to be aware of when the issues are happening, and then you need to have like really advanced technology in place to be able to handle those errors. Now we can talk about the key reasons for why you'd want to select batch processing. It's because of efficiency and performance. So processing events in batches reduces the overhead of handling each event separately. And by grouping them, the system can reduce the frequency of database writes, network calls. So because you're doing it once every day, you don't have to, it can be once. So batch processing is once, or can be at any frequency, but it's basically not real time. That's the main idea here. And because you've grouped them, the system will reduce the frequency of database writes. So you're not constantly writing to the database, you're not constantly making network calls, and you're not constantly causing expensive computations. Computations become cheaper because you have a predictable time when you will increase the compute on your servers on the cloud. So this improves overall performance and reducing processing costs. And you have resource optimization. So batch processing allows better utilization of system resources. So as it can perform actions in bulk and reduce the strain on CPU, memory, and I/O operations. For example, writing multiple records to a database in a single transaction is usually faster and less resource intensive than writing each record individually. So all throughout the day, there are some events that are taking place, and then you want to, which is lead added, for example, in a CRM system. And then you can either keep writing that to the database as soon as the lead is added, or you can wait at night and all of the leads that have been added in the day, you can add them together to the database. So these are two different approaches. The second one is just more efficient, like it's said here, because writing multiple records to a database in a single transaction is much faster and less resource intensive. And then you have network optimization. So you can send data in batches, which reduces the number of network requests and can reduce latency by minimizing the back and forth communication between services. And then scalability also is very easy with batch processing, because it can help with scaling applications by controlling the load on downstream services. So because the downstream services have to listen or consume these events, that leads to a lot of back pressure. With batch processing, you can reduce the amount of load that's going to these services, because instead of flooding a system with continuous real-time data, batches can be processed during off-peak time. So you know that there's very less traffic at night on your system, so you can process these events at night or in scheduled windows. So for example, you know that during lunchtime 2 to 4 there's not many people on the website placing orders. So during those times you can have, which are the off-peak times, you can have these scheduled windows. So windows being a keyword which we'll talk about here. Windows is basically instances of time which have been like from example 2 p.m. to 4 p.m., 3 p.m. to 5 p.m. where we're going to be processing these events. Why I'm talking about Windows is because we're going to be talking about Windows when we talk about scaling an event-driven system. This is what Windows means there. So in case I don't talk about windowing there in the sense what it means, just know that this is what it means exactly. Okay. Now coming back here, so we've talked about this. Yeah. The next thing is network optimization. So sending data in batches reduces the number of network requests and can reduce latency by minimizing the back and forth communication. We talked about that. Talked about scalability. Talked about Reduce costs, because batch processing can lower costs associated with API calls, data storage, and processing resources by minimizing repetitive actions. This is particularly beneficial in cloud-based systems where you pay for every transaction, because you're paying per transaction and data transfer, so it's very, very expensive in the cloud, so it just makes it cheaper. How does batch processing work? So you can collect first all the events. So events are gathered over a specified period of time or until a certain quantity is reached. So you can say that all the events between 6 a.m. to 2 p.m. we'll collect all of them together and we'll process them between 2 to 4. Or you can say that we'll keep collecting events till we have 10,000 events and then we'll start processing all of them together. So they're stored in a queue or in a buffer such as Kafka, AWS SQS, or a custom message queue. Then we have the batch triggering. So you can trigger the batch when it reaches a certain size or a time threshold is met. It triggers the processing. This can be based on time intervals, like every minute this has to happen, or event volume, like every 1,000 events. Batch processing. So once triggered, the batch of events is passed to a processing system, which may apply transformations, aggregate data. These are different aggregations. These are different transformations that happen on the events that we have talked about already. We've already talked about the kind of transformations that happen on the event and why they're important. So that's what is happening. So even with event processing, that's what's happening, and with batch processing, the same kind of transformations are happening. It's just happening in a different way. So once triggered, the batch of events is passed to a processing system, which may apply transformations, aggregate data, or perform the required business logic. Then you have saving and cleaning up. So after processing, the results may be saved to a database, sent to another service, or used to update downstream systems. Any processed events are then removed from the batch queue. Okay. So now let's talk about when to use batch processing as opposed to stream processing. So we'll use it when real-time responses are not required. So e.g. periodic reporting. We'll use it when there's a large volume of data that can be processed at intervals. And we'll use it when reducing costs and optimizing resource usage is a priority. So these three reasons you will use batch processing. So this is what stream processing looks like, which we have been talking about up until now, which is events are processed as soon as possible because we get real-time results. And stream processing uses a data streaming platform like Apache Kafka. You know that by now. You can ingest events, process them, or transform the event stream. Event stream processing can be used to detect meaningful patterns in event streams. And so simple event processing is when an event immediately triggers an action in the event consumer. So as soon as the consumer consumes the event, some new action is triggered. And then you have complex event processing, where you require an event consumer to process a series of events. So instead of just one event that the consumer is consuming, you can have like multiple events that the consumer consumes, and then you detect a pattern, and then you start a action. So that's stream processing, and then this is batch processing. So we have, up until now, we've been learning about stream and stream processing, and then or processing of events in general. And now we have learned about how you can do that either in a batch or you can do it in real time. Okay, so mostly we'll be doing it in real time mostly, but I've just told you what's the other way of doing batch processing. Okay, so now there are two topics we want to cover when it comes to scaling an event-driven system. One is scaling microservices with service registries. So we can talk about this quickly, and then we'll come back here, which is scaling an event-driven system with different methods. And we'll talk about all of these different methods. But before that, I'll just quickly remind you about my private mentorship. If you have not filled that form, the Google form, which is there in the description of this video, make sure you fill it. If you're interested in the private membership, you need to be a senior engineer. You need to have multiple levels of years of experience in the industry, and you should be willing to put in the work to take your career to the next level. And this is going to be extremely effective if you want to be applying for engineering leadership positions. So you've already seen the kind of knowledge that this takes to move up the career ladder. And this is just the beginning. This is just the tip of the iceberg. There's also in this video, we're just working a little bit on the architecture knowledge and architecting skills. You probably might have also seen the course that I have on cloud architecture, probably on my YouTube channel, on technical architecture, sorry. So there's all of that information, and that series is not complete, so there'll be like many more videos in that series as well. And then there's also a system design series on my channel, which I want to continue, but I just don't get the time, so I will keep doing that as well. But yeah, so you'll need to work on your architecting skills, your system design skills, and your scalable systems knowledge, your data intensive systems knowledge. So all of this you need to work on, and then but the entire program will be built completely customized according to your skill level and according to your needs and what you want to achieve. So do let me know. You know the outcomes already by now. You'll be able to do extremely well in your engineering career. You'll be able to go up. All right, so do fill the form in the description of this video. So now let's talk about scaling an event-driven system. So let's quickly talk about first service registries. Why? Because we've been talking about service registries earlier. So now let's just learn a bit more about them. Okay, so let's learn about scaling microservices with service registries. So let's say this is your auth service, and this is your user info service, your account service, your lead service, and your deal service. So you have all of these microservices, but your auth service now is not sure about what's the server IP address for one of these services, and not sure about the server port, because these services keep changing from time to time because of new deployments. We discussed about this some time back. Now, when the number of microservices increase, it's difficult to keep track of the server IP and server ports, especially when they keep changing, since new deployments are happening all the time, and also new services are introduced every now and then. So there will be, let's say, a new service that comes up called the payment service or something like that. Something new comes up. How would you know the server IP and the server port for this microservice? Or if this service changes and you have some new updates, it changes, it gets redeployed, how would you know? How would the auth service know about the server IP and the server port for this service? So to solve that, we have something called as a server registry, and the job of the server registry is to maintain a central log and keep updating them with details of each service's current IP and port. And microservices that need info from each other can hit the service registry first. So the auth service will first hit the service registry and then take the required information from any of these microservices. Okay, so we had discussed a little bit about this, but not in this much detail. Okay, but the question that arises from something like this, the question that arises, and what I see many people struggle with when they see something like this, because we have been learning about event-driven systems, and now suddenly I'm saying that you need something like a service registry. You'll make a request to it, and then you get information. So that kind of leads to a question, which is, so if we already have data flowing in streams between the services, do we really need synchronous communication? Because this is synchronous communication. You take the IP address of one of these services and then request for some information. So that is synchronous communication. So now people start getting confused. Then, if you want to scale up microservices architecture, and microservices architecture is related to event-driven systems, then how come suddenly we're talking about synchronous communication, right? So this becomes a big confusion for many people. That's why I am talking about it right now in detail. So the answer is that yes, in some cases, it's wise to keep some part of the communication synchronous. So even though you are working with asynchronous communication now because of event-driven systems, and you have now events, and you have like streams, or you have queues, or you have pub sub, whatever you have asynchronous communication where microservices are decoupled from each other. They're not waiting for information from another microservice. But it's still wise to keep some part of the communication synchronous while everything else can be mostly async. So even though I'm saying that async communication is the best, and that's what's required to scale up systems, that's what's required for scalable communication between microservices, it is wise to have a little bit of communication synchronous. So figure on the right shows a healthy example of how synchronous and asynchronous communications can coexist. Now, before we talk about this, I want to tell you that in some time, in just a few minutes, we'll be talking about the considerations when to go for synchronous microservices, when to go for asynchronous microservices. When I'm talking about service registries, I'm not saying that the microservices are async or sync. I'm just saying that even in async microservices, you could be using service registries, and even async microservices, there could be some part that's synchronous, and that's completely all right. And we're showing an example. This is an architectural example of how this can happen. So you have these message queues, which is for asynchronous messaging, and then you have synchronous communications. You have external systems and clients, APIs, calling the services, and the API is calling synchronously to other services. Other services are calling other services. All of this is happening synchronously, and even beyond the system, the services can call external clients to get information synchronously, and that can all happen even with asynchronous messages going on. And here, example on the right shows how systems evolve with multiple types of queues or streams and multiple types of third-party APIs like SOAP, REST, and even GraphQL. So that also is one more question that people have, which is one big confusion, is that can different types of standards for APIs exist in an asynchronous systems? Like, for example, if you have SOAP, REST, and GraphQL, which is required to interact with systems outside the system boundaries of our event-driven architecture, what kind of standards can we have, and what all, and can even queues and streams be used together, that kind of stuff, right? So the answer is yes, you can use queues and streams together. You can use synchronous and asynchronous communication together, hybrid. You can also have different types of API standards that are supported, and a healthy mix of async and sync communication, like I said. So it's shown here. You have Kafka being used for orders and stocks streams. So you have events being published onto these streams and being consumed. But at the same time, you have REST APIs. So operations is making REST API calls. There are supplier backorder is going for REST API calls with third-party supplier. And you have, between the microservices themselves, you have these REST API calls happening. And then from the customer, there's a REST API call happening at the shopping cart. And then you have SOAP and REST APIs here with third-party payment providers or postage services providers. And that could be GraphQL also for the mobile app. So this shows a very, very healthy architecture on how things can coexist. And now we want to talk about scaling an event-driven system in more detail. In the sense, we have talked about how we can do it with service registries and how synchronous and asynchronous communication can exist. But let's talk about the other methods of scaling an event-driven system. Okay, so there are some obvious things that help with scaling an event-driven system, which are mentioned here. These are the conventional methods or the obvious things. Actually, let me call them the obvious methods. It's much better. And then there are the not so obvious methods. So here, what I've written is, it may be counterintuitive, but event-driven systems can actually be scaled efficiently by clever use of acknowledgements and checkpointing. So just adding acknowledgements, like for example, when a consumer of a microservice, it says that, okay, I've received the event, that's an acknowledgement. So something just as simple as that, if it's done cleverly or properly, just this extremely small but nothing fancy thing can prepare a system for better scaling. So I'm not saying that this will scale the system, I'm saying it can prepare the system for better scaling. Just like instead of adding more servers, so like let's say when you have a backend server running, you want to scale it. So instead of just adding more servers, if you just made your code a little bit more efficient, you'd be able to scale your server-side code much better, right? Instead of just adding more compute or more number of servers. So it's the same logic, just add acknowledgement, so which is when the data is received, the components, mostly which are the consumers or consumers in a microservice, which is consumers microservice, can acknowledge receipt, and this ensures both sides are aware. And if you don't receive acknowledge, a retry can be initiated. So if there's no acknowledgement from the side of the consumer, a retry from the producer can be initiated. Checkpointing is another concept which saves the recent state. Just like a game, the game when even if you don't save a game, it saves the last checkpoint. So if you've played Halo, I play Halo a lot. So you have that option to go to the last checkpoint, right? So it's the same. So when you reach at a particular checkpoint and save your progress, and that's where you resume from later. Similarly, we can implement this in event-driven systems. So that's acknowledgement and checkpointing. Now, the other thing is, what you might not realize is to scale an event-driven system efficiently, one very legit way is to try and speed up the processing of events themselves. So not only are you trying to process, trying to scale the system by just, fancy techniques, what if you just process those events faster? Wouldn't that mean that in that less amount of time, you'll be able to process more events. That means the system is scaling because it's able to handle more events. And that's what this means. So for faster processing, we can do three things. One is event ordering, which means you can use timestamps and you can use watermarks. Okay. And I'm sure you understood what you are using timestamps, because watermarks we've just discussed before. Timestamps basically adding like a UTC timestamp and ordering the events in a particular way so that they just become easier to process. You can group the events and you can window the events. So we talked about windowing, where you create a fixed window of events, like let's say from 12 p.m. to 5 p.m. All of these events will be processed in a batch. Session window is when the person logs in, that's a new session, right? So all the events of this session or a number of sessions will be, we'll create a window of those events and we'll process them. And sliding window is just something that keeps changing. It's a bit flexible. So you have session window, you have fixed window, and you have a sliding window. So you can do windowing, you can have grouping, right? So you can group events with different methods. So these are just two methods, but based on fields and shuffle grouping. But you can have like many more different ways of event grouping. There's no limitation here, so there's no hard and fast when it comes to grouping. But windowing, these are the three ways of windowing, and these are two ways of event ordering. Okay, event ordering also you can do a lot more other things. So you can just process events faster with the help of these techniques, like order the events, group the events to process them faster, or create windows and then process them in a batch. The other thing you can do is you can handle events parallelly, and that's called as parallelization. So event systems are usually scaled by parallelization, which is a common technique, and there's which means that time-consuming problems can be broken into smaller subtasks, and they can be executed parallelly so that they don't hold up the system. And if events become too much to handle in the stream, they can be processed parallelly. So that means if a stream starts getting clogged up with events that are very difficult to handle, they can be processed on a different stream parallelly. So we can do this by horizontally by adding parallel stream instances, like I mentioned, or vertically by just adding more resources. So almost like how you do with a EC2 instance on AWS, you can either increase the compute on that same instance, or you can just add one more instance to your cloud and handle the traffic like that. So it's the same thing. So to the same stream vertically, you can add more compute or resources. That's called as vertical scaling, or you just add parallel stream instances. That's called as horizontal scaling. And data parallelism is executing the same task on different. So I've just mentioned what type of parallelism is there. So you can have data parallelism, or you can have task parallelism. So you can have different tasks being executed on parallelly on different streams, or you can have data parallelism where the same task is being executed on different event sets. So you create sets of events and you perform the same task on those event sets but parallelly, and here instead you do different tasks are being executed on the same events but parallelly. Okay, so these are some non-obvious ways in which you can scale events, and then we have also covered scaling microservices registries. But now let's talk about some obvious methods of scaling event systems. So one is partitioning and sharding the events themselves. So you can use partitioning or sharding. If you've learned a little bit of system design, you know what partitioning and sharding are. If you work with databases, again, you know what partitioning and sharding are. It's the same concept here. You can distribute event processing across multiple nodes or clusters, just like you would do in multiple different tables inside a database. So by grouping related events or entities into partitions, you can achieve parallel processing, reduce load on individual nodes, and enhance fault isolation, because now events are being parallelly processed. So you can so that means that on one individual node there's less pressure, or on one individual node there's less load also, because there are multiple nodes to handle the load. And you can also get better fault isolation, because you'll know where the fault is in which particular stream. And then you can have methods to handle back pressure. So you can implement back pressure control to manage spikes in event traffic and prevent system overload. So techniques such as buffering, rate limiting. If you learned a little bit of system design, you already know what buffering, rate limiting are. And implementing queue priorities. Again, these three concepts are very common in system design. Actually, I'm also planning to have a huge system design course, like a free course here online on YouTube. If you want me to create that, do let me know in the comments. I'll be happy to do that. There just needs to be enough demand for something. I'll create it. Can help manage high loads and avoid performance degradation. So techniques like buffering, rate limiting, and implementing queue priorities can help manage high loads and avoid performance degradation. Now, it's difficult for me to cover these three things right now because these are like huge topics on their own, and they're part of system design, and we shouldn't be covering this in microservices or event-driven architecture right now. But yeah, you can Google them out. You can watch videos about them on YouTube in case you're not sure. And then we have idempotent event processing. If you're from a Golang background, and if you've been following my channel, you're probably from a Golang background. You know what idempotency is, where we're ensuring all event consumers are idempotent, meaning they handle duplicate events gracefully. This is crucial in distributed systems where retries are common due to network issues or processing failures, and ensures accurate state without reprocessing errors. So it's just basically handling duplicate events gracefully. Okay. Then you have dynamic scaling and auto scaling policies. So you can use auto scaling based on queue length, processing latency, or CPU memory usage to dynamically adjust resources. This approach helps manage fluctuating workloads efficiently, scaling up during peak times, and just almost like what you would do with the server when you had like a lot of traffic. If you were running an e-commerce website, you would just increase compute, right, on the day of the sale, just exactly like that. You just increase CPU and memory usage for dynamic scaling, basically. And you can also optimize data serialization and deserialization. Now this, you probably know what serialization and deserialization is. That's like, from, let's say if you're working with Golang, from struct data to JSON, from JSON to struct, that's serialization and deserialization. We've worked with, or even if you're from Rust, you probably know, you've used the library, SERDE library, SERDE, which is for serialization and deserialization. Same thing. So here you can choose lightweight, high performance serialization formats. So protobuf, which we use in gRPC all the time, Avro, to reduce event messages size and improve throughput. So avoid unnecessary transformation and ensure serialization is optimized to reduce network and CPU load. Then you can use dedicated clusters for critical event streams. So separate critical and non-critical event streams by assigning them. So you can separate out the critical streams and non-critical event streams. Remember, just some time back, we talked about having different streams for high transaction values and a separate stream for low transaction value, because you can have dedicated clusters for them. Because with this, you're able to isolate high priority processing from low priority events, reducing contention and improving reliability for mission critical workflow. So if there's a high value transaction happening on a website, you can isolate those and you can improve reliability for those. Then you have leverage. We can leverage event batching and aggregation. So batching events to ensure to reduce the frequency. So we have just learned about batch processing just some time back. We're just talking about that here. So we can reduce the frequency of individual messages being sent over the network, which can decrease network latency and improve efficiency. And we can aggregate the related events when possible to minimize the number of messages and processing required per event. So aggregation is basically just grouping of events related, like maybe from a particular order, all the items can be aggregated, stuff like that, whenever possible, and this minimizes the number of messages on the stream. We can implement event sourcing for auditing and replayability. Now, event sourcing is a event-driven architecture pattern, and that will be covered in the next video. That's part of my next video, which is a list I'm maintaining here. And event sourcing is what I'll be covering, as you can see in that video, right? So all of these things will be covered in that video. So just going back to that right now. But still, let's just touch upon it, because it's a huge topic. but let's just touch upon it right now. So we can use event sourcing, let's say something called event sourcing, right? To store the complete history of events for each entity, allowing the system to replay events to recover state or scale to new consumers. This enables easier recovery, state rebuilding, and data consistency across components. Now, you know that this is being used to do all of these things, but you don't know what event sourcing is, and that's completely all right. That's a EDA pattern, and that will take us some time to understand, so I'm not going to cover it right now. Then you have schema registry for versioning and compatibility. So with frequent schema updates, because now we have systems that are scaling really quickly, systems that are evolving, so the schemas keep changing. So when with frequent schema updates, use something called the schema registry. So I've given an example of the Confluent schema registry, and you can manage versioning and compatibility. This enables different versions of services to consume events without causing serialization errors, ensuring smooth scaling. And you can optimize for consumer lag monitoring and recovery. So continuously monitor consumer lag. So consumer lag is basically the consumer microservice or the downstream microservice that's going to consume these events. They can start lagging because of that can lead to back pressure or a slowdown, and then we need to be aware about this slowdown happening so that we can intervene, or we can trigger scaling, like selective scaling of that particular consumer. And for that, we need to continuously monitor it. So you can use consumer groups strategically and rebalance consumers when needed to evenly distribute load and prevent bottlenecks. The next is event deduplication and ordering guarantees. So we can use techniques like unique event IDs or hash-based deduplication to prevent processing duplicate events. So we have to ensure for the consistency of the platform to not process duplicate events. And if we keep processing duplicate events, that leads to data inconsistency, and also it's difficult to scale because it's just not efficient, right? So for cases requiring strict ordering, leverage features like Kafka's lock compaction and ordering guarantees within partitions to maintain sequence integrity. And then you have then you can leverage asynchronous processing with non-blocking I/O. So you can design consumers with non-blocking I/O and asynchronous processing. So use technologies which are non-blocking like Node.js and provide asynchronous processing models like Node.js or Golang, any of these, to improve scalability under high loads, minimizing wait times and making better use of the resources. Okay, so these are the obvious methods to scale up. These are the not so obvious methods to scale up. And this is scaling with service registries. Now the next is some more concepts that I want to cover. I just want to tell you about these concepts, so that's just so that you're aware, because these fall in the same topic, which is event-driven architecture. And then we just have two more small sections to go through, and then we'll be done with the video. So let's go through some these extra concepts. So let's start with deferred execution. Now, just to let you know, the deferred execution and eventual consistency, these two concepts are related because deferred execution is something that takes some time for us to wrap our heads around, especially let's say when you're coming from a REST API background and you've always called REST APIs, you've never worked with events, streams, queues, and all of that, event-driven architecture in general. It's something that you'll find difficult to wrap your head around, because what's happening here is that a microservice is just emitting an event and forgetting about it for some time, in the hopes that there will be a consumer downstream in the stream. There will be a consumer that will pick up this event and process it. And in the beginning, when you're working with a system like this, you get very anxious because you're not sure when the data will come back, or when the data will get processed, or will it ever get processed. And you're putting all of your trust on a technology like Kafka, right? So in the beginning, it can be very, very weird. Like you might find it very weird when you're working with it, but just want to tell you that this is a very normal thing. So it's called as deferred execution. So if you're used to REST-based APIs, the concept of deferred execution can be tricky to comprehend. It's very, very difficult to comprehend. It takes time to get used to. The essence of event-driven architecture is that when you publish an event, you don't wait for a response, and it's a very different way of working compared to what you've already worked with. So the event broker holds or persists the event until all interested consumers accept or receive it. Okay, so event broker like Kafka holding the event until all the interested consumers have accepted or received the event, which may be sometime later. Because we discussed earlier, right, that events can be picked up after some time, or basically after some time. And sometimes you don't have control over after how long the consumers will pick up those events. So acting on the original event may then cause other events to be emitted, which are similarly persisted. So event-driven architecture leads to cascades of events. So what this means is that when the original event gets processed, the other microservices which are processing this event, they will lead to their own events, because for example, the order microservice, order has been placed. This event gets consumed by the payment microservice, which says, okay, payment has been made. Then it goes to the invoicing microservice, which takes this event and creates an invoice and says invoice has been created. Then this event goes to the email microservice, which sends an email and then says, okay, email has been sent, and so on. So like they create their own events. So this creates something called as a cascade of events, which are temporarily and functionally independent of each other. They're all independent of each other, but they're like but there's so many events created, and they're all created in a sequence. So all we know is that event A will at some point cause something to happen. That's all we know. And the execution of the logic consuming event A isn't necessarily instant. Its execution is deferred, as in it happens after some time. So it's just a new concept. Just takes time to get used to, and that's called as deferred execution. Now, eventual consistency is kind of related. So if you've if you've trained in system design, I say train in because it's not something that you learn. It's like you train, where you create multiple different systems, you design multiple systems, and it takes practice, right? So it's training in system design. So when you train, if you've trained system design, then you would know about consistency and eventual consistency. And with event-driven architectures, we have eventual consistency, where we don't really have control over consistency in the beginning, but we know that eventually something will be consistent. So we can emit an event, and that event leads to some change in the database somewhere. And we know that it might not happen now, but eventually things will be consistent. So that's why it follows on the idea of the deferred execution, where you expect something to happen later, but you don't wait for it. And that's the idea of eventual consistency. Since you don't know when an event will be consumed, and you're not waiting for confirmation, you can't say with certainty that a given database has fully caught up with everything that needs to happen to it. And you don't know what will be the case. So if you have multiple stateful entities like databases, MDM, and ERPs, you can't say they will have exactly the same state. You can't assume they're consistent. So however, for a given object, we know that it will become consistent eventually much later on. And then you have something called the event mesh. So what is an event mesh? Event mesh is something that's created and enabled through a network of interconnected event brokers. It's a configurable and dynamic infrastructure layer for distributing events amongst decoupled applications, cloud services, and devices by dynamically routing events to any application, no matter where these applications are deployed in the world, in any cloud or premises or IoT environment. Technically speaking, an event mesh is a network of interconnected event brokers. So that's it. So event mesh, you will, the only reason I'm covering this is because whenever you'll open up a video on YouTube, you might hear this term being thrown about a lot, event mesh, and this might confuse you. It's just multiple event brokers. That's just it, an event mesh. That's all it is. Now, events scheduling. Now, events, they don't, like I know we covered like a very narrow part of events where they just are being thrown or emitted onto the stream, and then they're just being processed. But because when we'll deep dive into Kafka, we'll know more, and one of those things would be event scheduling, that you can schedule events. So event scheduling in event-driven architecture involves controlling the timing of events. You can emit an event after some time also, ensuring they are emitted or processed at specific times. This could mean delaying the emission of events until certain conditions are met, or scheduling them based on predefined criteria. For example, in a stock trading application, you might schedule price checking events to trigger at the end of each trading day. So you can schedule that this event will happen at this particular point of time in a stock trading application. This is an example. This helps in orchestrating events that need to happen periodically or according to business logic. And scheduling can be done through cron jobs or job scheduling tools like COTS scheduler, or by using message brokers with delay mechanisms. Okay, so pretty straightforward. Let's talk about the next topic, which is deterministic event processing. And it ensures that events are processed in a predictable and consistent way, producing the same results every time given the same sets of events. And that's what we want, right? We want, if an event is emitted today, so there will be same result after processing it. And if the result, that same event is emitted 5 days from now, we want the same result to be generated after processing that event. So this concept is critical in systems where consistency is a priority, of course, especially in distributed systems where events can arrive in different orders. So if you have a distributed system, now distributed system, this word has been written very lightly here. If you don't know how distributed systems work, don't worry. I will in the future create a video on distributed systems as well. It's a huge topic. And in case you want to learn distributed systems, to drop a comment. Like if you want to learn the concepts of distributed systems, to drop a comment. I'll make a video just like this. It'll take like 4 hours. There'll be like a 4-hour video as well. So then with deterministic event processing, you have network latency, concurrent event processing, and distributed environments can make it challenging to ensure events are processed in a deterministic order. So we've understood what deterministic event processing is, but these things, right, latency in the network, events being processed concurrently, and distributed environments make it very difficult. But solutions include using sequence numbers in events, ordering mechanisms in event stores like Kafka's partitions with ordered offsets, and leveraging idempotent processing to avoid discrepancy. So these are the solutions, and Kafka does that really well. So with recent technologies, you're able to get deterministic event processing. It's already built in, but it's just good to know that you need this when you have a distributed system, especially where events can arrive in different orders at different times. Okay, so when an event gets late, it's not processed at the right time. How do you handle it? So these events that arrive after their expected time due to network delays or system failure, like let's say the stream went down for some time, or one of the emitter of the events that goes down for some time, or any other reasons, handling these late events effectively is crucial to maintaining data consistency, especially in real-time systems like streaming platforms. So how do you handle that? You handle that with the help of one is watermarks. So watermarks help to define the point in time after which late events are ignored or processed differently. So you can define that after this timestamp, handle these events differently. You can use windows. We've talked about windows already. Using event windows can accommodate late events with a certain within a certain period, aggregating results based on event timestamps rather than arrival time. So instead of checking when the event arrived, you can check when the event was emitted, because that will be the event timestamp. So you can aggregate results based on that instead of the arrival time of the event. And buffering and retry. So your systems can also buffer incoming data temporarily to wait for late events, though this may impact real-time processing. So if you have a mission-critical system which has real-time processing, which requires real-time processing like stock trading platforms, then it's a problem, because then if you're waiting for late events, buffering incoming data temporarily, this will impact real-time processing. Then you have these two concepts: pre-processing of events or processing the events in real time, right? So this involves whether to handle events in real time, like which is near instantaneous processing, or reprocess them later, which is common. Sorry, it's reprocessing, not pre-processing. Reprocessing them later, which is common when dealing with large data sets or correcting errors. Now there is something called as pre-processing of events as well, but let's not cover that because that'll just increase the complexity of this video even further. But that's something that we do in real-time systems to ensure that during real time, if things do get delayed, if the events are much bigger, it doesn't lead to latency. So real-time processing is used in applications like fraud detection, where immediate action is required. Like somebody is trying to swipe a card online, and you want to check if this transaction is fraudulent or not. It involves processing events as they arrive, which is more resource intensive but provides faster feedback. So it's resource intensive, but it provides faster feedback. Reprocessing is useful for batch-oriented systems or in cases where historical data needs to be reprocessed after a code update. For example, reprocessing is common in analytics pipelines where historical data needs recalculation. So anywhere where recalculation is required, reprocessing is required, that's reprocessing. So trade-off. Real-time processing ensures low latency but may miss certain details if late events are dropped, while reprocessing can ensure accuracy but at the cost of time and computational resources. So when you're reprocessing something, it'll take more computational resources and it'll take more time, but it will ensure accuracy, whereas real-time processing ensures low latency because the events are processed in near real time, but many certain details are missed if late events are dropped. Okay. So these were some of the concepts I wanted to cover as part of event-driven architecture. And now that we are done, we just covered scaling with service registries, scaling an event-driven architecture with some non-conventional and some conventional techniques, and some important concepts that I couldn't cover before. So we just covered it right now. And now we'll just go over these considerations and something called as hexagonal architecture. Now, hexagonal architecture is, I'm going to just touch upon it like from a 10,000 feet perspective. I'm not going to go into a lot of detail because this requires its own 1 hour video if I had to explain it properly. And there are 1 hour videos of this on YouTube. So if you want to go in detail, you can check it out. But I will just touch upon it from like a very, very 10,000 feet perspective-ish. From a 10,000 feet perspective, basically. And then we'll just talk about failure and resilience in microservices and challenges with microservices and all that, and then we can be done. Okay, so some considerations. Now, the thing is, we know that event-driven architecture is amazing, and we know that async microservices are the way to go. But you'd still want to use synchronous microservices in some instances, right? Because you might assume that are sync microservices dead? Are they not at all useful? And if you remember, I had mentioned that even if you have asynchronous microservices, which is like 90% of everything is async in your microservices architecture, even then 10% would be synchronous, right? Like there will be some communications that are synchronous, and that's completely all right, but it will still be termed as asynchronous microservice architecture. Synchronous is something that's like completely synchronous microservice architecture. And you might think it's now that we've learned so much about async microservices that sync is like, dinosaurs use sync and you don't need them anymore, but that's not true. There are some situations where you might need sync microservices as well. So let's talk about where you'd want to use them and their drawbacks, okay? And before that, let's talk about some microservices considerations. So what's the meaning of considerations? Consideration is like the things that you want to be thinking about when you're building your microservices. So the first thing that I usually think about is my event brokers. Are you using Kafka, or are you using whichever broker you're using? So like whichever technology you're using, it needs to be scalable, needs to be durable, needs to be highly available and highly performant, right? That particular technology, and also the brokers in that technology need to be all of this, because if they're not scalable, durable, highly available and performant, why are you using event-driven architecture in the first place? And I would be thinking about the single writer principle, where my order, my events would be, the order of event should be emitted only by order microservice. So for example, if I'm order related events will only be emitted by my order microservice, and user related events would only be emitted by my user microservice, okay? And then I will have to think about my event storage and serving. So partitioning to store those events, right? Partitioning is the same concept as databases. You're able to store more, more data in the database with the help of partitioning. And the events need to be strictly ordered. They need to be immutable. You can't just keep changing the state of the events after they've been stored. Indexing of the events, infinite retention. So would you want to have infinite retention, or do you want to have some amount of clearing the events after some time? Not from the stream itself, but the place where they're getting stored permanently. That's where you want to think about retention. And replayability. So how easy will it be to replay the events, or is there even the capability to replay the events? So I'll think about that, and I'll think about these additional factors, which is what kind of tooling does it support, this technology that I'm choosing, or what kind of hosted services are available. So for example, with Kafka, there are like multiple options that are available, even some fully managed ones that are available. And then the client libraries and processing frameworks that are available to me, as an additional factor. So for example, with Node.js, you have Molecular. With Golang, you have GoKit. And then community support, then long-term and tiered storage, and then whatever your firm is already using. So this is one factor for me. If my firm is already using some technology, I'll use that technology for building the microservices. I won't transition to a new technology. And I would also look at the community support. If it's an open source technology, it needs to have great community, and I'll check out the long-term and tiered storage options as well. And then performance consideration. This is the most important one. That's why this is actually, this one shouldn't be in bold, but these are additional factors. This one should be in bold, and here this one would be in bold, and here this should be in bold. So performance condition is the most important thing for me, because we are looking at streaming technologies, right? So in my microservices, I'll ensure schema compatibility between the microservices. I'll ensure that data, capturing data change using triggers, and syncing event data to data stores, and isolating internal data models. So I'll be thinking about performance consideration. So that's what I'll be thinking about when picking up event-driven architecture for my microservices. Now for my synchronous microservices, these are basically my API-based request and response fulfillment synchronous microservices. And these are the drawbacks. This is the reason why we don't go for synchronous microservices. So once you know that why you won't go for these, like in which scenarios you don't go for the synchronous microservices, you know for a fact that for those scenarios you will go for asynchronous microservices. Okay, and so let's look at that. So you have point-to-point coupling. The problem with synchronous microservices is that they rely on other services to help them perform their business tasks. Those services in turn have their own dependent services, which have their own dependent services, and so on. So all these services have their own dependent services, and so on. And this can lead to excessive fan out and difficulty in tracing which services are responsible for fulfilling which parts of the business logic. And that only makes sense. Like everything is synchronous, everything is tightly coupled. Then this microservice is going to send some data to this microservice, and this microservice is going to request data from some microservice, and everything is like tightly coupled and dependent on each other, and this leads to a lot of problem. And the scaling itself is dependent, because the ability to scale up your own service depends on the ability of all dependent services to scale up as well, and is directly related to the degree of communications fan out. Implementation technologies can be a bottleneck on scalability. And difficult service failure handling. This is a big challenge with synchronous microservices, because if a dependent service is down, then decisions must be made about how to handle the exception, deciding how to handle the outages, when to retry, when to fail, and how to recover to ensure data consistency becomes increasingly difficult the more services there are within the ecosystem. And API versioning and dependency management is a problem. So multiple API definitions and service versions will often need to exist at the same time. It is not always possible or desirable to force clients to upgrade to the newest API. This can add a lot of complexity in orchestrating API change requests across multiple services, especially if they're accompanied by changes to the underlying data structures. Okay, so that's API versioning and dependency management is a problem. Difficult service failure handling is a problem. Scaling is dependent, and everything is very tightly coupled. So all of these are the drawbacks. And then you have data access tied to implementation. So synchronous microservices have all the same problems as traditional services when it comes to accessing external data. Although there are service design strategies for mitigating the need to access external data, microservices will often still need to access commonly used data from other services. This puts the onus of data access and scalability back on the implementation communication structure. And not only that, but testing is also a problem. So integration testing can be difficult, as each service requires fully operational dependents, which require their own dependencies in turn. So these are the drawbacks that we have quickly run through of synchronous microservices. Now let's look at quickly the async or event-driven microservices. They're event-driven, they're extremely scalable, they're highly efficient, they're maintainable, and there are some drawbacks, but they have granularity, they have technological flexibility, business requirement flexibility, loosely coupled. The spelling of loosely is wrong. And you have continuous delivery support and high testability. And so it's event-driven, of course, because instead of waiting for request and response, you get events, and you can trigger stuff based on that. I don't know why they're 2 different points. And they're extremely scalable because no limit to the request and response. It's low latency, and individual services can be scaled up and down as needed. So these are all the big benefits of using event-driven services. They're highly efficient because low number of requests are required, easily maintainable because services expect particular events only, services emit particular events only, and makes the services extremely simple to fix. Some drawbacks. I'll come back to these drawbacks, but let's talk about some more benefits. Granularity. So services map neatly to bounded context and can be easily written when business requirements change. Then you have technological flexibility. So you can use different languages, different technologies, all of that good stuff. Business requirement flexibility. So we have granular microservices that we just mentioned here because we are able to change context and rewrite business requirements very easily. There are fewer cross-team dependencies compared to large services, and the organization can react more quickly to changes in business requirements that would otherwise be impeded by barriers to data access. They're loosely coupled because event-driven microservices are coupled on domain data and not on a specific domain data is all the subdomain stuff that we talked about earlier, not on a specific implementation API. That's how they're coupled. So data schemas can be used to greatly improve how data changes are managed. And continuous delivery support. So it's easy to ship a small modular microservice and roll it back if needed. And they also have high testability, which is something that's not there in synchronous microservices. So microservices tend to have fewer dependencies than large monoliths, making it easier to mock out the required testing endpoints and ensure proper coding. So that's this is the benefits with asynchronous event-driven microservices. So async microservices, I think, is the right word for you. Okay, and now let's talk about the drawbacks. They're very, very resource intensive. Now, we're talking about some drawbacks here, but then there are way more drawbacks that we are going to discuss in this section because this doesn't do justice. I've just put some drawbacks here because it shouldn't look like there are no drawbacks in async, and because we have talked about so many drawbacks of sync microservices. So I've just put them here just to keep the balance there, but we'll talk about a lot more problems in just the next section. So drawbacks are that they're very resource intensive, they're super complex, very difficult to architect, and the failure identification can be a big challenge. Sometimes centralized due to mainstreams can be a security threat. So if you're using streams, but like, and many of the microservices are linked to those streams, that can be a security threat. So this is a great way to organize your microservices, which is called the Hexagonal Architecture. And I have, now this is a huge, huge topic, and somebody called Alistair Cockburn, he's the one who popularized this. And I have given you the link of the person, his website here. So that's the right resource to go and read. There is no way I will do justice to this topic, but I'm just going to try to explain it very quickly anyways. But this, like I said, is a huge, huge topic, requires a lot, like a much longer video just for itself. But then let's just quickly talk about it. So we'll go over this quickly in about 5 to 10 minutes. I think the best representation is this diagram. So there is something called as the port. There's something called as the adapter. And adapters are the bridges, and ports are what allow applications to communicate with the outside world and with the rest of the business logic. And then the application is what's the main part in a hexagonal architecture. So the hexagonal architecture has the application, port, and adapters. These are the 3 things you need to know. And there are 2 different types of ports. One is the incoming port and the inbound port and the outbound port. So we'll learn about that as well. Right? And then there's something called as the driving side and the driven side. Okay, so I'll just repeat. There are ports which help the application talk to the outside world. There are adapters which connect to different technologies. There's the application itself which needs to process some business logic. Then there's the driving side and the driven side. Now let's look at all the points that I've written out for you guys. So just a second, sorry, I'll just move my mic. Okay. So you have the hexagonal architecture, which is also referred to as the ports and adapters architecture. It's an architectural pattern that allows input by users or external systems to arrive into the application at a port. So it allows the information to arrive at a port of the application. Okay, that's what we discussed. And this happens via an adapter. So arrive into the application at a port via an adapter. Okay, the information arrives to the port via an adapter. And whenever the information goes out, Whenever the information goes out, that's also going to happen with the help of an adapter. So that, I think that's written somewhere. And allows the output to be sent out from the application through a port, to an adapter. This creates an abstraction layer that protects the core of an application, isolates it from external and somehow irrelevant tools and technology. So you don't have to make changes in the applications again and again. Whenever the information has to come into the application, it comes via an adapter to a port. Information gets processed, and it can be sent out via a port, through the port via adapters again. So that's the driving side, and that's the driven side. That's all that's happening. That's all that the statement says. So even if you just read the statement, and even if you just take this away, if this is your only takeaway from hexagonal architecture, that's good enough. So we can see a port as a technology agnostic entry point. So the port, it doesn't care what technology the port is built in. It just is a a mechanism the application talks to the outside world with. It determines the interface. It's just the interface which, or an abstraction or an interface, which will allow foreign actors to communicate with the application, regardless of who or what will implement the said interface. So it doesn't matter who or what is implementing the said interface. The port is an abstraction that allows the application to talk to the outside world. That's about it. A port can be also called as a gateway, which provided by the core logic. It allows the entry or exiting of data to and from the application. So it allows the entry and exiting of data to and from the application. And there are two types of ports. So one is an inbound port, which is responsible for how the data comes in. Outbound is the data goes out. That's what it is. And you can see the business logic, which is the application here, and you have these multiple adapters and ports. Now, an adapter, let's talk about the adapter, will initiate the interaction with the application through a port. Okay, yeah, that's what we can see. It initiates the interaction with the port using a specific technology. For example, a REST controller would represent an adapter that allows a client to communicate with the application. There can be many types of adapters for any single port. So any port can have different types of adapters. Could be a REST adapter, could be a GraphQL adapter, could be a gRPC adapter, it doesn't matter. An adapter transforms one interface into another, creating a bridge between the application and the service that it needs. In hexagonal architecture, all communication between the primary, which use systems to achieve a particular goal, and secondary actors. So primary actors and secondary actors, which system uses to achieve primary actors' goals. And application port is done with the help of adapters. So yeah, so we have defined ports and adapters. So the primary or driving adapters. So you have primary and secondary adapters. So you have the primary adapters, which are the driving adapters, which is on the left side. And the secondary adapters, which are the driven adapters, which are on the right side. So the primary, or you can see here also, the primary and the secondary. So the primary or driving adapters represent the UI. It is a piece of code between the user and the core logic. They're called driving adapters because they drive the application, start actions in the core application. They start actions in the core application. Examples of primary adapters are API controllers, web controllers, or views. The secondary or driven adapters represent the connection to backend databases, external libraries, mail APIs, etc. So this data is coming from the UI. That's why we show a human being here. That's what we were saying here. That's the driving adapter. And this one is the database. This one is going to the database. So that's what we can see here. It's going to the database, which is happening in the backend. So user is driving the application, and the database is getting driven from the application. That's just what's happening, okay? You can see here, email being sent, that's the driven one, and driving the API controllers or UI are driving the core business logic. So now we understand everything about the port and adapter. Let's talk about, and the driving side and the driven side, inbound adapters, inbound port, outbound port, all of that. We understand all of that. Let's talk about the application. Application, as you know, is the core of the system, which has the business logic. So it contains the application services, which orchestrate the functionality or the use cases. It also contains the domain model, which is the business logic embedded in aggregates, entities, and value objects. The application is represented by a hexagon, which receives commands or queries from the ports and sends requests out to the external actors like databases via the ports as well. The first key concept of this architecture is to keep all the business models and logic in one place, and the second concept, each hexagon should be independent. So the first concept is that all the logic will be in these hexagons. And the second logic is that, the second key concept is that all of these applications are independent. So the driving or primary actors are the ones that initiate the interaction and are always depicted on the left side. So these are the primary ones depicted on the left side. And so we've talked about a driving adapter. And secondary, the secondary actors are the ones that are kicked into behavior by the application. For example, a database adapter. So this one, the driven side on the right side. So we've talked about both of these. Now, ports will be, most of the time, depending on the language you choose, represented as interfaces in the code. Okay, so they will be, the ports will be interfaces in the code because they will have level of abstraction. They would be independent of the language. And driving adapters will use a port, and an application service will implement the interface defined by the port. In this case, both the ports interface and implementation are inside the hexagon. Okay. And driven adapters will implement the port and an application service it will use. In this case, the port is inside the hexagon, but the implementation is in the adapter, therefore outside the hexagon. And then there are many advantages of using ports and adapters architecture. One of them is to be able to completely isolate your application logic and domain logic in a fully testable way. So all the application and domain logic in the application hexagon is fully testable. And port and adapters, all of that can be kept separately. So it lets you design all your systems interfaces by purpose rather than by technology. So you don't have to worry about technology because that's being handled at the port and adapter side. You can focus on the business logic and making it easier for your application's tech stack to evolve with time. If you need to change the persistence layer, go for it. If you need to allow your app to be called by Slack bots instead of humans, you can do it easily. So all you need to do is implement new adapters. So these adapters can be changed. So these can be REST API or GraphQL or gRPC, but it can also be adapters for other technologies like Slack or any other tool that's calling, like Zapier, any other tool that's calling the information. So this is just a very modern way of organizing your applications and your microservices. It's a great architecture to follow, and this just makes it easier for your application to talk to others. So I'll just quickly revise or reiterate everything. So you have the application, you have an application, and you don't want to worry about changing the technology in the application depending on what kind of systems you want the application to interact with. So you might want your application to interact with emails, with Discord, with Slack, with even AWS. You want some interactions to happen on AWS, or maybe some events to be created on Google Calendar. And you don't want to worry about writing all of that logic inside the application. So you create interfaces called the ports, which are able to perform some actions inside the application. And the ports get information from the adapter. Now there are two types of ports, inbound, outbound, and two types of adapters, the driving side and the driven side. The driving side adapters take information from the user or the UI or even API controllers and pass it to the inbound port. The application takes some action, processes these events, processes that information because it has the business logic capability. Then it creates these events or some actions outside, like in the database, which is the driven side. So these are the driven side adapters, and this port is called the outbound port. All the logic is written in the adapter and the ports. The application doesn't have to worry. So the port logic you'll find inside the application in the code. These are the interfaces, but the adapter code you'll find separately. And this makes you focus. Enables you to focus only on the business logic, and you don't have to worry about technological implementations too much, and your architecture can evolve very fast, very easily. Now let's talk about failure and resilience. So why do you want to focus on failure and resilience? Because your system needs to be resilient because it can enhance customer experience. So resilient applications ensure functioning and serving users without significant disruptions. So you don't want your system to get disrupted all the time. So it ensures a seamless user experience. You also get business continuity. So if you have an e-commerce platform running and you want to keep accepting orders all the time, you want to handle graceful failures gracefully. Resilient applications ensure business continuity and minimize the impact of disruptions on critical operations. And you also want to ensure stability and reliability. So resilient systems are better equipped to recover from failures, reducing downtime and enhancing overall stability. So that's why you want to focus on failure resilience. And now, so we've understood the why of failure resilience. Let's understand the how, or how do we ensure that our system or our microservices are more resilient. Just before that, just want to quickly remind you about the ultimate coming up, the ultimate Golang bootcamp that's coming up. I'm covering all of these topics. If you want a discount, the link for the Google form is in the description of this video. So let's go back. So how? So the first thing you can do is you can design for failure. And how do you design for failure? You adopt resilience patterns. So you adopt resilience patterns like circuit breaker, retry, bulkhead, and timeout patterns. Now, these 4 things, right? Circuit breaker, retry, bulkhead, and timeout. These are like really serious topics, and they are part of the next video that I'm going to do. So you have circuit breaker and bulkhead and retry, fallback. You have all of that here. So all of that comes under resilient patterns. And then you have the decentralization. So avoid having a single point of failure by decentralizing components. Distribute functionality across multiple servers, data centers, or even geographical locations to reduce the impact of failure. So you can try out multiple geographical locations, multiple data centers, and you can have functionality across multiple servers. That's what you do when you start scaling. You can have some redundancy and you can have some replication. So you can introduce redundancy at various levels of the system to ensure that if one component fails, another can take over. This can include redundant servers, databases, and network paths. So these 2 topics, decentralization, redundancy, and replication, these are system design concepts. And if I create a system design video in the future, like a massive bootcamp, I will talk about these. Then you have, or you can just learn more about them in case you don't know how these work. And fault isolation. So you can design system in a way that isolates faults to prevent them from cascading throughout the entire system. And isolating failures help contain the impact and allow the rest of the system to continue functioning easily. And then you also want to have automated recovery. So recovery, whenever systems fail, you want the system to come back online automatically. This includes automated backups, which is something you must be doing if you're building software right now. Configuration management and deployment rollback procedures. So if something wrong was deployed, you can just roll it back automatically. Graceful shutdown is something that I've shown in my Golang videos a lot of times. Design systems that to gracefully degrade in case of failures. When certain components fail, the system should still provide basic functionality rather than completely breaking apart. And you can have proactive monitoring and alerting. So the better your alerting and monitoring, the better, the less chances for failure, because with monitoring, basically you're able to see what issues can occur in the future, depending on which systems are taking a lot of load. And alerting basically means you're getting a message, you're getting an email, you're getting a Slack message, notification, Discord message, all of that. So you can adopt comprehensive monitoring tools to continuously track the health and performance of the system. So you can design alerts that notify the respective stakeholders when issues are detected, enabling prompt responses to failures. You can adopt containerization and orchestration. So adopting containerization platforms like Docker and orchestration tools like Kubernetes to deploy and manage your applications and microservices. Containers provide isolation and consistency, while orchestration simplifies the deployment, scaling, and monitoring of microservices. Now we have covered orchestration and containerization, which is Docker and Kubernetes, a little bit in this video, but it's just going to get covered a lot more in detail in the next video. We'll have a deep dive into containerization and orchestration for event-driven systems and for microservices, okay? Because that's a huge topic again on its own. Adopting chaos engineering. So it's a discipline that involves intentionally introducing control and well-monitored instances of failure. It's basically trying to fail your own system, trying to introduce failures to see how the entire system reacts, to identify weaknesses and vulnerabilities. The primary goal of chaos engineering is to proactively discover and address potential issues before they can lead to widespread outages or disruption. So you don't want the entire system to go down and have a widespread outage or disruption. So you introduce controlled and well-monitored failures, and you can that ways you can easily test the limits of your system. Automated deployments and rollbacks. So you can implement robust CI/CD pipelines to automate the deployment rollback of microservices along with automated testing. This ensures consistent and reliable deployment processes, reduces manual errors, and enables rapid recovery in case of failure. And you can also learn, experiment, adapt, and iterate. So you can adopt a mindset of continuous learning and improvement. Regularly review and update the system architecture and recovery processes based on evolving requirements. So it's basically saying that you ensure that you're reviewing your current system and ensuring that you keep fixing stuff and introducing new stuff that you think will lead to a more resilient software. Now the thing is, microservices are not the perfect solution. They're not the silver bullet. There are like many problems, and we'll go through all the problems now. Okay, so what are the challenges with microservices? One is increased complexity. As you would have guessed by now, since there are so many microservices now, It's a little more difficult to maintain. And yeah, just coordination and managing becomes more difficult. Many services because all of these have independent life cycles, independent deployments and scaling needs, so it becomes a little more complex. This complexity can make development, testing and debugging more challenging, as developers must understand how different services interact and depend on each other. Then you have data management and consistency issues. So ensuring data consistency across multiple services is difficult, especially since each service might have its own database, a practice known as database per service. So because each service has their own database, so it's just because of database per service pattern, so it just becomes more difficult to ensure consistency. And distributed data management requires handling issues like eventual consistency. We've discussed this already. Distributed transactions, this is a completely, it's a huge topic, which is part of the Saga pattern, and we'll talk about that in the next video, like I mentioned. And data duplication, which can be difficult to implement correctly. So distributed data management can be difficult to manage and implement. Then you have the inter-service communication and latency. So microservices need to communicate over the network, which introduces latency. So we've talked, we had like a whole section about how microservices interact with each other. So that was like the inter-service communication part. And this leads to latency, as you know, especially when services are in different locations or data centers. And communication between services often relies on APIs, which can be REST and gRPC, and messaging, which is Kafka and RabbitMQ, which can fail, requiring additional handling for retries, fallbacks, and circuit breakers to ensure resilience. But in addition to that, just setting up the communication itself is so complex, right? And setting up Kafka and RabbitMQ, that's a whole new way of working, a new different level of complexity. So it's not very straightforward. So deployment complexity also is a big problem, because managing and deploying multiple services independently requires advanced deployment strategies like blue-green or canary deployments. In case you don't know this, don't worry. In the next video, I'll cover deployments as well. And container orchestration, e.g. Kubernetes. So CI/CD pipelines need to handle complex workflows, ensuring each service is tested, deployed, and compatible with other services. And then there's also a problem with observability and monitoring, because you have to have distributed tracing. And how do you collect logs of different microservices at the same time, because multiple services are running independently, and tracking issues or debugging failures is more difficult. Observability requires comprehensive logging from all of the different servers, all of the different containers, and all of that stuff, distributed tracing and monitoring of each of these services. So monitoring tools like Prometheus, Grafana, and tracing tools like Jaeger and Zipkin are essential, but they also add additional setup and maintenance overhead, because you have to ensure all these servers are also running, they're working perfectly fine. Then you want to handle distributed failures. So in a microservices architecture, failure in one service can cascade to others, affecting the entire system's stability. So implementing resiliency patterns like circuit breakers, retries, and fallbacks across multiple services is challenging and often requires extensive error handling to avoid cascading failures. Then we also have increased resource utilization costs. So each microservice often runs as a separate container or instance, which can increase resource usage, CPU and memory, and costs, especially for small services. So managing and scaling multiple instances or services independently adds a lot of overheads, as well as additional costs for infrastructure, networking, monitoring, and orchestration tools. So that's what, obviously, if you're using multiple microservices, you just need more servers, you just need more containers. So resource utilization goes up. Testing all of these different microservices can also be a problem, because of interdependencies between services. So even though services, they are quite independent, but they still have a little bit of interdependence between them. They're decoupled, but they still need data from each other. So tests need to cover individual services, which are unit tests, service integration, and end-to-end workflows across multiple services. So running automated tests in a distributed environment can be slow and requires additional tools to simulate the network latency, faults, and dependencies. The other thing is network security, because now your microservices are talking to each other for so much more. So now there are chances of network security failure. So because microservices expose many endpoints that need to be secured individually, making the system more vulnerable to attacks. The more number of endpoints, the more network communications, the more surface area that needs to be protected. So security practices like mutual TLS, API gateways, and service mesh are necessary to protect communication between services, but these add a lot of complexity and require ongoing management and maintenance. Service, versioning, and backward compatibility. So each microservice may evolve independently, which means developers must handle versioning carefully to avoid breaking changes that affect independent services. So since each microservice have their own life cycle, they're being developed at their own speed, they will evolve independently, and developers must handle versioning carefully. So ensuring backward compatibility, which basically means that everything is also compatible with all the previous features, and managing multiple versions of APIs or data schemas becomes a significant challenge, especially as the number of services grows. So the more the number of services, the more difficult it becomes to manage the data schemas or the versions of the APIs. Then you have cross-cutting concerns and code duplications. Cross-cutting concerns like authentication, authorization, logging, and configuration management need to be implemented across multiple services, because you can't just have them at one microservice. So all of the data that's being accessed from multiple microservices, the requests need to be authenticated or authorized for that particular service or not. So which can lead to code duplication or the need for shared libraries. So without a centralized approach, it's easy to introduce inconsistencies, making maintenance and updates difficult across the entire system. Then you have orchestration and service discovery. So as microservices scale, managing communication between services requires a mechanism for service discovery. So we've talked about service registry already. That's what helps with the location of the IP and port. So tools like Console, which is a service registry, Eureka, and Kubernetes provide service discovery, but they require configuration management and adding, which now if you start using Kubernetes in your architecture, in your infrastructure, it just adds a huge layer of complexity, because you can't just manage Kubernetes very simply, right? It's a big problem. Then you have team coordination and communication. So microservices work best with cross-functional teams that manage specific services. As the number of services grows, so there's a need for communication and coordinating amongst teams. So if your teams don't want to work together, if they have some issues, it's going to be very difficult, because having microservices requires teams to work together to share and access data from the other microservices. So changes in one service can impact others, leading to dependencies that need to be managed through effective communication, versioning, and documentation. Changes here in this microservice will lead to will have some ripple effects on other microservices. So you need to manage that with the help of communication, versioning, and documentation. Cultural shift and learning curve. That's a big point, because now your DevOps teams need to learn new tools, patterns, and practices. They need to work with Kubernetes and Prometheus and all of that, and distributed tracing. So moving from a monolith architecture to microservices requires a shift in mindset, and may require developers, operations, and DevOps. So developers now need to work in a very different way. Ops guys and DevOps teams need to work in very different ways now, because concepts like CI/CD, IaaC, and DevOps culture are essential to microservices, which can require extensive training and adjustment for teams. So these are all the challenges that I've tried to cover, like as many challenges as possible. So you wouldn't want to just always go with microservices. But since there are so many challenges with microservices, and modular architecture is also a problem, is there something in between? Yes, there's something in between called the modular monolith. So when you transition from monolith to microservices, there's something in between called modular monolith. So what happens is, you have your application, you have different modules. So you can divide the application into different modules, and that becomes like a modular monolith. And when you look at these different modules, like the UI, application, domain, and infrastructure, these are 4 different components. And you have these modules, which are like the vertical slices. So across these 4 different components, you can have like feature number 1, feature number 2, feature number 3. So to build feature number 1, you have to build the UI components for it. You have to build the backend application side, domain side, and the infra side to deploy it. So you have these different features. So this is how modular monoliths can be represented, or you can represent them like this, which is an e-commerce app with modular monolith architecture. So you have product, basket, or your cart, and the order, and they have ability to list products, which has the UI, business logic, and data access, and add to the basket, which also has the UI, business logic, and data access. So these are basically the same thing represented, where the vertical slice has just been renamed to the name of the feature. Okay. So what are the benefits of using modular monolith? So here you can encapsulate the business logic. So the main benefit of the modular monolith is that the business logic is encapsulated in the modules, and it enables high reusability, while data remains consistent and communication patterns remain simple. You don't have to have like really complex communication patterns like you would have in microservices. The code is reusable code, and easy to refactor. So the code from one module to another module, or one feature to another feature, very easily shareable and reusable. So for large development teams, developing modular components of an application will increase reusability. So modular components can be reused that can help teams establish a single source of truth. and this will lead to faster and more consistent development. So also changing a module has less or no effect on other modules. Then you can also have better organized dependencies. So with modular monolith architectures, application dependencies will be more organized and visible. This will help developers to easily assess which parts of the application requires which dependencies. And the other benefits of modular monolith is that they're less complex. Of course, they're less complex than microservices architecture. And so it's easier to manage a modular monolith rather than hundreds of microservices, because modular monolith comes with basic underlying infrastructure and low operational costs. It can be better for small teams. So it's less complex to manage, maintain, and upgrade. So all of these things are really simple. So these are the different benefits of having modular monolith. So what are the challenges of modular monolith? Is it the silver bullet? I don't think so, because you have problem with diversifying technologies, because now everything is very tightly coupled. So even if you have these features and modules and all of that, they're all very, very tightly coupled. So modular monoliths don't provide all of the benefits of microservices. If you need to diversify technology, for example, when you use Golang or Rust and some other module, you can't do that because you can't have different language choices. You can't do it with modular monolith architecture. These types of polyglot technology stacks can't be used with modular monolith architecture. Okay, and can't scale and deploy independently. So you have to scale and deploy the entire project at the same time. You can't do this independently. And since the application is a single unit, it can't be scaled separately, and it can be scaled separately or deploy independently. It can be scaled separately or deployed independently like microservices. And this kind of application has to move, I made some mistake, some English is mistake somewhere, and I'm not able to figure out what I'm. So basically due to reaching of scalability limits and also performance issues. So when you have reached scalability and performance issues, you can't deploy them independently. I think I'll just remove that statement out because it's very, very confusing to me as well. So I'll just remove it. I think this is good enough, which is, since the application is a single unit, can't be scaled separately or deployed independently like microservices. And when do you want to use modular monolith? You want to use that when your project is small and needs super strict consistency. So if you have a bank, banking project where you're working on a bank account and needs super strict consistency, and that's all the project really does, doesn't do anything else other than transactions, so you're better off using modular monoliths. And if you want to be working with modernization and intermediate stages, so when you're running legacy systems currently and want to modernize and adopt microservices but don't want sudden inconsistency and data integrity issues, best is to refactor to a modular monolith first for a while and get the project ready for microservices rather than directly jumping from monolith to microservice. So you don't want to jump directly from monolith to microservices. If you're in a legacy system, you're better off first transitioning to a modular monolith and then preparing your system to transition to microservices so that you don't get a sudden jerk in your system. So it is a great intermediate stage, before you jump off to microservices. And when so the other reason to use, like when the other instance you can use modular monolith is that if it's a new project or a greenfield project. Greenfield project is something that you're building, maybe you're building a project from scratch. That's a greenfield project. So modular monolith will allow you to learn your domain and pivot your architecture much faster, because let's say you are building a new product and you don't know how the market is shifting, and because you want to learn actively from users, you want to build based on what the users are saying. It'll help you learn much faster and pivot your architecture much faster. We don't have to worry about things like Kubernetes and a service mesh at day one. You don't have the increased complexity, so you can evolve into that. So your deployment topology will be drastically simplified, and you can move to those problems until much later in your delivery, perhaps once you're profitable. Okay, so you don't have to worry about all of that until you're profitable. Now this is important, which is when not to use microservices. So you avoid using microservices if the application isn't expected to scale rapidly. Okay, if you are not like building the next fastest startup and you're not scaling really fast, and you're building like a small company, then you probably don't need to use microservices if the domain is not well understood. So if it's something new like Gen AI or something like that, something new, and you're not sure about how it's changing, you don't want to use microservices because very fast changes are not easy with microservices. For applications with tightly coupled components, so if you want high consistency, if you want tight coupling between the services, a lot of interdependence, you don't want to use microservices. When your infra or deployment capabilities are basic, so like let's say if you have only one DevOps engineer and he doesn't have a lot of skills, he's just an intern, you don't want to have microservices because he'll have a hard time deploying all of that stuff. And if you don't need separate scaling or different parts of the application, yeah, for different parts. So if you don't want like one part should scale more than the others, and you know that traffic is going to be consistent amongst all the microservices or all the modules, then it's you can avoid microservices. And if inter-service latency would be problematic. So if let's say if you're building a real-time data exchange and you think that no matter what technology you use, you won't get that real-time effect, real-time data transfer between all the microservices, then I think you can avoid microservices. When regulatory or compliance needs favor centralized control. So if you have regulations and compliances that need you to maintain centralized control, then you want to avoid microservices. And if your application doesn't require high availability of fault tolerance, so not all so maybe your application is quite basic, it doesn't require like high amount of availability, so you can just go for regular monolith. And if you're building an internal application, so if you're a company, you're building an internal application just for your employees, like an attendance system or something like that, you don't need to have microservices. You can just build something really basic and get away with it, right? So this is the entire board, and we have covered through everything related to microservices. We covered a lot of topics, and in the end, I was just rushing through things because, like, I've been speaking for a long time, as you can understand, and I have like lots of other work to do. So I wanted to at the end, I just got desperate, and I just wanted to finish the video. Because I've been shooting since multiple days. It took me like 5 weeks to put up this board, to build this board. As you can see, it's a lot of effort, right? A lot of effort, because researching, compiling all my thoughts, distilling all the knowledge that I have, putting that in in the right order, and going through the board together. Like that's a lot of work, and yeah, and now I've been shooting for like almost a week because I get time to shoot after office, like later in the night. So yeah, it's been challenging to make this video, but I hope you appreciate this, and I have to bring this information out because I don't want to die with all of this information. I want to teach people. I want to give it to you so that you guys know all this. Yeah, the two things that I wanted to remind you again was the Ultimate Golang Bootcamp. Make sure you fill the form, and if you are interested in taking your career up a notch, then you might want to check out my private mentorship, right? That's the thing you want to apply for. The form for that is also in the description of this video. And let's quickly go recap over what all we have discussed. So we started with these references, like you have these article references, you can read them. Then we looked at some slides, we got some introduction into microservices, and then we got a 10,000 feet perspective of how to transition from monolith to microservices. Then we looked at how online businesses work and why they need to have microservices. Then we looked at microservices from multiple different perspectives, from the perspective of a non-technical founder, perspective of a technical founder, perspective of a tech architect, software engineer, indie developer, and DevOps, and why they would want to have microservices. And then we looked at the $1 million topic, which is decomposition. We started learning about decomposition with business capabilities, with subdomains, by transition. We learned about the triangle pattern and the database per service pattern. Then we learned about the ideal characteristics of microservices. And is there a limit on the number of microservices? And if microservices are so great, then does that mean monolith is an anti-pattern? It's not an anti-pattern, right? We worked about with challenges with microservices, which we introduced some of the challenges, like the big ball of mud, and then the latency due to sharing data between microservices. We looked at solutions. So the first solution was the inter-service communication. We'll talk about that. Then we talked about the scaling client problem and how you can have multiple clients, and how the solution will be API gateways, backends for front-ends pattern, and the distributed API gateways, and then over-engineered solution, which was the load balance distributed API gateway. And then we looked at inter-service communication, like how do microservices communicate. So we looked at the general life cycle of a system, then how do microservices come into being, then how do microservices interact with each other, and they lead to a lot of a lot of communications, synchronous communications, and how you can start having these Redis cache to reduce the amount of calls being made to each microservices. Then you had redundant data storage, streaming between services, and how you can stream using interfaces, and how you can stream between the front end and the back end as well. we started looking at event-driven architecture. So this was like the main turning point in our video, where we learned about events and how and what events are and how they work. We learned about unkeyed, keyed, and entity events. We learned about how you can design events with different ways. We learned about queues. So events, to transfer events, we have queues or streams, and we learned about message queues. We learned about the queues, benefits of queues. We learned about the features of message queues, right? And then we learned about pub sub, which is like just a little more complex than queues, but much better also. So we learned about the pub sub features. We learned about use cases. We learned about what queues are. Sorry, what pub sub is, the benefits of pub sub, the 4 key components. Then we looked at event streams. So what streams are, their key components, the advantages of streams, how the streams work, the features, the message delivery options, and the delivery models and the advantages. I think we've already covered that. Then we looked at the event bloat problem and how events start becoming like really big, and how do you manage that. We have a solution here with an example. We looked at how the difference between queues and event streaming, and then we went through a complete event-driven architecture takeaway. Then we talked about how events can be processed. So you can transform the event with all these different methods, right? And why you would want to transform the events. Then we looked at some event-driven processing basics, so like the how of event processing. Then we looked at batch processing, key reasons, how it works, when to use it. And then we compared that with event processing. And then we learned about how you can scale an event-driven system. So we learned about some methods like the servicing, like scaling microservices with service registries, and why would you want to do that. We looked at some non-conventional and some conventional ways of scaling an event-driven system. We looked at some more concepts, some very important concepts that didn't fit into the board, so I covered them separately. Then we looked at some considerations for synchronous and asynchronous microservices, and some microservice consideration and what you would want to think before building microservices. And then we looked at the hexagonal architecture. I think you've understood that really well with ports, adapters, driving side, driven side, and the application, which is the hexagon. Then we learned about failure and resilience, and why you would want to have failure resistant or highly resilient microservices, and how do you do that in the first place. Then challenges with microservices, because microservices are not perfect, they're not the silver bullet, and there is something in between called the modular monolith, and you might want to just use that if you're not building something very complex. And then also we looked at when not to use microservices. Now, one thing that I need from you is I want you to share this video, because and I want you to bookmark this. I want you to come back to this, keep coming back to this, keep learning, relearning, because there's a lot of stuff we covered. And all of this is going to help you, like I said, until the time you become a CTO of a massive company. This is going to help you. Thank you so much for watching this video. Thank you so much for sharing this with your friends. And if you haven't subscribed to this channel, make sure you subscribe. And in the next video, like I said, we are covering a lot of stuff. So if you want to watch that video, do let me know in the comments that, hey, you know, Akhil, work on this video. I would like to watch it. And then I plan to create a like apart from this video, which is the event-driven architecture patterns video, I want to create a distributed systems video like this, you know, concepts, and then like a system design video like this, a concept video, you know, where we'll cover all the system design concepts. So with event-driven architecture patterns, which is the next video, we'll cover ETL, we'll cover eventual consistency, distributed transactions, we'll deep dive into Kafka concepts, we'll learn more about stream and event processing and how real-time events works, and patterns, reliability, failure management, containerization, orchestration of microservices, monitoring and tracing. And we'll learn about all of these different different patterns for event-based, event-driven architecture microservices. Okay, we'll learn all these patterns, and we'll learn some deployment patterns, all of that as well. All right, so thank you so much, guys, and I will see you in the next video. It's been a long, tiring journey for me, so I'll take like 1 week. I won't create any content. I'll just focus on my office work. Because I have to like keep sitting for a long time to make these videos, all right? So thank you so much for watching, guys, and I'll see you in the next video.